Hello there, and welcome to Life Beyond Seen, where curiosity gets cozy and science takes the scenic route to slumber. Tonight's gentle journey is heading somewhere most people will never visit, and honestly, a place that might be happier staying unvisited. We're going down into the Tonga Trench, one of the deepest, most intense and most unsettling parts of the ocean on Earth. It's the kind of place that makes even experienced scientists pause for a moment before they speak, not because they're being dramatic, but because the numbers down there don't behave like friendly numbers, they behave like warnings. And before we drift too far into the dark, let me ask you something simple. Where are you listening from tonight? Are you tucked into bed with the lights low, or are you still awake somewhere that's bright and busy? And what time is it in your little corner of the world right now? It feels fitting to talk about a place where time moves differently for machines, where every second of exploration cost effort, planning, and nerve. If you find this kind of quiet science soothing, or if you like the feeling of learning something strange while your mind slowly unwinds, I'd be grateful if you gave the video a like and maybe subscribed. It helps this calm little space reach more people who could use a soft landing at the end of a long day. Now settle in, let your shoulders drop, let your breathing slow, because far out in the Pacific Ocean, beyond the postcard blues and the gentle surface waves, there's a line in the earth where the seafloor simply gives up and falls away. And the deeper we go, the more the Tonga Trench begins to feel less like a location and more like a question the planet refuses to answer quickly. The Tonga Trench still terrifies scientists for a reason that has nothing to do with ghosts or sea monsters, and everything to do with how real it is. It is terrifying in the way a mountain is terrifying when you're standing too close to the edge. It's terrifying in the way a storm is terrifying when you realise the sky is not asking your permission. The trench is not evil, it's not angry, it's not even alive. But it is powerful in a way that doesn't care what humans are used to. When most people imagine the ocean, they picture the top layer. Sunlight, waves, maybe a boat rocking gently, maybe a coral reef, maybe a dolphin doing something photogenic. Even when people imagine the deep ocean, they often imagine a smooth, empty darkness, like a giant underwater night sky. But trenches are not smooth. They are wounds in the planet's crust. They are steep, sharp, and abrupt. They are places where the Earth has folded in on itself, where one part of the planet is being shoved down under another part, like a slow-motion collision that never ends. The Tonga Trench sits in the South Pacific, stretching near the island nation of Tonga, and it reaches down to depths that sound like exaggerations. If you drop the world's tallest buildings into it, they would vanish. If you could somehow place Mount Everest inside it, the peak would still be underwater. That is hard to picture because your brain is built for everyday scale. Your brain understands hills, lakes, and maybe a tall city building. But it does not naturally understand a crack in the earth that goes down for nearly 11 kilometres. That depth is not just impressive, it is punishing, it is crushing. It is a place where pressure doesn't feel like a concept anymore. It becomes a physical force that will destroy anything that isn't built with obsessive care. Every piece of metal, every seal, every window, every joint on a submersible has to be designed like it's going to war. Because it is. Down there, water doesn't behave like the water in your glass. It is denser. It is heavier. It presses in from every direction with a force that is difficult to explain without numbers. So let's use numbers anyway, because numbers are honest. At the surface, you're under about 1 atmosphere of pressure. That's the pressure of the air around you. At 10 meters underwater, the pressure roughly doubles. At 100 meters, it's about 11 times the pressure at the surface. Now keep going, keep stacking that weight. By the time you reach the deepest parts of the Tonga Trench, the pressure is over 1,000 times what you feel right now. It is like balancing a skyscraper on every square inch of your body. If you're listening in bed, warm and safe, that might sound distant, like trivia. But for scientists, it's personal. Pressure is the first reason the trench is frightening. It means the environment is not forgiving. It means mistakes do not come with second chances. It means exploration is slow, expensive, and tense. You can't just swim down there with a camera and a brave attitude. The trench does not care how brave you feel. It will crush your bravery into a compact, unrecognisable shape. And yet, pressure alone is not what makes the Tonga Trench so unsettling. There are other trenches. There are other deep places. The Mariana Trench gets most of the fame, and it deserves it. But the Tonga Trench has a different kind of reputation. It is tied to something else. Something that happens not in the water, but in the rock below it. It sits above one of the most active and complicated subduction zones on Earth. A subduction zone is where one tectonic plate slides beneath another. If that sounds calm, it isn't. It is the slowest, most unstoppable grind you can imagine. It is a collision happening over millions of years, with the energy of continents behind it. The plates don't glide smoothly like ice skaters. They lock, they strain, they jerk, they release. That release is an earthquake. Now here's where it gets strange. Most earthquakes happen relatively close to the surface, at least in geological terms. They happen where rock is brittle enough to snap. But near Tonga, scientists observe something that feels wrong the first time you learn it. Deep focus earthquakes. These are earthquakes that occur hundreds of kilometers beneath the surface. In some cases, they happen at depths where the rock should not behave like brittle rock anymore. It should be too hot, too pressurized, too plastic. It should deform slowly instead of breaking suddenly. And yet, it breaks anyway. This is one of the biggest reasons the Tonga Trench terrifies scientists. Not because it is deep, but because it seems to break rules that feel basic. It produces earthquakes in places where earthquakes should not happen. It creates seismic events so deep that they challenge how we think the planet works. Imagine squeezing a piece of warm wax. It bends, it squishes, it does not crack like a cold rock. Deep in the earth, temperatures rise, pressure rises, rock changes behaviour, it becomes more like wax. So why do we still see sudden snapping events far below the surface near Tonga? Scientists have theories, and some of them are unsettling in their own way. One idea involves water. Not water sloshing around like an underground river, but water trapped inside minerals. When oceanic crust is forced down into the mantle, it carries hydrated minerals with it. Under immense heat and pressure, those minerals can release water through chemical reactions. That released water can weaken the surrounding rock. It can reduce friction. It can create conditions where a sudden slip becomes possible. There is also the idea of phase transitions. Deep in the earth, minerals can change their crystal structure under pressure, snapping into a new form. That change can happen quickly, like a sudden rearrangement. If it happens on a large scale, it could contribute to deep earthquakes. Think of it like a solid reorganizing itself in a way that releases energy, not gradually but abruptly. Another possibility involves the slab itself, the subducting plate. The Tonga subduction zone is one of the fastest on Earth. The plate is being pulled down at an incredible rate, geologically speaking. Some scientists believe the slab is under such intense stress that it can still fracture, even deep down. It is like forcing a thick board to bend too far. At some point it stops bending and starts breaking. And if you're thinking, that's fascinating, you're right. But if you're thinking, that sounds dangerous, you're also right. Because the forces involved are not small. The trench is not just deep. It is connected to a machinery of the planet that can release energy on a scale that humans cannot control. That's where the fear comes in. It's the fear of not fully understanding. It's the fear of knowing enough to see the problem but not enough to predict it. The Tonga region is capable of producing massive earthquakes. It is also capable of producing tsunamis, and tsunamis are one of the few natural events that can turn the deep ocean into a fast-moving weapon. A tsunami in deep water is not a towering wall. Out in the open ocean it can be subtle, a long, low swell moving at the speed of a jet plane. Ships might not even notice it. But when it reaches shallower water, it slows down and the energy stacks upward. That's when it becomes the nightmare image people recognise. The challenge with tsunamis is that they don't always behave in simple ways. The ocean floor is not flat, the coastline is not uniform. The wave can refract, reflect, amplify or split. It can arrive in multiple surges, it can pull water out before it returns. And in regions around Tonga, where earthquakes and volcanic activity can happen together, predicting what will happen is even harder. Because it's not just earthquakes, the Tonga region also sits near a complex volcanic system. Volcanoes under the sea do not behave like volcanoes on land. They can erupt quietly, building structures over time, or they can erupt violently, blasting water, steam, ash and rock into the atmosphere. Underwater eruptions can trigger tsunamis too, not just from the force of the explosion, but from the collapse of volcanic structures, from landslides, from sudden displacement of huge volumes of water. If you remember the massive eruption of Hunga Tonga Hunga Ha'apai, you've already seen how surprising this region can be. That eruption sent shockwaves around the globe. It generated tsunamis that reached distant coastlines. It injected material high into the atmosphere. It was a reminder that the Pacific is not just a beautiful ocean. It is an active system with deep connections between sea and sky. And what makes scientists uneasy is that even with satellites, seismometers, and decades of research, there are still gaps. There are still things we do not measure well enough. The deep ocean is hard to monitor. Instruments are expensive. Maintenance is difficult. The environment is harsh. Data can be incomplete, and the trench is far from most major research centres, which makes consistent observation harder. So the Tonga Trench becomes this combination of extremes: extreme depth, extreme pressure, extreme geology, extreme uncertainty. It is not one fear, it is a stack of fears layered like the water above it. Then there's the biology, which adds a different kind of unease. Life in the deepest parts of the ocean is not supposed to be thriving, at least not in the way we usually imagine life. There is no sunlight, no photosynthesis, no warm, shallow reefs. And yet, life exists anyway. The Hadal zone, the deepest region of the ocean, is named after Hades, the underworld. It's a dramatic name, but it fits. It is dark, it is cold, it is isolated, and the creatures that live there often look like they were designed by someone who had never seen a normal fish. Scientists find amphipods, small crustaceans that look like pale shrimp, scavenging in the darkness. They find strange snailfish adapted to pressure so high that the proteins in most animals would fail. They find microbes living in sediments, surviving on chemical energy rather than sunlight. It is a reminder that life is stubborn. It does not need comfort, it needs opportunity. But here's the part that makes it unsettling again. Humans have found plastic in deep trenches. We have found chemical pollutants. We have found traces of our surface world in places that should have been untouched. That means even the deepest, most remote place on Earth is not truly isolated from us. The trench is not just a geological feature. It is also a mirror. It reflects how connected everything is, how the ocean circulates, how particles sink, how currents move, how human impact spreads. Scientists don't just fear the trench because it is dangerous. They fear it because it is honest. It shows what the planet is doing and what we are doing, whether we like it or not. Exploring the Tonga Trench is not like exploring a forest. You can't walk into it and look around. You send machines, you send instruments, you send robotic vehicles that cost as much as houses, sometimes as much as buildings, and then you wait, you listen. You hope the pressure doesn't find the smallest weakness. Even communication is difficult. Radio waves don't travel through seawater well. You can't just call the submersible like it's a phone. You use acoustic signals which are slow and limited. It is like trying to have a conversation through a thick wall using knocks and echoes. That isolation adds to the tension. When a vehicle goes down into the trench, it is alone. It is out of reach. If something goes wrong, you cannot rescue it quickly. You cannot send a diver. You cannot pull it out with a rope. You can only wait and see if it returns. That's why scientists respect trenches. It's not fear in the childish sense. It's fear in the adult sense, the kind that comes from understanding consequences. And the Tonga Trench is particularly challenging because it's not just deep, it's active. The seafloor there is shaped by tectonic forces. It is not stable. It is not a quiet valley. It is a place where the ground itself is being rearranged. When you look at maps of the ocean floor, you might imagine it as a smooth gradient, like a gentle slope down into the abyss. Trenches are different. They are steep. They are narrow. They can have complex walls. They can have landslides. They can have sediment shifting. They can have sections that are difficult to navigate with instruments. Now imagine trying to map that in the dark, under crushing pressure, with limited communication, and with a vehicle that has to survive every second of it. It's a slow process, it's a careful process, and it's why we still know less about parts of the deep ocean than we know about the surface of the moon. That might sound ridiculous at first, but it's true in a practical sense. The moon is easier to observe from a distance. The deep ocean hides behind kilometres of water. It is not visible from above. You have to go there to see it, and going there is hard. So when people ask why the Tonga Trench terrifies scientists, the answer is not one dramatic reason. It's the combination. It's the way it compresses every difficulty of ocean science into one location. Pressure, darkness, distance, mechanical risk, biological mystery, geological violence, and the uncomfortable truth that we are still learning how it works. And if you're wondering whether the trench is dangerous to people directly most of the time, no. Most of the time it sits there quietly, far from daily life, doing its slow tectonic work without anyone noticing. But the processes connected to it can have wide effects. Earthquakes can trigger tsunamis. Volcanic eruptions can affect the atmosphere. Changes in the deep ocean can influence circulation over long timescales. It's also a reminder that the Earth is not finished. It is not a completed object. It is still forming itself. The Tonga Trench is one of the places where the planet is actively recycling its crust, dragging old seafloor down into the mantle to be transformed into something new. That recycling is part of why Earth remains dynamic. It is part of why continents shift. It is part of why volcanoes exist. It is part of why the surface is renewed over geological time. Without subduction zones, the planet would be different. Possibly quieter, possibly less habitable, but also less alive in its own way. There's a strange comfort in that if you let it settle in. The trench is terrifying, but it is also part of the system that keeps Earth from becoming stagnant. It is destruction that makes room for creation. Not in a poetic way, but in a physical way. Rock goes down, melts, rises again elsewhere. The planet circulates itself. And still, the trench keeps its secrets. Scientists can measure earthquakes. They can map the shape. They can collect samples. They can observe life. But they cannot sit at the bottom and look around with their own eyes for long. They cannot easily build permanent stations down there. They cannot fully simulate the environment in a lab for long periods. So every expedition feels like a small step into a place that remains bigger than our understanding. And while you're listening to this, safe and comfortable, it's worth noticing how your mind reacts to the idea of that depth. Some people feel fascinated, some feel uneasy, some feel a quiet thrill. That reaction is part of why trenches hold power over us. They are one of the few places on Earth that still feel truly beyond our control. Not because we haven't tried, but because the environment sets the terms. The trench doesn't negotiate. It doesn't compromise. It simply exists. Now, as we keep moving deeper into this story, it helps to start with something simple, a mental picture of where the Tonga Trench actually is, what it looks like on the map, and why it sits there in the first place. Because once you understand the location, the shape, and the tectonic setting, the rest of the mystery starts to take on a clearer outline, like your eyes adjusting slowly to darkness. So imagine the Pacific Ocean, vast and restless. Imagine the island chains scattered across it like stepping stones. Tonga sits in a region shaped by plates that are constantly shifting. The Pacific plate is moving, pushing, diving, interacting with neighbouring plates in a complicated dance that is anything but graceful. In this area, the Pacific plate is subducting beneath the Indo-Australian plate, creating the trench. That subduction is fast, and it creates a chain of volcanoes, earthquakes, and deep geological structures that make the region one of the most active on the planet. And if that sounds like a lot of movement for something that seems so still from the surface, that's the point. The surface can look calm while the planet underneath is in motion. That contrast, calm above, violence below, is another reason the Tonga Trench unsettles people who study it. It is a reminder that what you see is not always what is happening. Even the water above the trench can be deceptively peaceful. The ocean doesn't show you what it's sitting on. It doesn't reveal the cliff edge. It doesn't mark the boundary with a warning sign. It just rolls on, blue and endless, hiding the fact that beneath it the seafloor drops away into one of the most extreme environments on Earth. And as we shift from this broad view into the specific details of the trench itself, its shape, its depth, its strange behaviour, we start to see why it remains such a strong focus for scientists who want to understand not just the ocean, but the planet. Because the trench is not just a hole, it is a process. It is the surface expression of deep forces. It is the visible edge of an invisible machine. And once you start thinking of it that way, the fear becomes clearer. It is the fear of standing near something enormous, something active, something that has been operating for millions of years, and realizing that you can measure it, you can model it, you can describe it, but you cannot stop it, and you cannot fully predict what it will do next. That is the kind of fear that doesn't make you panic. It makes you quiet. And that quiet is where the next part begins, because now that we've met the trench as an idea, it's time to look at the moment where the ocean floor stops being familiar and starts becoming something else entirely, where the map turns from gentle slopes into a sudden drop, and where the Pacific begins its long descent into the deepest places on Earth. A trench that doesn't want to be understood is not a poetic idea. It is a practical one. It's what it feels like when you're looking at a place on Earth that refuses to behave like the tidy diagrams in a textbook. It's what it feels like when you send down your best instruments, collect your best data, and still come back with gaps you can't explain without shrugging and saying, "We're not sure yet." The Tonga Trench is one of those places. If you've ever watched a map of the ocean floor, you might have noticed how calm it looks at first glance. A slow gradient here, a ridge there, a few scattered seamounts like bumps under a blanket. From far away, the deep sea looks like a quiet landscape. But when you zoom in on trenches, that calm picture breaks. The seafloor doesn't gently slope down, it drops. It collapses into a long, narrow scar that runs across the planet like a tear in fabric. And the Tonga Trench is not just any tear, is one of the deepest and one of the most geologically intense. Scientists have been studying trenches for a long time. They've mapped them with sonar. They've measured earthquakes around them. They've studied the chemistry of water and sediment nearby. They've watched how described plates move and interact. They've done all the things science does when it tries to turn the unknown into something measurable. So why does this trench still feel like it's resisting understanding? Because it sits at the intersection of extremes. It combines the deepest ocean environment with one of the most active tectonic systems on Earth. It is not a static hole, it is a moving boundary. It is a place where the planet is actively recycling itself, where the crust is being dragged down into the mantle and transformed under heat and pressure that no surface creature was ever meant to witness. And it is doing this with a speed and complexity that makes even experienced geophysicists uncomfortable. One reason is that the Tonga subduction zone is fast. In tectonic terms, it is almost aggressive. Plates are always moving, but here, the Pacific plate is sliding beneath the Indo-Australian plate at one of the highest rates on Earth. This matters because speed changes everything. A slow-moving subduction zone can still produce massive earthquakes, but a fast one can create different patterns of stress, different deformation, and different behaviours in the slab as it sinks. The slab in this case is the piece of oceanic plate being pushed downward. It is not a thin sheet. It is a thick, cold, heavy section of Earth's outer shell, and it is being forced into a hotter, denser interior. That is not a gentle process. It is a geological struggle. The slab bends, cracks, heats, and changes. It releases water from minerals. It interacts with surrounding mantle material. It generates magma that rises and feeds volcanoes. It stores stress like a compressed spring. Then sometimes it releases that stress suddenly. But the Tonga region doesn't just do the expected kind of earthquakes. It does deep earthquakes. Very deep earthquakes. And this is where the trench starts to feel like it's keeping secrets. Most people have heard of earthquakes happening near the surface. A fault breaks, the ground shakes, buildings sway, and the event is over in seconds or minutes. That's the kind of earthquake we experience directly. That's the kind that damages cities. Deep focus earthquakes are different. They happen far beneath the surface, sometimes hundreds of kilometers down. They can still be powerful and they can still be detected across the planet, but they don't fit neatly into the usual story of how rock behaves. Because deep down, rock is not supposed to snap. Near the surface, rock is cold enough and brittle enough to fracture. That's what a typical earthquake is, a sudden fracture and slip along a fault. But deeper inside Earth, temperatures rise and pressure increases. Rock begins to deform more like a thick, slow-moving solid. It should bend. It should creep. It should flow, not break suddenly like a dry stick. So when scientists observe a powerful earthquake at, say, 500 kilometers depth, their first reaction is often the scientific version of blinking twice. How is that happening? What exactly is breaking down there? What does a fault even mean at that depth? The Tonga subduction zone is one of the most important regions on Earth for studying this problem because it produces some of the deepest earthquakes ever recorded. It is part of a broader region that includes the Tonga Trench system, and it has generated deep seismic activity that pushes the limits of what we expect. There are several theories for why deep focus earthquakes happen, and none of them feel fully satisfying yet. Not because the scientists aren't clever, they are, but because the Earth is complicated, and because we can't easily go down there and watch it happen. We're trying to understand a process that occurs hundreds of kilometers beneath the surface using indirect signals. That is like trying to understand a conversation by watching ripples on a pond. One idea is dehydration embrittlement. It sounds technical, but the concept is fairly simple. Oceanic crust contains minerals that hold water in their structure. Not liquid water sloshing around, but water-bound chemically. When the slab sinks, it heats up. Under heat and pressure, those minerals change. They release water. That water can weaken the surrounding rock and allow sudden slip to occur. It's like turning a dry surface into a lubricated one at exactly the wrong moment. Another idea involves phase transitions in minerals. At certain depths and pressures, minerals can change form. Olivine, for example, a common mineral in the mantle, can transform into different structures as conditions change. These transformations can happen quickly and can create instability. Some researchers have suggested that this sudden rearrangement might contribute to deep earthquakes. There's also the concept of thermal runaway. If a small region starts deforming, it generates heat. That heat makes the material weaker. A weaker material deforms more. More deformation creates more heat. It becomes a feedback loop, and suddenly you get a rapid failure event that looks like an earthquake, even at depths where brittle fracture should be unlikely. All of these ideas are plausible, none are simple, and none can be tested in a direct, satisfying way, because we cannot drill to those depths. We cannot place a camera down there. We cannot scoop up a fresh sample of a fault zone from 600 kilometers below the surface. So instead, scientists build models. They run simulations. They compare seismic wave patterns, they study how waves travel through the Earth, how they reflect, refract and change as they pass through different materials. They infer what must be happening based on the signals they receive. And that brings us to another reason the trench feels like it doesn't want to be understood. The Earth is noisy. Seismic signals overlap. The ocean environment adds complications. Instruments have limits. Coverage is incomplete. The data is never perfect. Even the best models are only as good as the assumptions inside them. And in a place like Tonga, assumptions are dangerous. Because the subduction zone is not a simple, smooth plane. It is not a clean slab sliding under another plate like a sheet of paper. It is fractured. It is bending. It may be tearing in places. It interacts with mantle flow. It produces complex patterns of stress and deformation. It creates back arcs spreading behind the volcanic arc, which adds another layer of motion. So you don't just have one plate going down, you have a whole region being rearranged. Behind the Tonga Trench lies the Lau Basin, an area of back arc spreading where the crust is being pulled apart. That might sound like the opposite of subduction, and in a way it is. One part of the region is being consumed while another part is being created. That combination creates complicated forces, like a tug of war where the rope is also melting and reforming as you pull it. This is why geologists and geophysicists pay so much attention to this region. It's not just because it's deep, it's because it's active in multiple ways at once. And then there is the fact that trenches are not just deep, they are steep. The geometry matters. A trench is like a sharp edge on the seafloor, and the angle at which a slab descends changes how stress is distributed, how water is carried down, and how magma is produced. In the Tonga region, the slab is subducting at a steep angle. This steepness may help explain why the earthquakes can occur so deep. A steep slab can carry cold material deeper into the mantle before it warms up enough to lose its brittle properties. In other words, the slab stays rigid longer than it would if it were descending at a shallower angle. That's an unsettling thought if you're someone who studies the planet's interior. It suggests the Earth can transport cold, brittle rock deep into places where it normally shouldn't survive as a brittle structure. It suggests the interior is not as smoothly layered as we like to imagine. The deeper the slab goes, the more it interacts with different mantle conditions. It may stagnate in some regions. It may sink straight down in others. It may fold or buckle. It may break. And if it breaks, it could change how stress is transferred and released. This is not the kind of system you can understand with one clean explanation. It's the kind of system that forces scientists to speak carefully. And while all of this is happening below, the trench above it remains difficult to study for a simpler reason. It's far away. It's remote. It's expensive to reach. And the deep ocean is hostile to machines. When scientists explore the trench directly, they rely on submersibles and landers. A lander is essentially a device that sinks to the bottom, sits there, collects data, maybe takes images, maybe collects samples, and then returns to the surface. The engineering sounds straightforward until you remember the pressure. At depths near the Tonga Trench, the pressure is so high that small design flaws become catastrophic. A tiny crack can become a failure point. A seal that works at shallow depths can leak at Hadal depths. A material that performs fine in a lab can behave differently after hours under crushing force. Even the simplest act of taking a photograph becomes a challenge. You need a camera that can survive. You need lights because sunlight is gone long before you reach the bottom. You need power. You need communication. You need a housing that won't implode. An implosion is not a dramatic word here. It is a real risk. If a pressure vessel fails at depth, it can collapse instantly, and the energy release can be violent enough to destroy the entire system. That's why deep-sea engineering is cautious. That's why it's expensive. That's why every mission feels like a calculated risk. And then there's navigation. Underwater GPS doesn't work. Radio signals don't travel well through seawater. You can't just steer a vehicle like you're driving a car. You rely on inertial navigation, sonar, acoustic positioning. All of these have limitations, especially in a deep trench where the walls can interfere with signals. so the trench becomes hard to reach, hard to map, hard to observe, and hard to measure in real time, and the result is that it stays partly unknown. That unknown space is where fear grows, not the fear of a monster, but the fear of incomplete knowledge. Scientists are trained to be skeptical. They don't like mystery for mystery's sake. They like explanations that can be tested. They like patterns that can be repeated. They like data that can be verified. The Tonga Trench doesn't always offer that comfort. It offers fragments. It offers hints. It offers observations that sometimes raise more questions than they answer. For example, when researchers study the deepest ocean ecosystems, they find life where it shouldn't be easy for life to exist. That's not just interesting, it's challenging. It forces questions about how energy moves through the deep ocean. At the surface, life is powered mostly by sunlight. Photosynthesis creates the base of the food chain. But in the trench, there is no sunlight. The base of the food chain is different. It depends on organic material sinking from above, on marine snow, tiny particles drifting down. It depends on carcasses that fall like rare feasts. It depends on microbial processes in sediments. But even that is not always enough to explain what is found. Scientists have discovered that some trenches can act like traps, collecting organic material in a way that creates surprisingly rich ecosystems compared to surrounding deep plains. The trench geometry can funnel debris downwards. Currents can deposit material. It can become a deep, dark collection point. This is one reason trenches are biologically important. They're not just empty voids. They can be hotspots of deep-sea activity. But this too is complicated. Not all trenches behave the same way. The Tonga Trench has its own patterns of currents, sedimentation, and nutrient flow. It is influenced by the surrounding ocean and by geological activity. Understanding how life survives there requires understanding the physical environment, and the physical environment is tied to the trench's shape and to the broader circulation of the Pacific. Now add one more uncomfortable detail. Humans have found plastic pollution in deep trenches, microplastics, fibres, chemical traces, even in places that are far from any coastline, far from any city, far from any obvious source. This matters because it tells us the deep ocean is not isolated. It is connected to the surface through sinking particles, through currents, through the slow but steady movement of material. It means the trench is not just a natural mystery. It is also a record of human impact. And that is a different kind of unsettling, because it suggests that even the most remote, crushing, lightless environment on Earth is still part of our world. We don't get to pretend it's separate. When scientists go down into trenches, they don't just bring back data about geology and biology. They bring back reminders that the ocean is one system. What happens at the surface eventually reaches the bottom, so the trench becomes a place where multiple unknowns overlap. Deep Earth processes, deep ocean ecosystems, human impact, extreme engineering, sparse data. And all of that sits under the surface of an ocean that, from above, looks calm and ordinary. There's a certain kind of tension in that. The tension of knowing the planet has layers, and that the layers we live in are thin. The Tonga Trench is a boundary. It is a boundary between plates, between environments, between what we can reach easily and what we can only touch with machines. It is a boundary between the familiar and the extreme, and boundaries are where strange things happen. In biology, boundaries create diversity. The edge of a forest and a field can host more species than either environment alone. In geology, boundaries create activity. Fault lines, volcanic arcs, mountain ranges, trenches. The Tonga Trench is a boundary that happens to be hidden underwater, which makes it easy to ignore until something reminds you it's there. A strong earthquake, a tsunami warning, a volcanic eruption that sends shockwaves around the world. Those are moments when the trench stops being an abstract place on a map and becomes something real, something active, something capable of reaching far beyond its location. That's when scientists feel the weight of what they study. Because studying the trench is not just academic. It connects to hazards. It connects to risk. It connects to real communities across the Pacific who live with the consequences of tectonic activity. The fear, then, is partly responsibility. It's knowing that the better we understand these systems, the better we can prepare and the more lives we might protect. But it's also knowing that understanding is hard and that nature does not promise clarity on our schedule. There is another detail that makes the Tonga region feel particularly intense. The way the subduction zone interacts with surrounding plates creates complex seismic patterns. Some of the largest deep earthquakes ever recorded have occurred in this region. These deep earthquakes are not usually the ones that cause the most surface damage, but they reveal something about the interior that we can't ignore. They are signals from the deep earth. And every time a deep earthquake happens, scientists get another data point, another clue. Seismic waves travel through the planet and are recorded by instruments around the world. The wave patterns can reveal changes in density, temperature, and structure inside the Earth. They can help map the slab as it descends. In that sense, the trench becomes a natural laboratory, a place where the Earth is running experiments for us, whether we asked it to or not. But laboratories are usually controlled environments. The trench is not controlled. It is wild. It is immense. It is operating on timescales that dwarf human lives. So we gather data in bursts. We interpret. We revise. We argue. We propose new models. We wait for the next event. That cycle is normal in science. It's how understanding grows. But in a place like Tonga, the cycle feels heavier because the stakes are not just intellectual. And if you're someone who studies Earth systems, the trench can feel like a reminder of how much we still don't know about the planet we live on. We know the Earth has a crust, a mantle, a core. We know plates move. We know subduction happens. We know earthquakes are caused by stress release. We know volcanoes are fed by melting rock. But the details matter. The mechanisms matter. The exact conditions matter. And in the Tonga region, the details are still being worked out. This is why the trench doesn't want to be understood. Not because it has intentions, but because it exists in a realm where observation is difficult and the processes are complex. It is a place where we can't simply walk in and look around. We have to infer. We have to guess carefully. We have to be humble. And humility is not always comfortable. There is something else too. The trench is part of a broader story about the ocean itself. The deep ocean is not just a passive container. It is moving. It is circulating. It is layered. It stores heat. It stores carbon. It influences climate over long time scales. The Tonga Trench sits within the Pacific, which is the largest ocean on Earth, and the Pacific is not a quiet body of water. It is an engine. It drives weather patterns. It exchanges heat with the atmosphere. It supports ecosystems that feed billions of people. So when we talk about trenches, we're not talking about isolated pits. We're talking about parts of a system. And systems are always harder to understand than individual pieces. If you want to understand a single rock, you can hold it. You can measure it. You can test it. If you want to understand a trench, you have to understand the plate that forms it, the mantle it sinks into, the water above it, the currents that move through it, the organisms that live in it, the sediments that accumulate, the chemistry that changes with depth, the earthquakes that occur below, and the human activities that influence what sinks down. That's a lot to hold in one mind. It's also why the trench is so compelling, because it's one of the few places on Earth where you can feel, even through data and maps, that the planet is bigger than our daily concerns. It's a place where the numbers are so extreme that they force you to slow down and respect them. A depth of nearly 11 kilometers is not a detail you casually mention. It's a depth that changes what is possible. It changes how materials behave. It changes how life survives. It changes how exploration works. And the trench doesn't just sit there. It's connected to forces that can shake the entire planet. This is why, even though scientists are not usually the type to admit fear, the Tonga Trench earns something close to it. Not panic, not superstition, a quiet professional unease. the kind you feel when you're studying something that can't be paused, can't be stopped, and can't be fully controlled. And that unease is useful. It keeps people careful. It keeps them honest. It keeps them from pretending they know more than they do. Because when you're dealing with the deep ocean and the deep earth, pretending is not safe. Now, as we keep going, it helps to move from the idea of the trench as a stubborn mystery into the physical reality of what it looks like. Not just the depth number, but the shape, the slope, the suddenness of the drop, and how it changes the seafloor from something broad and rolling into something steep and dramatic. Because once you picture the moment where the ocean floor suddenly falls away, you start to understand why the trench doesn't feel like a normal place. It feels like a boundary you weren't meant to cross, and yet it's sitting there on Earth, waiting quietly beneath the waves as if daring anyone to look closer. If you've ever stood at the edge of something high, a cliff, a steep staircase, even the top of a tall building, you know the feeling that comes before you even move. Your body reacts before your thoughts fully catch up. Your stomach tightens. Your feet become more aware of the ground. Your brain does a quick calculation that sounds like, "Don't be careless." Now imagine that edge, but underwater. Imagine it hidden beneath kilometers of darkening blue. Imagine it stretching for hundreds of miles, not as a single dramatic drop, but as a long boundary where the seafloor stops being a gentle landscape and becomes something abrupt, steep, and severe. That is what a trench feels like, and the Tonga Trench is one of the sharpest examples we have. The ocean floor is often misunderstood because we rarely see it. On land, we are constantly reading the shape of the ground. We notice hills, we notice slopes, we notice valleys. Even if we don't think about it, our eyes and bodies understand terrain. But the seafloor is hidden, so it becomes abstract. People imagine it as a flat plane, like a smooth bathtub bottom. It isn't. The ocean floor has mountains, ridges, cliffs, plateaus, volcanoes, and cracks. It has entire mountain ranges longer than continents. It has valleys deeper than the Grand Canyon. It has places where the crust is spreading apart and places where it is being swallowed. And the most dramatic places of all are trenches, because trenches are where the seafloor seems to lose its nerve and drop away. The Tonga Trench is one of those places where the change is not subtle. If you were travelling across the seafloor in a submersible, the landscape might feel almost gentle at first. Not gentle in a comfortable sense, because you would still be in darkness and pressure, but gentle in terms of slope, a gradual descent, a wide plain, soft sediment, the quiet feeling of a deep ocean basin. And then the terrain would shift. The bottom would start to tilt downward more sharply. The sediment would change. The walls would rise on one side like a dark ridge. The slope would steepen. The space would narrow. And then at some point you would realise you're no longer on a broad ocean floor. You're on the edge of something that goes down much farther than your instincts want to accept. This is not just a dramatic way of describing it. It's the geometry of trenches. Trenches are narrow compared to the vastness of the ocean basins. They are like long, deep grooves carved into the sea floor. They are often only tens of kilometres wide, but they can run for thousands of kilometres. They are the deepest parts of the ocean, and they exist because of plate tectonics. If you want a simple picture, imagine the Earth's crust as a set of moving slabs. These slabs float on the mantle, which behaves like a slow, deforming solid over long timescales. Where slabs pull apart, you get mid-ocean ridges. Where slabs collide, one can be forced downward beneath the other. That downward bending is what creates a trench. But that bending doesn't happen gradually across an entire ocean. It happens at a boundary, a line, a zone where the plate is being pulled down into the earth. That line becomes the trench. The Tonga Trench forms where the Pacific plate is being forced beneath another plate system in the region. It is part of a long arc of subduction in the South Pacific, and it is one of the fastest subduction systems on Earth. That matters because the faster the plate moves, the more dramatic the bending can be. When a plate begins to subduct, it doesn't just slide down like a smooth ramp. It bends sharply. The front edge is pulled down and the rest of the plate follows. That bending creates enormous stress. The plate is being flexed like a massive sheet of rock, and rock does not like being flexed. The stress can crack the plate. It can create faults. It can allow seawater to penetrate into the crust. It can alter the minerals inside it. It can set the stage for earthquakes. All of this begins at the edge, right where the seafloor starts to fall away. So the drop is not just a landscape feature. It is a sign of something mechanical happening, a visible scar where the Earth is actively moving its crust into the interior. And when you look at bathymetry maps, the maps of ocean depth, the Tonga Trench stands out like a long dark line. The colours shift quickly, the depth contours pack close together, which tells you the slope is steep. In some places, the descent is so abrupt that it resembles an underwater cliff rather than a gentle valley. This suddenness is part of what makes trenches unsettling. They feel like they shouldn't be there. The ocean is already deep. It already feels endless. And then a trench appears, and it's as if the planet is saying, "You thought you understood deep. You are still in the shallow end." The change in depth is not just psychological. It changes everything about the environment. As the ocean floor drops, pressure increases rapidly. Temperature remains cold, but pressure becomes the dominant force. The water becomes denser. The physical properties of materials change. The behavior of sediments changes. The kinds of organisms that can survive changes. And light disappears long before you even get close to a trench. Sunlight fades quickly in the ocean. By about 200 meters, you're in the twilight zone, where light is dim and blue. By about 1,000 meters, sunlight is essentially gone. Below that, there is no natural light at all. So when you approach the trench, you are already in complete darkness. The drop is not visible like a cliff on land. You don't see it from far away. You detect it through instruments, through sonar, through changes in slope, through the way your vehicle's depth gauge keeps climbing. This makes trenches feel more like sudden absences than visible structures. You can't look ahead and see the bottom. You can only know it's there because the numbers keep changing. It's a strange way to experience terrain. On land, your eyes guide you. Underwater, especially in the deep, your eyes are almost useless unless you bring light. And even with light, you can only see a small patch at a time. The trench wall might appear as a looming shadow, a texture of rock and sediment sliding past the edge of your lamps. Everything outside that circle of light is unknown. That is another reason the trench feels like it falls away suddenly. It doesn't reveal itself gradually. It is there, and then it is not there. The seafloor under you goes from something you can imagine standing on to something that feels like it has been cut open. Now, scientists don't explore trenches the way we explore land. They don't walk across the seafloor. They map it from above using sonar, and they send down landers and submersibles for specific missions. Mapping is one of the first ways we learn where the seafloor falls away. Ships use multi-beam sonar, sending out sound waves that bounce off the bottom and return. By measuring the time it takes for the sound to return, scientists can calculate depth. With enough passes, they build a detailed map. But even mapping trenches is difficult. The deeper the water, the wider the sonar beams spread. Resolution decreases. The trench walls can create shadows where sonar doesn't reach. The shape is complex. And in remote regions like Tonga, full high-resolution mapping takes time, funding, and effort. So even today, there are parts of the trench system that are not mapped as well as we'd like. That matters because shape influences everything. A trench is not a simple V-shaped cut. It can have terraces, like steps. It can have landslide scars. It can have sediment fans. It can have narrow channels. It can have sections where the wall is steep and rocky, and other sections where it is coated in thick sediment. In some places, the bottom of the trench might be relatively flat, a narrow strip where fine sediments have settled. In other places, it might be uneven, shaped by recent seismic activity. And seismic activity is common here. When earthquakes happen near trenches, they can trigger underwater landslides. Sediment can slump down the walls. Blocks of rock can shift. the trench can change shape over time, not in a way humans notice day to day, but in a way that matters over decades and centuries. So when scientists describe the Tonga Trench as a place where the ocean floor suddenly falls away, they're also describing a place that is actively being reshaped. It is not a static canyon, it is a dynamic boundary, and that boundary has consequences far beyond the trench itself. Because when the seafloor falls away at a subduction zone, it is not just creating depth, it is creating conditions for earthquakes. The bending plate accumulates stress, the interface between plates locks and slips, the slab descends and changes, water is carried down, melting occurs, volcanoes form in arcs above the subduction zone, so the trench is the visible surface feature of a deeper system. It is the surface line that tells you something is going down here. In the Tonga region, that something is intense. The Tonga Trench is paired with a volcanic arc, the Tonga Volcanic Arc, which includes underwater volcanoes and islands. This arc exists because the subducting plate releases water into the mantle above it. That water lowers the melting point of mantle rock, producing magma. That magma rises and forms volcanoes. So the trench is not just a deep hole, it is part of a conveyor belt. Oceanic crust goes down, magma comes up, earthquakes happen along the way. The surface ocean above it remains calm, pretending nothing is happening. That contrast can be unnerving if you think about it too long, because it means the Earth can be doing something violent and powerful directly beneath a quiet surface. Now, if you were to drop something into the trench, it would not fall forever. It would sink through water that becomes colder and darker and more pressurized. It would pass through layers of ocean that are different in temperature and salinity. It would drift in currents you cannot see. It would eventually reach the bottom, where the water is near freezing, the pressure is crushing, and the environment is still. But even the bottom is not simple. Trenches can trap water masses. They can have unique circulation patterns. The shape can influence how deep water moves. In some trenches, water can become isolated for long periods, creating distinct chemical conditions. This matters because chemical conditions affect life, and trenches are not lifeless. There is a common assumption that the deepest ocean is a barren place, but the deepest parts of the ocean are not empty. They are sparse compared to shallow ecosystems, but they host organisms adapted to extreme pressure and low food availability. The trench environment is like a test of biological endurance. Every creature there has had to solve the same problem: how to survive under pressure that would destroy most life. Pressure affects membranes, it affects proteins, it affects how enzymes function, it affects how cells maintain structure. Deep-sea organisms have evolved adaptations, like flexible proteins and special compounds that stabilize their cells. One of the most famous trench dwellers is the Hadal snailfish, a soft-bodied fish that can live at depths where most fish would be crushed. It has a body adapted to pressure, and it lacks a swim bladder because a gas-filled bladder would collapse. It moves slowly. It exists in a world where fast motion is expensive. Amphipods, small crustaceans, are also common in trenches. They are scavengers, feeding on whatever organic material reaches the bottom. They can appear in surprising numbers around baited traps placed by scientists. These organisms are part of why trenches are scientifically valuable. They show us what life can do when conditions are extreme, but they also add another layer of unease, because they remind us that the trench is not just a physical abyss. It is a living environment. It is not dead space. It is a place with its own food web, its own chemistry, its own rhythms, and it is a place we have barely begun to understand. Now, the phrase "suddenly falls away" also describes the mental shift that happens when you realize how quickly the ocean becomes deep. At the surface, the ocean can feel like a large pool. Even if you know it is deep, the surface tricks you. It reflects the sky. It looks familiar. It looks manageable. But the moment you think about a trench, you realize the surface is only a thin skin. If you could remove the water and look at the seafloor directly, trenches would look like scars. They would look like deep cuts that should not exist on a smooth sphere. They would make the planet look damaged, even though they are part of how it works. That image is part of why trenches capture imagination. They are the closest thing we have to natural abysses on Earth. They are places where the planet seems to open up, and the Tonga Trench is particularly dramatic because it is part of a system that is not only deep, but also seismically active and volcanically active. So when the seafloor drops there, it is not dropping into stillness, it is dropping into a zone of motion. This is one reason scientists pay close attention to how the trench is shaped and how it changes. The slope, the sediment, the geometry of the plate interface. All of these influence earthquake behaviour. They influence how stress accumulates and releases. They influence the potential for tsunamis. In subduction zones, the most dangerous earthquakes are often megathrust earthquakes, where the boundary between plates slips over a large area. These events can displace the seafloor and generate tsunamis. The shape of the trench and the plate interface can affect where these slips occur. Now, Tonga is not always in the news for giant megathrust events, the way some other subduction zones are, but the region is still capable of large earthquakes, and it has a complex system that includes back-arc spreading and volcanic activity, which can contribute to hazards in different ways. For scientists, the trench is part of a broader hazard puzzle. Understanding the trench helps understand the system. Understanding the system helps improve monitoring and preparedness. But again, monitoring the deep ocean is difficult. Seismometers on land can detect earthquakes, but underwater instrumentation is harder to maintain. Tsunami sensors exist, but coverage is limited. The deep ocean remains under-instrumented compared to the surface world, so the trench remains partly unseen, even as it shapes events that can affect people far away. There is also a subtle point here. Trenches are not just deep because of the subduction process. They are deep because of the weight and structure of the plate itself. As the oceanic plate bends downward, it creates a depression. But the plate is also cold and dense compared to the mantle, which helps it sink. The slab is heavy. It pulls itself down. This is sometimes called slab pull, and it is one of the main forces driving plate tectonics. In the Tonga region, slab pull is strong. The slab is descending steeply and rapidly. That contributes to the trench's depth and to the overall tectonic intensity. So the trench is not just a passive result, it is part of a feedback system. The slab sinks, which deepens the trench, which reflects the bending and sinking, which continues. This is one reason the Tonga Trench can be so deep. It is part of a fast, steep, strongly driven subduction system. And that brings us back to the feeling of suddenness. Because when a system is fast and steep, changes can be sharp. The seafloor falls away, and with it your sense of scale. If you were to descend in a submersible, you would notice the numbers on the depth gauge increasing steadily. At first, it might feel like a slow drift. 1,000 meters, 2,000, 3,000. The pressure increases, the temperature drops, the outside world becomes black. But as you approach trench depths, the environment becomes more extreme. The pressure becomes harder to ignore. The margin for error shrinks. The vehicle's design becomes your entire safety. Even though the descent might take hours, the sense of crossing into another realm can feel sudden. Not because the descent is physically abrupt, but because your mind reaches a point where it can no longer treat the ocean as deep in the normal sense. It becomes something else. It becomes Hadal. That word, Hadal, refers to depths below about 6,000 meters, named after Hades. It is not a scientific term meant to scare people. It is simply a way to describe the deepest zone of the ocean, but the name carries weight, because the place is extreme. In the Hadal zone, the pressure is crushing. Food is scarce. The environment is cold. The trench walls rise like dark borders. The bottom is narrow. The sense of isolation is complete. And the Tonga Trench sits deep in that zone, one of the most extreme examples of it. This is why the trench feels like a sudden fall. It is a boundary not just in depth, but in conditions. Above, the deep sea is already harsh, but it is still within the range of what we have explored more frequently. Below, the trench depths are rarer. Fewer missions, less data, more uncertainty. So when the seafloor drops into the trench, it also drops into a zone of limited knowledge. That limited knowledge is part of what keeps scientists uneasy. Because when you cannot see something clearly, you cannot predict it as well. You cannot model it as confidently. You cannot test your ideas as directly. And in a region like Tonga, where the deep ocean is linked to active tectonics, uncertainty is not comfortable. Now, there is another aspect of trenches that often gets overlooked. Trenches are not only deep, they're also long. They stretch across the planet like scars, and they mark some of the most important boundaries in Earth's tectonic system. The Tonga Trench is part of the boundary that shapes the South Pacific. It is connected to the broader Ring of Fire, the belt of subduction zones and volcanoes that circles the Pacific. So the trench is not an isolated oddity. It is part of a global pattern. But it is one of the deepest and most active parts of that pattern. And that is why scientists study it so closely. They want to know why it is so deep. They want to know why the slab behaves the way it does. They want to know why deep earthquakes happen. They want to know how the trench affects ocean circulation. They want to know what life survives there. They want to know what signals from the trench can teach us about the Earth's interior. In other words, they want to understand the sudden fall, not just as a shape, but as a process. Because the fall is not the end. It is the beginning of the slab's descent into the mantle. It is the beginning of deep geological transformation. It is the beginning of the forces that create earthquakes and volcanoes. The trench is the visible edge of a deeper story. And as we continue, the next thing to notice is where this story takes place on the surface world. The Tonga Islands, the people living nearby, the surrounding ocean. Because it's easy to talk about trenches as remote features, but they exist in real regions with real communities, and the tectonic forces beneath them shape the world above in ways that are not always obvious until something happens. So with the trench edge in mind, that moment where the seafloor stops being a gentle basin and starts dropping into the deep, we can begin to look at the neighbourhood above it and the hidden forces beneath it, the ones that make this part of the Pacific feel quiet on the surface and intensely alive underneath. When people hear the name Tonga, they often picture something soft and calm. A chain of islands in the South Pacific, blue water, warm air, palm trees moving in a light breeze, the kind of place that looks like it was designed to lower your blood pressure. If you've ever seen photographs of Tonga, they tend to lean into that feeling. Sunlight on the water, boats floating lazily, a horizon that looks endless. And that image is not wrong. Tonga really is beautiful. It really is quiet in the way many island nations feel quiet, where the ocean seems to absorb sound and the pace of life feels slower. But there is a second Tonga that exists beneath that calm surface. A Tonga that doesn't show itself in postcards. A Tonga that is not soft at all. Because this island chain sits above one of the most active and powerful geological systems on Earth. It's the kind of contrast that makes scientists uneasy, and it's the kind of contrast that makes the Tonga Trench so compelling. The surface world looks gentle. The deeper world is anything but. To understand why this region is so intense, it helps to think of Tonga as sitting on the edge of something enormous, like a quiet town built on the rim of a volcano. Most days, nothing happens. People live their lives. The ground feels solid. The ocean feels steady. But underneath, forces are always at work, building stress, moving rock, shifting pressure, and rearranging the planet in ways that are too slow to notice until they are suddenly not slow anymore. Tonga is located in the southwestern Pacific Ocean, and it sits near a boundary between tectonic plates. That boundary is part of the larger Ring of Fire, the belt of subduction zones and volcanic arcs that surrounds the Pacific like a jagged crown. This is where a large portion of the world's earthquakes and volcanoes occur, and Tonga is positioned in one of the most active sections of that belt. The Pacific plate is moving, and in this region it is being forced downward beneath the plate system on the other side. This process is called subduction, and it is the engine that drives the trench. It is also the engine that drives much of the violence beneath the surface. Subduction zones are not gentle collisions. They are not like two cars bumping into each other and stopping. They are more like one car sliding under another and continuing to move, except the cars are hundreds of kilometers thick, and the collision is powered by the weight of the Earth itself. The subducting plate bends downward and sinks into the mantle. As it does, it drags rock and sediment with it. It carries water locked inside minerals. It changes under heat and pressure. It releases fluids. It triggers melting in the mantle above. That melting produces magma. That magma rises and feeds volcanoes. Meanwhile, the boundary between the plates locks and builds stress. And when that stress is released, earthquakes happen. So the violence beneath Tonga is not random. It is the expected result of a system that is constantly grinding and shifting. But what makes Tonga especially interesting and especially unsettling is how active the system is and how many different processes overlap in the same region. In some subduction zones, the story is relatively straightforward. One plate goes down, an arc of volcanoes forms above, earthquakes occur along the boundary, and the system continues. In the Tonga region, the story is more complicated. Behind the volcanic arc lies a back arc basin, the Lau Basin, where the crust is being pulled apart and new seafloor is forming. That means while one part of the region is being consumed, another part is being created. It is a zone of destruction and construction happening side by side. This creates a kind of tectonic tension. The subduction zone is pulling the region one way, and the back arc spreading is pulling it another way. The plates are not simply colliding. They're interacting in a complex shifting system. For scientists, complexity is not just interesting, it is also a warning sign. Complex systems are harder to predict. They behave in ways that are not always intuitive. They can have cascading effects. A change in one part can influence another part, and in Tonga those changes can happen quickly in geological terms. The Tonga Trench and its associated subduction zone are known for being fast. The Pacific plate is descending rapidly here compared to many other regions. That rapid descent can influence the steepness of the slab, the depth of earthquakes, and the overall energy of the system. When a slab descends steeply, it can carry cold material deep into the mantle. It can stay rigid longer. It can generate deep focus earthquakes. It can interact with mantle flow differently than a shallow slab would. And Tonga is famous for deep focus earthquakes. This is one of the key reasons scientists study the region so closely. Deep earthquakes are rare compared to shallow ones, and they challenge our understanding of how rock behaves. In the Tonga region, deep earthquakes occur at depths where rock should be too hot and too pressurized to break suddenly. Yet it does. So Tonga becomes a kind of natural laboratory for studying the deep earth. Every deep earthquake sends seismic waves through the planet. Those waves are recorded around the world. Scientists analyze them to infer what the slab looks like, how it is moving, and what the interior of the Earth might be doing. In a sense, Tonga is constantly sending signals from deep underground. Signals that say, something is happening down here, and you should pay attention. But there is another layer to the violence beneath Tonga, and it is one that people feel more directly. Volcanoes. The Tonga volcanic arc includes both island volcanoes and underwater volcanoes. Many of these are not household names. They're remote. They're rarely visited. Some of them are not even fully mapped. But they are active, and they are part of the system that makes this region so dynamic. Volcanoes in subduction zones form because the subducting slab releases water and other fluids into the mantle above. Those fluids lower the melting point of the mantle rock, producing magma. The magma rises because it is less dense than the surrounding rock. It collects in chambers. It erupts. This process can produce different kinds of eruptions. Some are relatively gentle, producing lava flows. Others are explosive, producing ash clouds and shock waves. Underwater volcanoes can be especially unpredictable because water interacts with magma in complex ways. When magma meets seawater, it can cool rapidly, fragmenting into fine particles. It can create steam explosions. It can generate pressure waves. It can trigger collapses of volcanic structures. Underwater eruptions can also produce tsunamis, either through explosive displacement of water or through landslides and collapses. And Tonga has provided a dramatic example of this in recent memory. The eruption of Hunga Tonga Hunga Ha'apai was one of the most powerful volcanic events in decades. It was not just a local event, it was global. It sent atmospheric shockwaves around the world. It generated tsunamis that reached far coastlines. It produced an enormous plume that reached high into the atmosphere. For many people, it was the first time Tonga appeared prominently in global news. For scientists, it was both a fascinating event and a reminder of how much energy this region can release. What makes such eruptions particularly unsettling is that they involve multiple systems at once. The volcanic system interacts with the ocean. The eruption interacts with the atmosphere. The shock waves travel through air. The tsunamis travel through water. The seismic signals travel through rock. It is a multi-layered event, and it highlights how connected Earth systems are. In other words, the violence beneath Tonga does not stay beneath Tonga. It can ripple outward. This is one reason why scientists are so interested in the Tonga region. It is not just about local geology. It is about understanding a system that can influence broader processes, from ocean circulation to atmospheric dynamics to seismic hazards. But even with all this, Tonga itself often feels quiet. That quietness is part of what makes the contrast so striking. People live on islands above a moving boundary. They fish, they travel, they build homes, they raise families, they experience storms, droughts, and the normal challenges of island life. And beneath them, the planet is in motion. This is not unique to Tonga, of course. Many people live near subduction zones: Japan, Indonesia, Chile, Alaska. But Tonga's position, above one of the deepest trenches and one of the most active deep earthquake zones, makes it especially intense. It is like living above a deep mechanical process that is always running. Most of the time, that process is quiet. It moves slowly. It builds stress. It releases small events that go unnoticed. But sometimes it releases something large enough to be felt. Earthquakes in the region can be frequent. Many are small, but some are large. Because the region is remote and sparsely populated compared to major urban centres, many earthquakes do not cause widespread damage, but they still matter, because they are signals of what the plates are doing, and they matter because earthquakes can trigger tsunamis. Tsunamis are not common everyday events, but they are part of the risk landscape for island nations in the Pacific. Tonga, like many places in the region, has to live with that reality. This is where the scientific fear becomes practical. It is one thing to study a trench as an abstract feature. It is another thing to know that the system connected to that trench can generate events that affect real communities. Scientists who study Tonga are not just studying a hole in the ocean. They are studying a boundary that can produce hazards. And hazards are difficult because they involve uncertainty. Earthquake prediction, in the strict sense of knowing exactly when and where a quake will happen, is not currently possible. Scientists can estimate probabilities. They can identify zones of risk. They can monitor seismic activity. They can improve warning systems. But they cannot say, this will happen at this exact time. Tsunami warnings can be issued quickly after an earthquake, but the exact behaviour of a tsunami depends on many factors: the shape of the seafloor, the location and depth of the earthquake, the direction of rupture, the presence of landslides, the coastline shape, the local bathymetry. In Tonga, the complex seafloor and the presence of both tectonic and volcanic sources make the hazard picture more complicated. So scientists approach the region with respect. They study it carefully. They build models. They install instruments where possible. They analyse events when they occur. but the region still surprises, and that is where the trench's reputation comes from. It is not just deep, it is unpredictable in the way active systems are unpredictable. Now, there is another aspect of Tonga's quiet neighbourhood that makes it scientifically interesting. The ocean around Tonga is part of the broader Pacific circulation. The Pacific is not a static body of water. It has currents that move heat, salt, nutrients and oxygen around the planet. Deep ocean trenches can influence local circulation patterns. They can trap water masses. They can create unique conditions for sediment accumulation. They can act as sinks for organic material. They can shape how particles move downward. So the Tonga Trench is not just a geological feature, it is part of the ocean system. This matters because the deep ocean plays a role in climate. It stores heat, it stores carbon, it exchanges gases with the atmosphere over long timescales. Trenches, by trapping sediments and organic matter, may play a role in long-term carbon storage. They may act as places where carbon is buried. They may influence deep ocean chemistry. Scientists are still exploring these ideas, and the Tonga Trench is one of the places where such questions can be studied. But again, studying it directly is difficult. The trench is remote. The depths are extreme. Missions are expensive. Instruments are hard to maintain. The environment is harsh. So even though Tonga's neighbourhood is quiet on the surface, it is a challenging place to observe. An observation matters because without it the models remain uncertain. This is one reason why the deep ocean remains one of the least understood environments on Earth. We have satellites that can observe the surface ocean. We have weather models that track storms. We have networks of seismometers on land. But the deep ocean is harder to instrument. When something happens deep underwater, like an earthquake or a volcanic eruption, we can detect it through seismic signals, and sometimes through changes in sea level. But we often lack detailed real-time data from the source region. This makes the system feel partly hidden, and hidden systems can be unsettling. The Tonga Trench and its surrounding region are hidden beneath water. The tectonic forces are hidden beneath rock. The deepest earthquakes occur far below where we can observe directly. The volcanic systems can be underwater, out of sight. So Tonga becomes a place where much of the action is invisible, but the consequences can still be felt. This is why scientists often describe the region in terms of contrasts: calm above, violent below, quiet islands, active boundaries, beautiful surface, intense interior. Now, it is worth remembering that the people of Tonga are not passive observers of this. They live with the ocean, they live with the land, they live with the reality of storms and waves and occasional seismic events. They have knowledge of their environment that comes from lived experience, from history, from tradition. Modern science adds instruments and models, but it is not replacing local understanding. It is adding another layer. And in a region like Tonga, layers matter. Layers of water above the trench, layers of rock beneath the islands, layers of history in the communities, layers of scientific data built over time. All of these layers create a picture that is more complex than the simple idea of a deep trench. Now, if you zoom out even further, you can see that Tonga's neighbourhood is part of a larger tectonic story in the Pacific. The Pacific plate is moving northwest. Subduction zones around the Ring of Fire are consuming it. Over millions of years, the Pacific plate will continue to shrink as it's subducted. The Tonga Trench is one of the places where that consumption is happening rapidly. This is a reminder that Earth's surface is temporary. Continents shift. Oceans open and close. Plates are created and destroyed. The quiet ocean surface is sitting on a planet that is constantly changing. And that is the deeper reason the Tonga region feels so intense. It is not just a place where things happen. It is a place where the planet is actively reshaping itself. If you could speed up time and watch the region over millions of years, you would see the trench migrating, the slab descending, the volcanic arc shifting, the back arc basin opening, islands forming and eroding, earthquakes flickering like pulses, it would look alive. But we don't experience Earth at that time scale. We experience it moment by moment. We experience the surface calm. We experience the quiet. And then sometimes we experience a sudden reminder of what is underneath. That reminder might be a tremor, a warning siren, a news report about an eruption, a wave that arrives when it shouldn't. Those moments are why the region commands respect. For scientists, the fear is not constant. It is not a panic. It is a background awareness. The awareness that the system is powerful, that it can surprise, and that understanding it fully is a long-term challenge. And that challenge is part of what draws people to study it. Because if you can understand Tonga's violent forces beneath its quiet neighbourhood, you can learn something about how subduction zones work in general. You can learn something about deep earthquakes. You can learn something about volcanic arcs. You can learn something about the deep earth. And in the process, you might improve hazard assessments. You might improve warning systems. You might contribute to safer communities. So the trench is not just a curiosity. It is part of a broader effort to understand Earth as a system. Now, as we move forward, it makes sense to look at the larger structure that Tonga is part of. The Ring of Fire is often mentioned, but it is rarely explained in a way that feels real. It sounds like a dramatic name, and it is dramatic, but it is also a straightforward description of where Earth's tectonic energy is concentrated. So the next step is to trace how the Tonga Trench fits into that ring, and why this particular section behaves the way it does. With a steep slab, fast subduction, deep earthquakes, and a seafloor that seems to be in constant motion even when the surface looks perfectly still. When people hear the phrase Ring of Fire, they often imagine something dramatic and obvious, like a glowing circle of volcanoes visibly burning around the edge of the Pacific. It sounds like a fantasy map. It sounds like something you'd see from space, a fiery halo drawn around the ocean. But the real Ring of Fire is both more subtle and more unsettling than that. It isn't a neat ring. It isn't always visible. Much of it is underwater, and instead of a continuous line of flames, it's a chain of boundaries, fractures, collisions, and sinking slabs that wrap around the Pacific like a jagged seam in the planet. It's also one of the clearest reminders that the Earth's surface is not stable. The Ring of Fire is where a large portion of the world's earthquakes happen, and where many of its volcanoes are found. It includes places that are famous for seismic activity: Japan, Indonesia, Alaska, Chile, and many others. But it also includes places that are far less famous, places that are remote, quiet, and hidden beneath open ocean. The Tonga Trench is one of those places, and when you look at Tonga as part of the Ring of Fire, you start to see it not as an isolated deep spot, but as one step in a much larger descent, a hidden staircase into the deep earth. That staircase is made of subduction zones. Subduction zones are the places where one tectonic plate is forced beneath another. If plate tectonics is the slow movement of Earth's outer shell, then subduction zones are where that shell is being recycled. Old oceanic crust is being dragged down into the mantle. New crust is being created elsewhere, mainly at mid-ocean ridges. The Earth is constantly renewing itself, but not gently. It renews itself through collisions, fractures, melting and grinding movement. And the Ring of Fire is where that renewal is most active. Now, the word staircase might make it sound like a tidy set of steps, but in reality, it's more like a steep broken descent, with each subduction zone acting like a different section of the drop. Some slabs descend at shallow angles, creating broad zones of deformation. Others plunge steeply, creating deep trenches and deep seismic activity. The Tonga subduction zone is one of the steepest and fastest. That makes it one of the clearest examples of this staircase into the deep. It is also one of the most intense. If you could slice the Earth like a cake and look at a cross-section through the Tonga region, you would see the Pacific plate bending downward at the trench and sinking into the mantle. Above it you would see the overriding plate, the volcanic arc, and behind that, the back arc basin. The geometry is striking. The slab is steep. It drops like a heavy sheet being pulled down. And the deeper it goes, the more it becomes part of the mantle's internal circulation. This is where the Ring of Fire becomes more than a surface feature. It becomes a window into the deep earth. Because subduction zones are not just boundaries at the surface, they are pathways. They carry material from the surface into the interior. They transport water, carbon, sediments, and entire slabs of crust down into regions where those materials are transformed. The Ring of Fire is not just a ring of volcanoes, it is a ring of descent. That descent matters because it changes the mantle. The mantle is not a uniform layer of rock. It has convection, it has temperature differences, it has chemical variations, it has flow patterns that are slow but persistent. Subducting slabs sink into it like cold currents in a warm fluid. Those slabs can influence mantle circulation, they can trigger upwellings, they can change the distribution of heat and material, they can affect the long-term evolution of Earth's surface. So when scientists study the Tonga Trench, they are not just studying the trench itself, they are studying one of the clearest examples of a slab sinking deep into the mantle. This is why Tonga is sometimes described as a place where the Earth is being drained into itself. The slab is being pulled down, and that pull is strong enough to shape the region around it. In many subduction zones, the slab sinks at an angle and eventually flattens out at a certain depth. In some regions, slabs stagnate around the boundary between the upper mantle and the lower mantle, roughly 660 kilometers down. They can spread out, forming what scientists sometimes call slab graveyards, zones where old slabs accumulate. In the Tonga region, the slab appears to penetrate deep, and the seismicity extends to great depths. This makes it a valuable region for studying how slabs behave when they descend far into the mantle. And that brings us to the earthquakes again, because the Ring of Fire is not just about volcanoes, it is about seismic energy. The Ring of Fire produces frequent earthquakes because subduction zones accumulate stress. The plates do not slide smoothly. They lock, they strain, they release. But Tonga's earthquakes include deep ones, and that deep seismicity is part of what makes it feel like a staircase. It's as if the slab is not just moving downward, but breaking and shifting along the way, sending signals at different depths. Each earthquake is like a marker on the descent, a reminder that the slab is active as it sinks. Scientists map these earthquakes and use them to trace the slab's shape. This is one of the most important tools for understanding subduction zones. Earthquakes occur within the slab and along its boundary, and their depths can reveal the slab's position. In the Tonga region, the earthquake pattern forms what is called a Wadeti-Benioff zone, a sloping plane of seismic activity that marks the subducting slab. The depth of earthquakes increases as you move inland from the trench, tracing the slab downward. This is a key reason Tonga is so valuable to study. The slab is clearly defined by seismicity, and it descends steeply. It provides a relatively clear picture compared to some other regions where seismicity is more diffuse. But clear does not mean simple, because even if you can trace the slab, you still have to explain why it behaves the way it does. Why does it descend so steeply here? Why does it produce such deep earthquakes? Why is the subduction rate so fast? Why does the back arc basin open behind it? Why does the volcanic arc behave the way it does? These questions connect Tonga to the broader Ring of Fire, because the Ring of Fire is not uniform. Different subduction zones behave differently. Some produce giant megathrust earthquakes more frequently. Some produce more explosive volcanism. Some have shallow slabs. Some have steep slabs. The differences come from many factors: the age and density of the subducting plate, the speed of plate convergence, the geometry of the boundary, the presence of sediments, the temperature structure, the interaction with nearby plates. In Tonga, the subducting plate is old and dense, which makes it more likely to sink steeply. Old oceanic crust is colder and heavier. It has had time to cool as it moves away from mid-ocean ridges. When it reaches a subduction zone, it has more negative buoyancy, meaning it wants to sink. So Tonga's slab is like a heavy object being pulled downward. That pull contributes to the speed of subduction. This is part of what makes Tonga feel like a staircase into the deep. The slab is not reluctant, it is sinking with force, and that force affects the region behind the arc. Back arc spreading occurs when the overriding plate is stretched and thinned behind a subduction zone. It can happen because the slab is pulling down and retreating, causing the trench to migrate and the region behind it to open up. This creates a back arc basin where new crust forms. The Lau Basin behind Tonga is an example of this. It is an active spreading centre in a region that is also experiencing subduction. So in one place you have crust being consumed, and nearby you have crust being created. That is a vivid reminder that plate tectonics is not a simple push-pull system. It is a dynamic process where forces interact in complex ways. The Ring of Fire is full of these interactions, but Tonga is one of the places where they are especially dramatic. Now, volcanoes are the other major feature of the Ring of Fire, and Tonga's volcanic arc is part of that chain. Volcanoes in subduction zones are different from volcanoes in places like Hawaii. Hawaii is a hotspot volcano system, where magma rises from deep mantle plumes. Subduction zone volcanoes are fed by melting triggered by water released from the slab. This makes subduction zone volcanoes often more explosive. The magma can be richer in silica, more viscous, and more gas-rich. That combination can lead to violent eruptions. In Tonga, many volcanoes are underwater, which adds another layer of complexity. Underwater eruptions can be hard to detect until they break the surface or produce noticeable effects. They can build temporary islands, they can collapse, they can generate tsunamis. The Hunga Tonga Hunga Ha'apai eruption showed how powerful an underwater or near-surface eruption can be. It was not a gentle event. It was explosive enough to send shockwaves around the planet. That eruption was part of the Ring of Fire's activity, and it reminded the world that the Ring of Fire is not just a list of famous volcanoes, it includes hidden systems beneath the sea. Now, if you zoom out again, the Ring of Fire forms because the Pacific Plate is surrounded by subduction zones. The Pacific Plate is being consumed around its edges. This is why the Ring of Fire exists. It is the boundary of a large plate that is sinking into the mantle in multiple places. This is an important point. The Ring of Fire is not just random volcanoes, it is a tectonic pattern driven by plate motion. The Pacific Plate is moving, and as it moves, it collides with other plates. Where it collides, it often subducts. Where it subducts, trenches form. Where trenches form, earthquakes occur. Where slabs release water, volcanoes form. So the Ring of Fire is a connected system. Tonga is one segment of that system, but it is a segment that stands out because of its depth and its steep slab. And that steep slab is what makes it feel like a staircase into the deep. It is one of the clearest pathways for material to sink deep into the mantle. This has implications beyond Tonga itself. When slabs sink into the mantle, they carry surface materials downward. They carry water and carbon. Over long timescales, this affects the Earth's geochemical cycles. It affects how much carbon is stored in the mantle versus released through volcanoes. It affects the composition of magmas. It affects the long-term evolution of the atmosphere. So the Ring of Fire is not just a hazard zone, it is part of the Earth's long-term recycling system. But recycling in geology is not gentle, it involves destruction. The Tonga Trench is destruction made visible. It is the edge where the plate begins to go down, and because Tonga's slab is sinking so steeply and quickly, it is a particularly intense part of the recycling system. Now, one of the reasons the Ring of Fire is unsettling is that it produces both frequent small events and rare catastrophic ones. Small earthquakes happen constantly. Many go unnoticed by humans. They are part of the system releasing stress in small increments. But sometimes stress builds and releases in large events. These can be megathrust earthquakes that generate tsunamis. They can be massive eruptions. They can reshape coastlines and affect climate. The Ring of Fire has produced some of the largest earthquakes in recorded history, and some of the most explosive eruptions. Tonga's system is capable of producing large events, and it has produced events that have global reach. So scientists watch it not just out of curiosity but out of caution. They monitor seismicity, they monitor volcanic activity, they study the structure of the slab, they analyse changes over time. But again, the deep ocean makes this harder. The Ring of Fire is partly underwater, many subduction zones are offshore, many volcanic arcs include underwater volcanoes. Monitoring these systems requires ocean bottom seismometers, pressure sensors, and other instruments that are expensive and difficult to maintain. So the Ring of Fire's hidden staircase is not just hidden in a metaphorical sense, it is literally hidden underwater. This is one reason why surprises still happen. Systems that are harder to monitor are harder to anticipate. Now the Tonga region is also interesting because it shows how a subduction zone can influence the shape of the ocean itself. The trench creates a deep groove. The volcanic arc creates islands and seamounts. The back arc basin creates a region of spreading, a new crust. So the ocean floor around Tonga is not flat. It is sculpted by tectonics. It is a landscape of motion. And that landscape influences ocean currents. It influences how water masses move. It influences how sediments are deposited. It influences where life can find food. So even the ocean above the Ring of Fire is shaped by what is happening below. That is part of the hidden staircase too. The staircase is not just a path into the mantle. It is a structure that shapes the seafloor and influences the ocean. Now, if you're listening and thinking that all of this sounds like a lot of moving parts, that's because it is. The Ring of Fire is one of the most complex and active tectonic systems on Earth. It is not one process, it is many processes interacting. Tonga sits in a particularly intense part of it, where the slab is steep, the trench is deep, the seismicity is strong, and the volcanic arc is active. So when scientists talk about the Tonga Trench, they're often talking about the Ring of Fire's deeper mechanics. They're talking about how the Earth moves its crust downward. They're talking about how energy is released. They're talking about how the mantle is influenced by sinking slabs. In that sense, the trench is not just a scary deep place. It is a key piece of the planet's internal engine. But engines can be dangerous, especially when you don't fully understand every part of them. That is why the Ring of Fire's hidden staircase into the deep is unsettling. It is a reminder that the Earth's surface is not a stable platform. It is a moving shell above a dynamic interior. And Tonga is one of the places where that interior is most clearly connected to the surface through a steep, fast subduction system. Now, as we continue, the next thing to focus on is the environment itself, the physical conditions that make the trench such a hostile place for exploration. Because it is one thing to understand the tectonic system on a map. It is another thing to think about what it means to send a machine into a place where pressure becomes a constant threat. So the next step is to look at the force that defines the trench more than anything else. The weight of the ocean above it, and the pressure that comes with it, the kind of pressure that makes materials behave differently, and makes exploration feel like a careful negotiation with physics. Pressure is one of those things that sounds manageable until you meet it in the wrong place. At the surface, we live inside pressure all the time. The air pushes on you constantly, and your body pushes back. You don't notice it because it's normal, it's balanced. It's the quiet background force of everyday life. Even when you climb a mountain and the air gets thinner, the change feels gentle enough that your body can adjust, at least up to a point. But in the deep ocean, pressure stops being background. It becomes the main character. It becomes the rule maker. It becomes the thing that decides what survives, what breaks, what bends, what collapses, and what never even gets the chance to exist. And in the Tonga Trench, pressure is not just high, it is overwhelming. This is one of the most direct reasons the trench terrifies scientists. Not because scientists are easily scared, but because pressure is honest. It does not care about confidence. It does not care about cleverness. It does not care how much funding you have or how advanced your technology is. Pressure is simply the weight of everything above you, and at the bottom of a trench, there is a lot above you. When people imagine the deepest ocean, they often think about darkness first. They think about strange fish with glowing lights. They think about silence. But the reality is that pressure is the first true barrier. Pressure is what makes the deep ocean inaccessible in a way that mountains and deserts are not. You can hike up a mountain with a backpack. You can cross a desert with water and planning. But you cannot casually descend into the Hadal zone. The environment down there is so hostile that it will destroy unprotected objects in an instant. To understand why, it helps to slow down and build a picture carefully, step by step. The same way the pressure builds meter by meter. At sea level, the pressure you experience is about 1 atmosphere. That is roughly 101,225 pascals. That number is not important by itself. What matters is that your body is adapted to it. Your lungs work in it. Your blood circulates in it. Your ears balance it. Now go down into the ocean. Water is much denser than air, so pressure increases much faster with depth. For every 10 meters you descend, pressure increases by about 1 additional atmosphere. That means at 10 meters, you're at about 2 atmospheres. At 20 meters, about 3 atmospheres. At 30 meters, about 4 atmospheres. If you have ever been scuba diving, you have felt this. Your ears need to equalize. Your breathing feels different. You're aware of the weight, even though it's not crushing. But scuba divers do not go anywhere near trench depths. Most recreational dives are under 40 meters. Even technical divers, with specialized training and equipment, rarely go beyond a few hundred meters. The deepest human dives are extreme exceptions, and they are still tiny compared to the Hadal zone, because the Hadal zone begins around 6,000 meters. At 6,000 meters, you're under roughly 600 atmospheres of pressure. At 10,000 meters, you're under roughly 1,000 atmospheres, and the Tonga Trench reaches close to that scale. So at the deepest parts, the pressure is on the order of 1,000 times what you experience at the surface. That is hard to picture, because your brain doesn't have a daily reference for it. We don't live with forces like that. We don't feel them. We don't experience them. The closest comparison people often use is something like an elephant standing on your thumb, or a stack of cars, or a skyscraper pressing down on a small area. Those comparisons help, but they still don't capture the reality. Because the pressure in the deep ocean is not a weight pressing down from above like a heavy object on your head. It is pressure pressing in from all directions. That is what makes it so brutal. If you put a heavy object on top of something, the object can still expand sideways. It can deform. It can escape. But in deep water, pressure surrounds you. It presses from above, below, left, right, front, back. It squeezes everything evenly, like the ocean is trying to compact reality itself. This is why the deep ocean is such a harsh environment for machines. Not because machines can't handle weight, but because they can't handle being squeezed uniformly with that much force unless they are designed for it. Think about a soda can. At the surface it feels solid, but if you remove the air inside it, it collapses easily. That collapse happens because the outside pressure is stronger than the inside pressure. The can doesn't fail because it is weak. It fails because the pressure difference is too large. In the deep ocean, everything is like that soda can. Any air-filled space is a vulnerability. Any hollow chamber is a potential failure point. Any sealed container has to withstand enormous compressive forces. And that is why deep-sea vehicles are built the way they are. They are often shaped like spheres or thick cylinders because those shapes distribute pressure evenly and resist collapse better than flat surfaces. A sphere is one of the best shapes for surviving pressure because it has no corners. Corners create stress concentrations. Flat surfaces bow inward under pressure. Curved surfaces resist that deformation. This is why many deep submersibles have spherical pressure hulls. But even a sphere is not magic. The material has to be strong enough. The walls have to be thick enough. The design has to account for microscopic flaws. Because under that kind of pressure, tiny flaws become big problems. A small crack can propagate. A weak weld can fail. A seal can leak. A window can fracture. and when failure happens at depth, it is not slow, it is sudden. An implosion at great depth can occur in milliseconds. The pressure outside is so high that the structure collapses inward violently. The water rushes in, and the energy release can be enormous. It is not like a gentle leak. It is like the ocean snapping shut. This is why pressure feels like physics should give up. It pushes materials beyond what we usually deal with. It forces engineers to design for extremes. It forces scientists to accept that exploration is dangerous not because of predators or storms, but because the environment itself is trying to crush their tools. And the Tonga Trench adds another layer of difficulty, because it is not just deep, it is also remote, and it is part of an active tectonic region. So you are dealing with pressure, distance, and geological unpredictability at the same time. Now, pressure doesn't just affect machines, it affects life. The fact that anything lives at trench depths is one of the most surprising things about the ocean, because pressure is not just a mechanical force, it affects chemistry and biology. At high pressure, molecules behave differently. Chemical reactions can shift, proteins can change shape, membranes can become less stable, enzymes can function differently. Most life on Earth is adapted to surface pressure. If you take a surface organism and expose it to trench pressure, it will not do well. It may die quickly, its cells may fail, its proteins may denature, its membranes may rupture. So the organisms that live in trenches are not just normal creatures living deeper, they are specially adapted to pressure. One way they do this is through their cell membranes. Membranes need to stay flexible to function. Under pressure, membranes can become more rigid. Deep-sea organisms often have membrane compositions that maintain fluidity under pressure. They also have proteins adapted to function under high pressure. Proteins are complex folded structures, and pressure can affect how they fold. Deep-sea organisms have proteins that remain stable and functional under conditions that would disrupt surface proteins. Another key adaptation involves small molecules called piezolites, compounds that help stabilize proteins under pressure. One of the most well-known is trimethylamine N-oxide, often shortened to TMAO. This compound helps protect proteins from pressure-induced damage. Interestingly, some studies have found that TMAO levels in fish increase with depth, up to a point. It is part of how deep-sea fish can survive pressure. But there may be limits. At extreme depths, the chemistry becomes challenging, even for these adaptations. This is why trench life is not unlimited. There are depth limits for many groups of animals. Certain fish, for example, are not found below certain depths because their biology cannot handle it, even with adaptations. And yet, some organisms do survive. Amphipods, snailfish, microbes, strange worms, tiny crustaceans. They live in a world where pressure is the dominant condition. That world is not only crushing, it is cold. Temperature at trench depths is typically near freezing, just above 0 degrees Celsius. Cold slows down biological processes, it slows metabolism, it reduces chemical reaction rates. Combined with pressure, it creates an environment where life has to be efficient and resilient. Food is also scarce. There is no sunlight, no plants, no algae, no photosynthesis. Life depends on organic material sinking from above and on chemical processes in the sediments. So trench organisms are living under pressure, in cold darkness with limited food. The fact that they exist at all is a reminder that life is adaptable, but it is also a reminder that life at trench depths is not abundant in the way shallow ecosystems are. It is a sparse, specialized world. Now, pressure also affects sound and movement. In water, sound travels faster than in air. That is why whales can communicate over long distances. But in deep water, sound behavior can change with temperature and pressure gradients. This matters for exploration because deep-sea vehicles often rely on acoustic communication. Radio waves do not travel well through seawater. Light does not travel far in darkness, so sound becomes the main way to communicate and navigate. But acoustic communication is slow compared to radio. It has limited bandwidth, it is subject to interference, it can be distorted by terrain. So a submersible in the trench is not just physically isolated, it is also communication isolated. It is operating with limited connection to the surface. That adds to the tension. When something goes wrong at depth, you cannot fix it quickly. You cannot send help. You cannot pull it out easily. You can only wait. Pressure makes waiting feel heavier, because you know the environment is constantly pressing on your equipment second after second. Now, let's talk about what pressure does to materials, because this is where the trench becomes an engineering problem as much as a scientific one. Most deep-sea vehicles use specialised materials for pressure housings. Titanium is common because it is strong, corrosion-resistant, and relatively light compared to steel. High-strength steel is also used in some cases. Syntactic foam is used for buoyancy, because normal foam would collapse under pressure. Syntactic foam is not like the foam in your couch. It is a composite material filled with tiny hollow spheres, often made of glass or ceramic, embedded in resin. These spheres can withstand pressure, allowing the foam to remain buoyant at depth. This is one of those details that sounds small until you realise it's essential. Without buoyancy, a vehicle cannot return to the surface easily. It would sink and stay there. Buoyancy is the difference between a mission and a lost machine. Deep-sea landers often use ballast weights to sink. When it's time to return, they release the ballast, often using an acoustic command. The vehicle becomes buoyant and rises, but pressure affects everything in this system. Release mechanisms have to work under pressure. Batteries have to function. Electronics have to be protected. Seals have to remain intact. And then there are the cameras, lights, and sensors. Cameras have to be housed in pressure-resistant containers. Lights have to operate efficiently in cold water. Sensors have to measure temperature, salinity, pressure, chemistry, and sometimes biological signals. Each component is a potential failure point, and failure points are not forgiving at trench depth. This is why deep-sea missions are often described as expensive and risky, not because scientists like spending money, but because the environment demands robust design. You cannot cut corners, you cannot improvise at the last minute, you have to plan for the worst-case scenario, because the worst-case scenario is always present in the form of pressure. Now, the Tonga Trench adds another twist. It is not just deep, it is part of an active region. That means the seafloor can be unstable, earthquakes can occur, sediments can shift, landslides can happen, volcanic activity can disturb the area. So a vehicle on the bottom is not only being crushed by pressure, it may also be sitting in a landscape that can change. This is not common, but it is possible. A strong earthquake could trigger sediment movement. A landslide could bury instruments. A volcanic event could alter the chemistry. So the trench is not just a static pressure environment. It is pressure plus geological activity. And this combination is part of why it feels like physics should give up. You're asking machines to survive crushing force in a place where the ground itself is part of a moving system. Now, there is something else about pressure that is less obvious, but important. Pressure makes everything slower and more cautious, not because pressure slows time, but because it slows decision-making. When scientists plan a trench mission, they have to think about every detail. They have to think about how long the descent will take, how long the vehicle can stay on the bottom, how much battery power it has, how it will communicate, how it will release ballast, how it will avoid obstacles, how it will recover. They have to think about what happens if the vehicle doesn't come back, because sometimes it doesn't. Deep-sea exploration has a history of lost instruments. Sometimes a lander fails to release ballast. Sometimes communication is lost. Sometimes a component fails. Sometimes the vehicle is damaged. Each loss is not just financial, it is also emotional. Scientists invest years in designing missions. They invest hopes in the data they might collect. When a vehicle is lost, it can feel like losing a piece of the unknown that you almost touched. Pressure is always there, waiting to exploit the smallest weakness. So scientists respect it, engineers respect it, everyone involved respects it. And that respect can feel like fear, because it is an awareness of how little margin there is. Now, it's worth noticing that pressure is not inherently evil. It is just a physical consequence of depth. It is what makes the deep ocean the deep ocean. But it is also what keeps the trench mysterious. Because pressure limits exploration. It limits observation. It makes missions rare and expensive. That means we have fewer opportunities to gather data, fewer chances to map the bottom, fewer chances to observe life, fewer chances to sample sediments. So pressure is not just a barrier to machines, it is a barrier to knowledge. And that is part of why the Tonga Trench still terrifies scientists. It is not just dangerous, it is difficult to study. It remains partly unknown because the environment resists our attempts to observe it. Now, after pressure, the next major force that shapes trench exploration is darkness. Not darkness as a spooky idea, but darkness as a practical reality. Darkness affects navigation. Darkness affects perception. Darkness affects biology. Darkness changes what the ocean feels like. Because even if you could build a machine that ignores pressure, you would still be descending into a place where light is absent, where your eyes become irrelevant, and where the only way to see is to bring your own illumination into a world that has not seen sunlight for millions of years. And that shift, from pressure as the crushing force to darkness as the absorbing force, is where the trench begins to feel less like a location and more like an entirely separate environment, one that does not welcome visitors but will tolerate them briefly if they are built strong enough. Darkness in the deep ocean is not the kind of darkness you experience when you turn off a bedroom light. It's not a soft dimness where your eyes slowly adjust and you start to make out familiar shapes. It's not the darkness of a cloudy night, where the moon still gives you a little guidance. It's not even the darkness of a cave, where you can at least feel the walls and know how close they are. The darkness in the Tonga Trench is complete. It is the absence of light in a way that feels absolute because sunlight cannot reach it, and because nothing down there produces enough natural light to change that fact. You can bring lamps, you can bring cameras, you can bring the brightest LEDs we know how to build, and the trench will still feel like it is swallowing the light rather than receiving it. And this is another reason the trench terrifies scientists. Darkness is not just unsettling emotionally, it is difficult practically. It changes how you explore, it changes how you measure, it changes how you navigate, it changes how you think about distance and space. On land, we rely on sight constantly. We glance at a horizon and understand scale. We look at a slope and know whether it's steep. We see a storm approaching. We see a road turning. We see the face of another person and interpret emotion in an instant. Underwater, sight is limited even near the surface. Water absorbs light quickly. It scatters it. It filters it. It turns everything blue and dim. That's why shallow coral reefs look bright and colourful, but the colours disappear as you descend. Red light is absorbed first, then orange, then yellow. By the time you reach deeper water, everything looks blue or grey, and then eventually even blue disappears. In the open ocean, sunlight fades into the twilight zone, the mesopelagic, where there is still some faint light from above but not enough for photosynthesis. Below that is the midnight zone, the bathypelagic, where there is no sunlight at all. Below that, deeper still, is the abyssal zone, and below that, in the deepest trenches, is the Hadal zone. By the time you reach trench depths, you are far beyond the point where the sun matters. The darkness down there is not an event, it is a condition. It has been that way for millions of years. It will remain that way long after we're gone. So when scientists descend into the Tonga Trench, they are not just going into deep water, they're going into a world where light does not exist naturally. The only light that appears is the light you bring, and it is temporary. It is a visitor, and visitors stand out. That matters because life in the deep sea is adapted to darkness. Many organisms there are sensitive to light. Some avoid it. Some are attracted to it. Some use their own light, bioluminescence, for communication, hunting, and defense. But in trenches, bioluminescence exists in a different context. In the mid-water deep, bioluminescence is common because organisms are suspended in the water column. They use light to signal or lure prey in the dark. In the trench environment, much of the life is closer to the seafloor, living in or on sediment. The conditions are different. Food is scarcer, movement is slower, the ecosystem is shaped by what sinks from above. Still, darkness is the constant. And darkness affects more than biology. It affects how scientists work. If you cannot see, you must rely on instruments. That sounds obvious, but it changes everything. It changes what you can learn quickly. It changes how you interpret what is happening. It changes how confident you can be in your understanding. Imagine trying to explore a landscape on land with your eyes closed, relying only on touch and sound. You could still learn things, but you would be slower. You would be cautious. You would miss details. You would struggle to build a mental map. That is what trench exploration is like. Even with cameras, you only see what your lights illuminate, and your lights illuminate a small patch. Everything else is black. This means the trench feels bigger than it already is, because your visual world shrinks down to a tunnel of light. A submersible might have powerful lamps, but in deep water, light does not travel far. Particles in the water scatter it. Sediment stirred up by movement can reflect it back. If the vehicle gets too close to the bottom, it can create a cloud of silt that turns the water into a blinding fog, except the fog is underwater and black. So even with light, visibility can be limited. This is one reason deep-sea videos often look eerie. You see a bright circle of light in the centre, and beyond it, nothing. A creature swims through the beam, then vanishes. A patch of seafloor appears, then fades away as the vehicle moves. It is like watching the world through a flashlight in a pitch-black room, except the room is enormous, and the floor is thousands of meters below where you started. Now, you might think, fine, so it's dark. Scientists can still measure things, and yes, they can. But darkness changes how you measure because it removes the simplest kind of observation. You cannot simply look around and see patterns. You cannot easily spot hazards. You cannot judge distance well without reference points. This makes navigation harder. Underwater navigation is already difficult because GPS does not work underwater. Radio signals do not travel well through seawater, so submersibles and landers rely on acoustic navigation, inertial systems, sonar mapping, and careful planning. In darkness, you cannot use visual cues to correct your path. You cannot see a landmark from far away. You cannot see the shape of the terrain until you are close enough for your lights to reach it. So the trench becomes a place where you move slowly and cautiously, because you are always close to something you cannot see. This is especially true in a trench environment because trenches have steep walls. They are not flat plains. The bottom is narrow. The slopes can be sharp. The terrain can change abruptly. A submersible descending into the trench is not just going down into open water. It is approaching a structure with edges and slopes, like a canyon. But unlike a canyon on land, it is invisible until your instruments reveal it. This is one reason trench exploration feels tense, even when nothing dramatic happens. You're navigating in darkness near steep terrain, under crushing pressure, with limited communication. It is the kind of environment where caution becomes instinct. Now, the title here is The Darkness That Swallows Light and Sound matters too, because in the deep ocean, sound is the main way humans communicate and sense the environment. We often think of the deep ocean as silent. We imagine it as a quiet void. But the ocean is not silent. Sound travels extremely well in water, better than in air. It travels farther. It travels faster. It can carry information across long distances. Whales use sound to communicate across entire ocean basins. Some fish make sounds. Ice cracking can be heard underwater. Storms above can send noise down into the water column. Even distant ships contribute to background noise. But the trench environment changes how sound behaves in subtle ways, and it changes how humans use sound for exploration. Sonar is one of the most important tools for mapping the seafloor. It uses sound pulses that bounce off surfaces. Multi-beam sonar on ships maps the seafloor from above. Side-scan sonar can create images of seafloor texture. Submersibles can use sonar to detect obstacles and navigate. In the trench, sonar becomes essential because you cannot rely on sight. But sonar has limitations. Sound waves can reflect off walls. They can create confusing echoes. Steep slopes can create shadows where sonar does not reach. The geometry can distort the returns. So even sound, which is the deep ocean's main sense, can be complicated by the trench's shape. And then there is acoustic communication. Deep-sea vehicles often communicate with the surface using acoustic signals. These are basically sound messages, but acoustic communication is slow. It has limited bandwidth. It can be interrupted by noise. It can be affected by the environment. It is not like talking on a phone. It is more like sending short, careful signals through a medium that does not always cooperate. So the trench becomes a place where both light and sound are limited. Light is almost absent. Sound is available but imperfect. That combination creates isolation. And isolation is another reason scientists feel uneasy about trenches. When you send a vehicle into the Tonga Trench, it is out of reach. If it fails, you cannot rescue it quickly. You cannot send a diver. You cannot pull it out easily. You have to wait for it to return, or accept that it may not. Darkness amplifies that feeling because you cannot see what is happening. You cannot watch the vehicle descend. You cannot see the seafloor from the surface. You cannot see the conditions it is experiencing. You are relying on numbers and signals. Depth, pressure, temperature, orientation, battery levels, acoustic pings. That is a very different experience from most exploration. It is exploration by inference. Now, the trench darkness also affects how life behaves. In the deep ocean, many organisms have reduced or absent eyes. Some have eyes adapted to detect faint bioluminescence. Some are blind. In trenches where sunlight never reaches, eyes are not as useful. But darkness does not mean nothing is happening. It means life has adapted to different senses. Many deep-sea organisms rely on touch, vibration, and chemical cues. They detect food through smell. They detect movement through changes in water pressure. They find mates through chemical signals. They navigate by following gradients in the environment. In a trench, where food is scarce, these senses matter. Scavengers like amphipods can detect bait from surprisingly far away. Scientists sometimes deploy baited traps to study trench life, and amphipods can arrive quickly, swarming around the bait. This is one of the strange things about trench biology. Even in a place where food is scarce, when food appears, life responds. But the response is not dramatic in a fast, chaotic way. It is often slow and steady. The creatures move deliberately. They conserve energy. The darkness encourages that kind of life. There is no reason to move quickly unless you have to. There is no light cycle to follow. There is no day and night in the usual sense. There is only the constant blackness and the slow arrival of food. This creates a different rhythm. Now, when humans bring light into that rhythm, it can disrupt it. A bright submersible light can startle organisms. It can cause them to flee. It can attract some species. It can alter behaviour. This is one reason scientists try to be careful with lighting and observation. They want to observe natural behaviour, not behaviour altered by the presence of a glowing machine. But the deep ocean makes this difficult. You need light to see, but light changes what you see. So even observation is a trade-off. Now let's talk about something that makes trench darkness even more unsettling. The way it changes your sense of distance. In the deep ocean you cannot see far, so everything feels close. A wall appears suddenly. A creature appears suddenly. A patch of seafloor appears suddenly. This can create a feeling of claustrophobia even though you're in an enormous space. It is a strange psychological effect. You're surrounded by open water, but your visible world is small. Your mind fills in the rest with imagination, and imagination is not always kind. Scientists are trained to focus on data, but they are still human. When they watch trench footage, they still feel that unease. The darkness is not just a lack of light, it is a lack of information. And humans do not like missing information. We are pattern seekers. We like to know what is around us. We like to see threats before they reach us. We like to understand space. The trench denies that. It offers only what your lights and instruments can reveal. Now, there is another subtle detail about trench darkness that matters. It affects time. Not time in the physics sense, but time in the human sense. On the surface, day and night give structure. Light tells you when to wake and when to sleep. Even if you ignore it, your body responds to it. In the trench, there is no day-night cycle. There is no sunrise, no sunset, no change in light. So the environment is timeless in a sensory way. It does not provide cues. For organisms living there, this means life is structured differently. Biological rhythms still exist, but they are not driven by sunlight. They may be driven by food availability, by currents, by internal clocks. For humans exploring, the lack of light makes the trench feel like a place outside normal experience. This contributes to the emotional weight of deep-sea exploration. It feels like leaving the surface world behind. Now, the phrase swallows light and sound is not just about the physical absence. It is about how the trench absorbs your attempts to make it familiar. You bring light, and it disappears into blackness beyond your beam. You send sound, and it returns with echoes and distortions, telling you the shape is complex and hidden. You send a vehicle, and it becomes a small, fragile thing in a vast environment. So the trench remains dominant, and dominance is unsettling. It reminds you that the environment is bigger than your tools. Now, there is one more detail that makes trench darkness particularly challenging: sediment. Trench bottoms often have fine sediment, particles that have settled slowly over time. This sediment can be easily disturbed. A submersible approaching too closely can stir it up. A lander touching down can create a cloud. An earthquake can trigger sediment movement. In darkness, a sediment cloud is not just murky, it can be blinding. If your lights reflect off suspended particles, your camera view can become useless. It becomes a bright haze. Your visibility drops to almost nothing. So even when you bring light, the environment can take it away again by filling the water with reflective dust. This makes trench exploration feel like working inside a snowstorm, except the snow is mud and the storm is underwater. So scientists plan carefully. They approach slowly. They use sonar to guide them. They keep distance from the bottom when possible. They avoid stirring sediment, because once the sediment is disturbed, it can take a long time to settle, and while it settles, you are effectively blind. Now, darkness also shapes what we don't see. There are creatures in the deep ocean that we have never observed. There are behaviours we have never recorded. There are chemical processes we have not measured. There are interactions we have not detected. The deep ocean is vast. Trenches are small compared to the whole ocean, but they are still enormous compared to our ability to explore them. So when scientists talk about trench darkness, they are also talking about the unknown. Not the unknown in a mystical sense, but the unknown in a practical sense. We simply have not looked enough. And we have not looked enough because it is hard. The trench swallows light because it is deep and dark. It swallows sound in the sense that it complicates acoustic signals. It swallows knowledge because it limits exploration. So the darkness becomes part of the trench's reputation. It is not just an absence, it is a barrier, and barriers create fear. Now, after pressure and darkness, the next thing that often surprises people about trenches is that they are not empty. They are not silent voids with nothing living. They are ecosystems with organisms that have adapted to pressure and darkness in ways that seem almost impossible. So the next step is to look at those creatures, not as monsters, but as survivors. Because the life in the Tonga Trench is one of the clearest examples of how biology can adapt to extreme conditions, and it is also one of the reasons scientists keep returning to the deep, even when the environment makes every mission feel like a careful gamble. When you first hear that animals live in the deepest parts of the ocean, it sounds like a mistake. Not because life in the ocean is surprising, but because the conditions in trenches are so extreme that your brain naturally assumes nothing complex could survive there. No sunlight, near freezing water, crushing pressure, limited food. That combination feels like a final answer, and yet it isn't. Life exists in the Tonga Trench and in other Hadal trenches, not in huge numbers the way it does in a coral reef, but enough to remind us that biology is not easily discouraged. These creatures live in a place where most of the rules we take for granted stop being reliable. They live as if the surface world's normal limits do not apply. But the truth is a little more grounded than the phrase makes it sound. The rules still apply, physics still applies, chemistry still applies, evolution still applies. The creatures aren't breaking reality. They are adapted to it. They are built for a world that is completely different from ours, and that is why they can feel so unsettling. Because when you see them, you realize the deep ocean is not empty. It is simply unfamiliar. The Hadal zone, the zone of trenches deeper than about 6,000 meters, is one of the least explored habitats on Earth. There are not many places like it. Most of the ocean floor is abyssal plain, deep, dark, cold, but not trench deep. Trenches are the extreme end of the spectrum, so trench creatures are not just deep-sea animals, they are extreme deep-sea animals. And to survive, they have to solve problems that surface creatures never face. The first problem is pressure. Pressure affects everything. It affects cell membranes. It affects proteins. It affects the way molecules interact. It affects how organisms move and maintain their internal structure. Most animals that live at shallow depths have bodies that would fail under trench pressure. Their cells would malfunction. Their proteins would change shape. Their tissues would not behave properly. So trench animals have evolved bodies and chemistry that can handle it. One of the most famous examples is the Hadal snailfish. Snailfish are not glamorous animals. They are soft-bodied fish that often look a little unfinished, like they were assembled quickly. Many species live in deep water, and a few species have been found in trench environments. At trench depths, snailfish are among the deepest living fish known. They are not muscular predators with sharp teeth and fast reflexes. They are slow, delicate-looking creatures that survive by being efficient. They do not have swim bladders, because a gas-filled bladder would be crushed. Instead, their bodies are adapted to neutral buoyancy through other means. Their tissues contain compounds that help stabilize proteins under pressure. Their bones are less dense. Their bodies are flexible. They look fragile, but they're perfectly suited to the environment. This is one of the first rules don't apply moments people have when they see trench footage. You expect something armoured, something tough. Instead, you see something soft. It feels wrong until you remember what pressure does. Pressure crushes empty spaces. It collapses air pockets. It destroys rigid structures that cannot flex. In some ways, being soft is an advantage. A soft body can distribute pressure more evenly. It can avoid catastrophic collapse because it has fewer rigid cavities to fail, so the trench favours a certain kind of design. Soft, flexible, efficient. This is not universal, but it is common. Another group of trench survivors that scientists encounter often are amphipods. Amphipods are small crustaceans related to shrimp and crabs. In shallow water, amphipods might be small scavengers or swimmers. In trenches, amphipods can become some of the most common visible animals. They are scavengers, and they are good at it. Scientists sometimes deploy baited traps into trenches, and amphipods arrive quickly, sometimes in large numbers. They swarm over the bait, tearing off pieces, feeding rapidly. This behaviour can look intense, but it makes sense. Food in the trench is scarce. Most of the time the bottom is quiet. Organic material drifts down slowly as marine snow, tiny particles of dead plankton, fecal pellets, and other debris. Occasionally something larger falls, like a dead fish or whale remains, and it becomes a rare feast. When a feast appears, scavengers respond. Amphipods have adapted to this lifestyle. They can detect chemical signals in the water, they can move toward food, they can feed quickly, they can survive long periods with little to eat. They also have to deal with pressure, and like many trench organisms, they have chemistry adapted to it. Now, amphipods might not sound terrifying, but they are part of what makes trench ecosystems feel strange. You see them in the lights of a lander, swarming like insects, except they are deep underwater at depths where your mind expects nothing. That mismatch is unsettling. Then there are the microbes, the smallest and most important life forms in the trench. Microbes are everywhere on Earth. They live in hot springs, in ice, in deserts, inside rocks. They are the ultimate survivors. In trenches, microbes live in sediments and water, forming the base of many deep ecosystems. In the Hadal zone, microbes can survive on very little. They can process organic material that sinks from above. They can use chemical energy from minerals in sediments. They can form communities that are invisible to the naked eye but essential for nutrient cycling. Microbial life is not dramatic to watch, but it is a reminder that the trench is not a dead zone. It is an ecosystem, and ecosystems mean interactions, food webs, decomposition, recycling. Even in darkness, even under pressure, life continues its basic processes. Now, one of the strangest things about trench ecosystems is how they can be both sparse and active. If you imagine a trench bottom, you might picture a barren plain of mud. In some places, it may look like that. But when scientists deploy cameras, they often see movement. Small animals crawling, amphipods drifting, fish appearing briefly, worms in sediment. The activity is not constant, but it is there. And that is where the rules don't apply feeling grows stronger. Because the trench is not supposed to be busy. It is supposed to be empty, but it isn't. Now, another type of creature that appears in trench environments is the sea cucumber. Sea cucumbers are strange even in shallow water. They are soft, elongated animals related to sea stars and sea urchins. They move slowly. They feed on sediment, extracting organic material. In the deep sea, sea cucumbers can be common on abyssal plains. In trenches, some species can survive as well. They move across the bottom like slow vacuum cleaners, processing mud. They are not glamorous, but they are important. They recycle nutrients. They keep sediment ecosystems functioning. There are also polychaete worms, bristleworms that live in sediment. Some are predators, some are scavengers, some feed on detritus. They are part of the trench's hidden life. And then there are organisms that are harder to classify in the moment. Gelatinous creatures drifting in the water column. Transparent animals that appear briefly in camera lights. The deep ocean is full of gelatinous life. Jellies, siphonophores, salps. Creatures that are mostly water and yet perfectly alive. In the trench, some of these may appear, but much of the trench life is tied to the bottom because food tends to settle there. Now, the trench environment shapes these creatures in a few consistent ways. First, many trench animals are small. This is partly because food is limited. Large bodies require more energy. In an environment where meals are unpredictable, smaller bodies can be an advantage. Second, many trench animals are slow. Movement costs energy. In the cold, deep sea, metabolism is slower. Many animals conserve energy by moving deliberately. Third, many trench animals are scavengers or detritivores. They feed on what falls from above. They are not chasing abundant prey. They are waiting for food to arrive. Fourth, many trench animals have reduced skeletons or flexible bodies. Again, pressure favours designs that do not rely on rigid air-filled structures. But even within these patterns there are surprises. One surprise is that some trenches may be richer in organic material than surrounding abyssal plains. Trenches can act like traps. Their shape can funnel sediment and debris downward. Currents can deposit material in the trench axis, Landslides can deliver pulses of organic matter, so the trench can become a collection point. This means the trench ecosystem can sometimes be more active than you would expect, at least in certain areas. But it also means the trench is a sink for human debris. Scientists have found plastic in deep trenches, fibres, microplastics, chemical pollutants. Even at Hadal depths, the signature of the surface world is present. This is one of the most disturbing things about trench biology. Not because it is surprising that pollution spreads, but because it shows how connected the planet is. Even the deepest places are not isolated. They are part of the global system, and trench creatures are now living in a world that includes our waste. Some organisms may ingest microplastics, some may accumulate chemicals. The long-term effects are still being studied, but the fact that it is happening at all is unsettling. It means the trench is not a safe refuge from human influence. Now, another reason trench creatures feel like they break the rules is because they challenge our assumptions about limits. We often talk about extreme environments as if they are at the edge of what life can tolerate. But the Hadal zone is one of the most extreme environments on Earth, and life still exists there. So where is the limit? Scientists are still exploring that question. There are likely limits based on pressure and chemistry. Certain biological structures cannot function beyond certain pressures. Certain molecules cannot remain stable. There may be a depth beyond which complex multicellular life cannot survive. But even that is not fully settled. Every time scientists find a fish deeper than expected, or a community of organisms thriving in a trench, it pushes our understanding. And this matters beyond Earth. Because if life can survive in trenches, it suggests life might survive in other extreme environments, like the subsurface oceans of icy moons. Places like Europa and Enceladus have oceans beneath ice. Those oceans may be dark, cold, and under high pressure. If life exists there, it would likely resemble deep ocean life more than surface life. So trench biology is not just about Earth's weird creatures. It is also a clue about what life might be capable of elsewhere. Now, the Tonga Trench itself is not as famous for biological discoveries as some other trenches, partly because it has been explored less. The Mariana Trench has received more attention. But the Tonga region is still part of the Hadal world, and it likely hosts similar kinds of organisms. And because the region is tectonically active, it may have unique features. Sediment composition may differ. Food input patterns may differ. Chemistry may differ. These differences could shape the ecosystem in subtle ways. For example, if tectonic activity triggers landslides, it could deliver sudden pulses of organic material to the bottom. That could create feast events that scavengers respond to. If volcanic activity influences water chemistry, it could affect microbial communities. If the trench geometry traps water masses differently, it could influence oxygen levels and nutrient distribution. These are the kinds of questions scientists ask, and the kinds of questions that keep trenches interesting. But again, the environment makes answering them difficult. To study trench life, scientists need samples, they need images, they need measurements of chemistry and sediment. They need to deploy traps and collect organisms. Doing that at Hadal depths is challenging. Sampling devices must survive pressure. Collection containers must remain sealed. Instruments must function in cold water. The vehicle must return safely. Even when samples are collected, keeping them alive or intact for study is difficult. Pressure changes during ascent can damage organisms. Some deep-sea organisms cannot survive decompression. Their bodies are adapted to high pressure, and bringing them to the surface can be fatal. So scientists often study trench organisms through observation and through chemical analysis rather than keeping them alive. This limits what can be learned, and that limitation contributes to the sense that trench creatures live outside the rules. They are difficult to study, they are difficult to keep, they exist in a world that does not translate easily to the surface. Now, there is also something about trench creatures that is psychologically unsettling. It is the way they look. Deep-sea creatures often look strange to us because we are adapted to a world of sunlight and shallow water. Our brains are used to certain shapes and colours. We're used to fish that look like fish, animals that look like animals. In the deep, many creatures are pale, because there is no need for camouflage colours. Many are translucent. Many have large mouths or unusual proportions. Many have soft bodies. Many look like they're designed for a different planet. That visual strangeness triggers a reaction in people. It feels like a mismatch. It feels like the deep ocean is producing forms that are not meant for our eyes. And in a way that is true. They're not meant for our eyes. They are meant for the dark. So when we shine lights on them and film them, we are seeing them out of context. We are seeing them under conditions they never evolved for. That can make them look even stranger. But if you strip away the shock, the reality is that trench creatures are not monsters. They are solutions. They are evolutionary answers to extreme problems. How do you survive without light? You don't rely on vision. How do you survive with scarce food? You conserve energy and scavenge. How do you survive under pressure? You adapt your chemistry and body structure. How do you reproduce in a vast, dark environment? You use chemical cues, or you rely on chance encounters, or you produce many offspring. Each adaptation is practical, and that practicality is what makes trench life so impressive. Now, one of the reasons scientists find trench creatures fascinating, and sometimes unsettling, is because they represent the edge of known biology. Studying them can reveal new proteins, new metabolic pathways, new chemical compounds. It can reveal how life maintains stability under pressure. It can reveal how cells protect themselves. These insights can have practical applications. For example, enzymes from deep-sea microbes might be useful in industrial processes that require high pressure or low temperature. Compounds that stabilize proteins might inspire new biomedical research. So trench creatures are not just curiosities, they are sources of knowledge. But they are also reminders that we are not the default. Humans tend to think of our environment as normal. We think of sunlight, oxygen-rich air, moderate pressure, and comfortable temperatures as the standard. But most of the planet is not like that. Most of the planet is ocean. Most of the ocean is deep. Most of the deep ocean is dark, cold, and under pressure. In that sense, trench creatures are living in what might be the more common environment on Earth, while we live on a thin surface layer. That perspective can be humbling, and humility can feel unsettling. Now, as we move forward, it's worth noticing that these creatures are not just surviving in darkness and pressure. They are also surviving in a chemical environment that is different from the surface. Deep water chemistry changes with depth. Oxygen levels can vary. Nutrients can vary. The composition of sediments can vary. In trenches, the accumulation of organic material and the isolation of water masses can create unique chemical conditions. So to understand trench life, scientists also need to understand trench chemistry, because life does not exist separately from its environment, it is shaped by it. And in the Tonga Trench, the chemistry of the Hadal zone is part of what makes the place feel so alien. It is a world where water behaves differently, where sediments hold secrets, and where the smallest chemical changes can determine whether life thrives or fades. So the next step is to move from the creatures themselves to the invisible environment that supports them. The strange chemistry of the Hadal zone, the way water and sediment interact at extreme depths, and the subtle processes that keep this deep ecosystem running in a place where sunlight never reaches and pressure never relaxes. Chemistry is easy to ignore when life is comfortable. At the surface, chemistry is everywhere, but it hides behind familiar experiences. You drink water, you breathe air, you eat food. You don't usually think about dissolved gases, nutrient cycles, pH levels, or the way minerals react under pressure. You can live your entire life without ever needing to care about the chemistry of the environment, because the environment is built for you. The Hadal zone is not built for you. In the Tonga Trench, chemistry stops being background. It becomes part of the survival story. It shapes what can live there, what can't, what breaks down, what accumulates, and what changes slowly over time. And the strange part is not that the chemistry is complicated. The strange part is that it is unfamiliar. and it behaves differently than what we expect from surface water. When we think of the ocean, we often think of it as one big body of water. But the ocean is layered. It has different water masses with different temperatures and salinities. It has currents that move heat and salt around the planet. It has zones with more oxygen and zones with less oxygen. It has regions where nutrients are abundant and regions where nutrients are scarce. The Hadal zone sits at the extreme bottom of this layered system. It is not just deep water, it is a place with its own physical and chemical conditions. To understand why the chemistry is strange, it helps to start with something simple. The deep ocean is cold. At trench depths, the water temperature is usually close to freezing, often around 1 to 2 degrees Celsius. Cold water holds more dissolved gas than warm water, including oxygen. That might make you think the Hadal zone should be oxygen-rich, but it isn't always that simple. Oxygen in the deep ocean is not determined only by temperature. It is determined by circulation and by consumption. Oxygen enters the ocean from the surface, where it dissolves into seawater. That oxygen is then transported into the deep by currents and by the sinking of dense water in certain regions. Once oxygen is in the deep ocean, it is slowly used up by organisms. Microbes consume oxygen as they break down organic material. Animals consume oxygen as they respire. Over time, oxygen levels can decline if the water is not replenished. So the oxygen chemistry of the Hadal zone depends on how well deep water is ventilated, how quickly water is exchanged, and how much organic material is being decomposed. In trenches, water circulation can be unusual. Trenches are deep, narrow features. They can trap water masses. They can create zones where water stays for long periods. They can be influenced by currents that flow along the trench axis. They can be affected by mixing events, such as storms, internal waves, and earthquakes. This means the Hadal zone can have pockets of water with distinct chemical characteristics. Some trench bottoms may have relatively well-oxygenated water. Others may have lower oxygen levels. The exact conditions depend on the trench and on local oceanography. So when scientists talk about Hadal chemistry, they are talking about a system that is not uniform. It is patchy, layered, and influenced by both ocean circulation and local trench geometry. Now, oxygen is only one piece of the story. Another major part is carbon. At the surface, carbon moves through the ocean in the form of dissolved carbon dioxide, bicarbonate, carbonate ions, and organic carbon produced by photosynthesis. Phytoplankton in the sunlit zone use CO2 to build organic matter. That organic matter becomes food for other organisms. Some of it is consumed and returned to the water as CO2. Some of it sinks. This sinking material is one of the main ways the surface ocean connects to the deep. It is often called the biological pump. The idea is simple. Life at the surface captures carbon, and some of that carbon is transported downward as organic particles. In the deep ocean, microbes break down this organic matter. As they do, they consume oxygen and release CO2. This changes the chemistry of deep water. So deep water tends to have higher dissolved CO2 and lower pH than surface water. In trenches, this process can be intensified because trenches can collect sinking material. Think of the trench as a funnel. Organic particles sink everywhere in the ocean, but the trench's shape can trap them. Sediment can slide down the walls. Currents can deposit material in the trench axis. Over time, the bottom can accumulate organic-rich sediment compared to surrounding abyssal plains. This can create a chemical environment that is more active than you would expect. More organic matter means more microbial decomposition. More decomposition means more oxygen consumption and more CO2 production. So trench bottoms can sometimes have chemistry that reflects this increased breakdown of organic material. This matters for life. Microbes thrive where organic material is available. They break it down and recycle nutrients. They form the base of deep ecosystems. But increased microbial activity can also reduce oxygen levels, which affects what kinds of animals can survive. So trench chemistry is tied directly to trench biology. Now, another strange chemical feature of the Hadal zone is nutrient cycling. At the surface, nutrients like nitrate, phosphate, and silicate are used by phytoplankton to grow. When phytoplankton die or are eaten, nutrients can be recycled in the surface layer, or they can sink. In the deep ocean, nutrients tend to accumulate because organic matter is broken down, and nutrients are released back into the water. This is why deep water is often nutrient-rich compared to surface water. But in trenches, the accumulation of organic matter and the isolation of water masses can create unique nutrient patterns. The sediments at the bottom of trenches can act like chemical reactors. Microbes in sediments break down organic matter and produce compounds that diffuse into the water. The sediment-water interface becomes an active zone where chemistry is constantly changing. For example, when microbes consume oxygen, they create oxygen pore zones in sediment. In these zones, other chemical processes take over. Microbes can use nitrate instead of oxygen. They can use sulfate. They can produce methane. They can produce hydrogen sulfide. These processes depend on what is available and on the chemistry of the sediment. So even though the trench water above may contain oxygen, the sediment below can be oxygen poor and chemically active. This creates gradients. Oxygen may be present in the water column, but it may disappear quickly in sediment. Other chemicals may increte in sediment and diffuse upward. This is one of the strange things about Hadal chemistry. It is not just about the water, it is about the interaction between water and sediment. Now, pressure itself influences chemistry. High pressure affects gas solubility. It affects reaction rates. It can change the stability of certain compounds. It can influence how minerals dissolve or precipitate. For example, carbon dioxide behaves differently under pressure. The equilibrium between dissolved CO2, bicarbonate and carbonate shifts with pressure and temperature. This influences pH and carbonate chemistry. Carbonate chemistry matters because it affects organisms that build shells or skeletons from calcium carbonate. In deep water, calcium carbonate can dissolve more easily because of pressure, temperature, and CO2 levels. There is a depth called the carbonate compensation depth, where calcium carbonate dissolves faster than it accumulates. Below this depth, shells made of calcium carbonate tend to dissolve. Trenches are far below this depth, so in the Hadal zone, calcium carbonate structures are not stable in the same way they are in shallow water. This affects what kinds of organisms can build shells and how sediments are composed. Many deep-sea organisms use different materials, or they have reduced hard structures. The chemistry does not favour thick carbonate shells, so the Hadal zone is chemically selective. It shapes biology by making some strategies less viable. Now, the Tonga Trench adds another layer of chemical complexity because it sits in a tectonically active region. Subduction zones are not just mechanical systems, they are chemical systems. They transport water and sediments into the mantle. They release fluids. They create volcanic activity. They alter the chemistry of the surrounding environment. Underwater volcanic activity can influence local water chemistry by releasing gases and minerals. Hydrothermal systems can release chemicals that support microbial life. Even without obvious vents, tectonic activity can influence sediment composition and fluid flow. Now, the Tonga Trench itself is extremely deep, and hydrothermal vents are more commonly discussed in mid-ocean ridge settings rather than trench bottoms. But the broader Tonga Arc region includes volcanic activity and back arc spreading, which can produce hydrothermal systems. Hydrothermal vents are places where seawater circulates through hot rock, picks up minerals, and emerges as mineral-rich fluid. These vents support unique ecosystems based on chemosynthesis, where microbes use chemical energy rather than sunlight. In the trench, the main energy source is usually organic material from above, but nearby hydrothermal systems can contribute chemical inputs that affect the region. So Tonga's chemistry is influenced not just by depth, but by geology. Now, there is another strange chemical story in trenches that has become more important in recent years: human pollution. Scientists have found microplastics and persistent organic pollutants in deep trenches. These substances are carried into the deep ocean by sinking particles and by currents. They accumulate in sediments and can be ingested by organisms. Microplastics can act as surfaces for microbes. They can carry chemicals. They can be mistaken for food. Persistent pollutants, like certain industrial chemicals, can bind to particles and sink. They can accumulate in deep sediments. So the Hadal zone is not chemically isolated. It is part of the global ocean system, and it receives what the surface sends down. This is one of the most unsettling aspects of Hadal chemistry. It means the trench is not untouched. It is not pure. It is connected. And because trenches can trap sediments, they may also trap pollutants. So the trench becomes a record of human impact. Now, when scientists study Hadal chemistry, they often use specialized sampling devices. They collect water samples at depth. They collect sediment cores. They measure dissolved oxygen, nutrients, carbon compounds, trace metals, and other chemical indicators. But sampling at trench depth is difficult. Water samplers must be pressure resistant. Bottles must seal properly. Instruments must function under pressure. Sediment corers must penetrate the bottom and retrieve intact samples without disturbance. Even when samples are retrieved, preserving them is a challenge. Pressure changes during ascent can alter chemical conditions. Gases can come out of solution. Microbial activity can change samples if they are not processed quickly. So Hadal chemistry research requires careful methods. This is another reason trenches remain partly mysterious. The chemistry is hard to measure accurately because the environment is extreme, and the sampling process can alter what you are trying to study. Now, let's talk about the sediments themselves, because trench sediments are not just mud. They are archives. Sediments accumulate over time. They contain particles from the surface ocean. They contain remains of organisms. They contain minerals from land. They contain volcanic ash. They contain chemical signatures of ocean conditions. In a trench, sediment can accumulate differently than on abyssal plains. The trench can collect material from its walls. Landslides can deliver sudden layers. Earthquakes can trigger sediment flows called turbidity currents, which can deposit thick layers quickly. So trench sediments can record sudden events. For example, a major earthquake might trigger a sediment slump that deposits a distinct layer. A volcanic eruption might deposit ash. A tsunami might redistribute material. By studying sediment cores, scientists can reconstruct past events. This is important because it helps build a history of the region. It helps scientists understand how often large earthquakes occur, how often landslides happen, how the system behaves over time. So the chemistry of the Hadal zone is not just about the present, it is also about the past. The sediments contain chemical fingerprints that can tell us about changes in productivity at the surface, changes in ocean circulation, changes in climate, and changes in geological activity. Now, the Hadal zone also has a strange relationship with the surface because of sinking particles. Marine snow, the steady rain of organic particles, is the main connection between surface life and deep life. But marine snow is not uniform. It depends on surface productivity, it depends on seasons, it depends on climate patterns. It depends on events like algal blooms, so the trench's chemistry can be influenced by what happens far above it. A change in surface plankton communities can change the composition of sinking organic matter. A change in ocean temperature can change productivity. A storm can mix nutrients and trigger blooms. These surface events can affect what eventually reaches the trench bottom. But the time lag can be long. Particles sink slowly. Some are consumed on the way down. Only a fraction reaches the deepest depths. So the trench receives a filtered version of the surface world. This is another reason the chemistry feels strange. It is influenced by the surface, but in a delayed and altered way. Now, let's connect this back to why the Tonga Trench terrifies scientists. Chemistry in the Hadal zone is strange because it is hard to measure, hard to predict, and tightly linked to both biology and geology. It is part of what makes the trench a complex system rather than a simple deep hole. And complexity is unsettling, because complex systems can surprise you. A small change in oxygen levels can affect microbial activity. A change in microbial activity can affect nutrient release. Nutrient release can affect what organisms can survive. Geological events can disturb sediments and release chemicals. Volcanic activity can alter water chemistry. Human pollution can introduce new compounds, so the trench is chemically active, even though it looks still. That is a strange thought. A place of darkness and crushing pressure, and yet chemistry is constantly happening. Reactions, diffusion, decomposition, recycling. The Hadal zone is not frozen in time. It is dynamic, just slow. Now, as we move forward, it's time to take this chemical story and connect it back to one of the most disturbing features of the Tonga region. Earthquakes that occur at depths where rock should not behave like brittle rock. Because chemistry and physics intersect in the deep earth. Water released from minerals can weaken rock. Phase transitions can change mineral structure. These processes can contribute to deep earthquakes. So the next step is to look at earthquakes born in places that should not break, and why the Tonga region produces them so consistently, sending signals from deep inside the planet that remind scientists again and again that the Earth's interior is not as predictable as we would like it to be. Earthquakes feel simple when you only know them from the surface. A fault slips, the ground shakes, the event is recorded, people rebuild, life continues. That is the version most of us carry in our heads, because it matches what we experience. Even if you've never lived through a strong earthquake, you've probably seen videos of one. The shaking looks violent, but the idea behind it seems straightforward. Rock breaks, energy releases, the earth moves. But the deeper you go into the planet, the less that story makes sense. And in the Tonga region, the earth has a habit of producing earthquakes in places where the usual rules say earthquakes should not happen at all. This is one of the most unsettling things about the Tonga Trench system, and it's one of the strongest reasons scientists still speak about it with a certain careful respect. Not because the trench itself is shaking constantly in some obvious way, but because the subduction system beneath it produces deep earthquakes. Earthquakes that come from depths where rock should not behave like a snapping solid. It should behave like something else. It should deform slowly. It should flow. It should creep. It should stretch and squeeze without sudden failure. And yet, it breaks anyway. To understand why this is so strange, it helps to start with the basics of what an earthquake is. An earthquake is a sudden release of stored elastic energy in rock. Stress builds up as tectonic plates move, faults lock. The rock on either side of a fault is forced to deform. Eventually the stress exceeds the friction and strength holding the fault in place, and the fault slips. That slip releases energy in the form of seismic waves. This is why earthquakes are sudden. It's not because the plates move suddenly, plates move slowly. It's because the stress accumulates slowly and then releases quickly. That explanation works well for shallow earthquakes, the kind that occur in the upper crust. Near the surface, the rock is cold enough and brittle enough to fracture. It behaves like a solid that can store stress and snap. But deep inside the earth, conditions change. Temperature increases, pressure increases, rock becomes more ductile, meaning it can deform without fracturing. It becomes more like a solid that can flow over long time scales. It can still be strong, but it doesn't behave like brittle glass. It behaves more like something that bends. This is why deep earthquakes are so unsettling. They are not supposed to happen, at least not in the same way. Most earthquakes occur within the first 70 kilometers of the Earth's surface. These are shallow earthquakes, and they are the ones most likely to cause damage because they are close to people and structures. Then there are intermediate depth earthquakes, which occur between about 70 and 300 kilometers, and then there are deep focus earthquakes, which occur deeper than about 300 kilometers, sometimes as deep as 600 to 700 kilometers. The Tonga region produces these deep earthquakes, and deep focus earthquakes are rare in the global sense. They occur almost exclusively in subduction zones, because subduction zones are the only places where cold, rigid slabs of oceanic lithosphere are carried down into the mantle. So deep earthquakes are like signatures of subduction. But Tonga's deep earthquakes are especially notable because the slab there is steep and fast, and the seismicity extends to great depths. This means the Tonga subduction system is not just producing earthquakes near the surface boundary, it is producing earthquakes deep inside the Earth. That raises a basic question. What is breaking down there? Because the mantle at those depths is hot. It is under enormous pressure. The rock should not be brittle, and yet seismic waves indicate sudden rupture events. This is why scientists sometimes describe deep focus earthquakes as one of the biggest mysteries in seismology. We can record them, we can locate them, we can measure their magnitude, we can analyse their waveforms, but explaining the mechanism is difficult. It is like hearing a glass shatter in a room where the temperature is high enough that glass should be soft. The sound tells you something broke, but the environment tells you it shouldn't. Now, one reason the Tonga region is so important is that it produces enough deep earthquakes to allow detailed study. Each earthquake is a data point. Each one sends waves through the Earth that can be recorded around the globe. Scientists use these waves to map the interior structure, to trace the slab, and to test models of deep earthquake mechanisms. But even with data, the explanation remains challenging. So let's walk through the main ideas scientists use and why none of them are fully comfortable. One leading idea involves dehydration embrittlement. The oceanic plate that subducts carries water. Not liquid water in big pockets, but water locked into minerals. The oceanic crust and the upper mantle portion of the plate contain hydrated minerals formed when seawater interacts with rock at mid-ocean ridges and fractures. As the slab sinks, it heats up. Under increasing temperature and pressure, these minerals become unstable. They undergo metamorphic reactions and release water. This released water can weaken the rock around it. In shallow and intermediate depths, this can help explain earthquakes. Water reduces effective normal stress, lowering friction, making it easier for faults to slip. It can turn stable sliding into unstable slip. It can create conditions for sudden rupture. This mechanism works well up to a certain depth. But deep focus earthquakes occur deeper than the depths where many dehydration reactions are expected to happen. By the time you reach 500 or 600 kilometers, most of the slab should have lost much of its water, so dehydration embrittlement may not explain the deepest events. It might explain some, but not all. Another major idea involves phase transitions in minerals. Deep in the mantle, minerals change structure under pressure. The same chemical composition can rearrange into a different crystal structure. This is not a slow melting process. It can be a solid-state transformation. One important mineral here is olivine, which is common in the upper mantle. Under certain conditions, olivine transforms into a denser form. This transformation is part of what defines the boundary between the upper mantle and the transition zone. But under the cold conditions inside a subducting slab, olivine can persist in a metastable state, meaning it remains in its original form longer than expected. It resists transforming because the slab is colder than the surrounding mantle. If that metastable olivine eventually transforms suddenly, it could create a rapid volume change and release stress, potentially triggering an earthquake. This is sometimes called transformational faulting. The idea is that the mineral transformation creates weakness and sudden deformation, allowing rupture to occur even in a deep environment. This theory is attractive because it links deep earthquakes to the unique conditions of subducting slabs, cold and fast-moving, and it provides a mechanism that could operate at great depths. But it is difficult to test directly. We cannot observe the transformation happening, we infer it. Another idea is thermal runaway. This theory focuses on the idea that deformation generates heat. If a small region of the slab begins to deform, it produces frictional heating. That heating weakens the material, A weaker material deforms faster. Faster deformation produces more heat. This feedback loop can cause a localized zone of rapid failure, producing an earthquake-like event. This mechanism could operate in deep conditions where brittle fracture is not expected, because it relies on instability and deformation rather than classic cracking. Thermal runaway is appealing because it can explain suddenness in a ductile environment. But again, it is difficult to confirm. Deep earthquake science is full of these theories. Each one fits part of the puzzle. None fits all of it perfectly. And that is where the unease comes in, because deep focus earthquakes are not just an academic curiosity. They tell us something about the interior of the Earth that we do not fully understand. They tell us that the subducting slab is not simply sinking smoothly. It is undergoing internal changes. It is storing stress. It is failing in sudden ways. In Tonga, this is especially pronounced. The slab descends steeply. It remains relatively cold compared to the surrounding mantle. It produces deep earthquakes that trace its path. So Tonga becomes one of the clearest examples of the earthbreaking where it shouldn't. Now, it's important to clarify something. Deep earthquakes do not usually cause the same surface damage as shallow ones. The deeper an earthquake occurs, the more the seismic waves spread out and lose intensity before reaching the surface. But deep earthquakes can still be large, and they can still be felt over wide areas. They can also trigger secondary effects in the subduction system. They can alter stress distribution. They can influence shallower faults. They can affect volcanic systems indirectly. So they are not harmless. And even if they were harmless, they would still matter, because they reveal something about how the planet works. Now, Tonga's deep earthquakes also highlight the idea that the Earth is not uniform. We often picture the mantle as a smooth layer of hot rock. But the mantle has structure. It has temperature variations. It has compositional differences. It has slabs sinking through it. It has upwellings rising. It has boundaries where minerals change phase. Deep earthquakes occur in this complex environment. In Tonga, the slab's steep descent may allow it to penetrate deeply, possibly reaching or interacting with the lower mantle. This raises questions about what happens to slabs when they reach the 660-kilometre boundary, the boundary between the upper mantle and the lower mantle. Some slabs flatten out there, some penetrate, some stagnate. The behaviour depends on temperature, composition, and the dynamics of mantle convection. Tonga's slab may be one of the slabs that penetrates deeply. If so, that has implications for mantle circulation and for how the Earth mixes material over long timescales. Deep earthquakes can provide clues about this. Now, there is another unsettling aspect of deep earthquakes. They are not always isolated events. They can occur in clusters. They can have aftershocks. They can have complex rupture patterns. In shallow earthquakes, aftershocks are common because the main rupture changes stress on nearby faults, triggering additional slips. Deep earthquakes can also have aftershocks, which suggests that even at depth, the rock can behave in a way that allows stress transfer and triggered failure. This is surprising because it implies a brittle-like behaviour in a region that should be ductile. So deep earthquakes are not just single events. They can be part of a system of failure. This reinforces the sense that the deep slab is not stable. It is changing, cracking, transforming, and releasing energy. Now, the Tonga region is also known for producing some of the largest deep earthquakes ever recorded. Deep earthquakes can reach magnitudes above 7.0. They can be felt across continents. They can produce long-period shaking. These events remind scientists that deep earthquakes are not small anomalies. They can be powerful, and power in the deep earth is unsettling because it is hard to relate to. At the surface, we can see faults. We can map them. We can measure slip. We can study rocks directly. In the deep earth, we cannot. We rely on seismic waves. Seismic waves are like messages sent through the planet. They carry information about what happened and what the Earth is made of. But interpreting those messages requires models, assumptions, and careful analysis. So deep earthquakes are both data and mystery. They give us information, but they also remind us how indirect our knowledge is. Now, this connects back to the Tonga Trench itself, The trench is the surface expression of the subduction zone. It is the place where the slab begins its descent. The deep earthquakes are part of that descent, so the trench is not just a deep place in the ocean, it is the beginning of a deep process in the earth. And that process includes failure at depths where failure should not happen. This is why scientists sometimes describe subduction zones like Tonga as places where the earth is doing something complicated and not fully understood. The slab is sinking, but it is also interacting with the mantle. It is releasing fluids. It is changing minerals. It is generating earthquakes. It is feeding volcanoes. It is a system that operates on many levels at once. Now, to make this feel more real, imagine a piece of oceanic plate as it approaches the trench. At the surface, it is cold. It is dense. It is carrying sediments and hydrated minerals. It bends downward. It begins to sink. As it sinks, it heats up slowly, but it remains colder than the surrounding mantle for a long time. It passes through depths where dehydration reactions occur, releasing water. It passes through regions where minerals change phase. It passes through zones where stress accumulates and releases. Along the way, earthquakes occur. Some are shallow, some are intermediate, some are deep. Each one is a crack in the descent, a sudden adjustment in a slab that is being forced into a new environment. This is why deep earthquakes feel like they shouldn't exist. They are the sound of the slab failing in a place where failure is unexpected. Now, the fear scientists feel is not fear of the earthquake itself, in the moment. It is fear of the unknown mechanism. Because if we do not fully understand why deep earthquakes happen, we do not fully understand how slabs behave. And if we do not fully understand slab behaviour, our models of the Earth's interior are incomplete. This matters because the Earth's interior influences surface processes. It influences volcanism. It influences plate motion. It influences long-term climate through carbon cycling. It influences the evolution of continents. So deep earthquakes are not isolated curiosities. They are part of the planet's system. And Tonga is one of the best places to study them. But studying them means admitting uncertainty. It means accepting that even with modern instruments, even with global seismic networks, even with decades of research, there are still processes in the Earth that we cannot explain fully. That is humbling. And humility can feel like fear when the thing you are studying is powerful. Now, as we continue, the next step is to focus on one specific category of deep earthquakes that is especially associated with this region. Deep focus quakes, the ones that occur hundreds of kilometers down, and why they are so strange that they have forced scientists to rethink what they thought they knew about rock, pressure, and the limits of brittle failure. Because Tonga does not just produce earthquakes. It produces earthquakes from depths that make you stop and check the numbers, and then check them again, just to be sure the Earth really did that. Deep focus earthquakes are the kind of events that make scientists pause, even after decades of studying earthquakes. Not because they are always the biggest, and not because they always cause the most damage at the surface, but because they happen in a part of the Earth where the usual earthquake logic starts to fall apart. When you learn about earthquakes in a basic way, the explanation feels clean. Stress builds up along a fault. The fault locks. The rock stores elastic energy. Then the rock breaks or slips suddenly, and the energy is released as seismic waves. That story makes sense near the surface, where rock is cold enough to fracture. But deep focus earthquakes happen far below the surface. They happen deep inside subducting slabs, hundreds of kilometers down, in regions where the rock should not behave like brittle rock. It should not snap. It should not rupture suddenly. It should not create the kind of sharp seismic signals that we associate with a fault breaking. And yet, deep focus earthquakes do exactly that. This is why they are mysterious. They are not supposed to exist in the form we observe them, and the Tonga subduction zone is one of the most important places in the world for studying them, because it produces deep focus earthquakes frequently and clearly. It's like the Earth keeps repeating the same impossible trick in the same region, giving scientists more chances to watch and measure it. Now, the first thing to understand is what deep focus means in practical terms. Most earthquakes happen at depths less than 70 kilometers. These are shallow earthquakes. They are common. They can be destructive. They are close enough to the surface that the shaking is intense. Intermediate depth earthquakes occur between about 70 and 300 kilometers. These are also common in subduction zones. Deep focus earthquakes occur deeper than about 300 kilometers, sometimes reaching depths near 700 kilometers. That is not a small difference. That is not a little deeper. That is a completely different environment. At 300 kilometers, you are deep in the mantle. At 600 kilometers, you are approaching the boundary between the upper mantle and the lower mantle. Temperatures are high. Pressure is immense. The rock is under conditions that change its behavior. So deep focus earthquakes are not just deeper versions of shallow earthquakes. They are something else, and this is where the mystery begins. Because brittle fracture, the classic rock breaks idea, requires rock to behave elastically and store stress. It requires a certain level of rigidity. It requires that the rock cannot simply flow to relieve stress. Near the surface, that is true. The rock is cold enough that it behaves brittlely. At great depth, the rock is hotter and under higher pressure, and it tends to deform plastically, meaning it can change shape slowly without breaking. If you take a metal spoon and bend it slowly, it deforms plastically. It does not snap like glass. Deep mantle rock behaves more like that spoon over long time scales. So how do you get a sudden rupture event in that environment? That is the core question, and it has several possible answers, but none of them fully closes the case. One way to approach this is to think about what makes subduction zones special. Deep focus earthquakes do not happen randomly in the mantle. They happen in subducting slabs. A subducting slab is a piece of cold oceanic lithosphere that has been carried down into the mantle. It is colder than the surrounding mantle, sometimes by hundreds of degrees. It is also mechanically different. It can remain rigid and strong as it sinks, even while the surrounding mantle is softer and flowing, so the slab is like a cold blade moving into a warm environment. That matters because temperature controls how rock deforms. Cold rock is stronger and more brittle. Warm rock is weaker and more ductile. So deep focus earthquakes occur in the cold slab, not in the warmer mantle around it. This already helps. It means the environment is not uniformly ductile. There is a rigid structure within it. But it still doesn't fully solve the problem, because even cold slabs are still at high temperature and pressure at great depth. So scientists need mechanisms that can create sudden failure even in a high-pressure, high-temperature environment. Now, one of the leading candidates is mineral phase transformation, especially involving olivine. Olivine is a common mineral in the upper mantle. Under certain conditions, olivine transforms into denser forms as pressure increases. This is part of what defines the mantle transition zone, between about 410 and 660 kilometers depth. Normally, as mantle rock sinks or as pressure increases, olivine changes structure. It becomes a different mineral phase. This is not melting, it is a rearrangement of atoms into a denser configuration. But in a cold subducting slab, this transformation can be delayed. The slab is cold enough that the transformation happens more slowly. This means olivine can persist in a metastable state, at depths where it should have already transformed. This metastable olivine is like a loaded spring. It is stable enough to exist, but it is not in its preferred state at that pressure. It is waiting. If conditions change, or if the transformation begins in one region, it can propagate, creating a sudden transformation front. This transformation can produce a rapid change in volume and mechanical properties. It can weaken the rock. It can create shear zones. It can allow sudden slip. This idea is often called transformational faulting. The concept is that deep focus earthquakes are not classic brittle fractures. They are rupture events driven by mineral transformations inside the slab. This is appealing because it fits the location of deep earthquakes. It fits the depth range. It fits the idea that slabs are cold and can carry metastable minerals deep. But it still leaves questions. How exactly does the transformation create a rupture that produces seismic waves similar to shallow earthquakes? How does the rupture propagate so quickly? How does it generate the observed waveforms? Scientists have models, but the details are complex. Another candidate mechanism is dehydration-related processes, but at deep focus depths, dehydration alone is less likely to be the main driver, because most of the slab's water should have been released at shallower depths. Still, some water can be carried deeper than expected, depending on mineral composition and slab temperature. Water can influence phase transitions and deformation, so even if dehydration is not the direct trigger, water may still play a supporting role. Then there is thermal runaway, another idea that sounds simple but becomes complicated when you dig into it. Thermal runaway is based on a feedback loop. If a small region inside the slab begins to deform, it generates heat. That heat weakens the material. A weaker material deforms faster. Faster deformation generates more heat. This can concentrate deformation into a narrow zone and cause a sudden failure event. In other words, the slab can develop a localized shear zone that fails rapidly, producing an earthquake. This mechanism does not require brittle fracture in the traditional sense. It requires an instability in deformation. It is like bending something until a small region becomes hot and soft, and then all the deformation focuses there. This is plausible at depth, where temperature and pressure allow ductile deformation, but where sudden localization could still produce seismic signals. But again, the details are hard. How does the slab develop the initial instability? How does the heat build fast enough? How does the rupture propagate? Now, the reason deep focus earthquakes are so mysterious is not just because we lack a single explanation. It's because the earthquakes themselves behave in ways that make them feel surprisingly familiar. Deep focus earthquakes produce seismic waves that travel through the Earth and are recorded worldwide. They have distinct P waves and S waves. They have focal mechanisms that indicate shear failure. They can have aftershocks. They look like earthquakes. And that is part of the problem. Because if they look like earthquakes, we want them to be earthquakes in the usual sense. We want them to be fault slipping. But the environment suggests they should not be. So the mystery is partly psychological. It is the mismatch between what the data shows and what the environment should allow. Now, the Tonga subduction zone is especially important because it produces a lot of deep seismicity. If you look at global maps of deep focus earthquakes, you see clusters in certain subduction zones. Tonga Kermadec is one of the main clusters. Japan has deep earthquakes. The Izubonin-Mariana system has deep earthquakes. Some parts of South America have deep earthquakes. But Tonga stands out because of how steep the slab is and how deep the seismicity extends. The slab there is like a straight descent into the mantle. This makes it easier to study in some ways. The geometry is clearer. The seismicity outlines the slab. So Tonga provides a kind of clean laboratory for deep focus earthquake science. But it is still not easy. Because deep focus earthquakes are not just rare curiosities. They can be large, and they can happen suddenly, and they can occur at depths where we cannot observe directly. We cannot drill there. We cannot send instruments into the slab. We cannot sample the rock at 600 kilometers depth. We can only infer what is happening from seismic waves. That means deep focus earthquake science is like detective work. You have signals recorded at the surface. You have models of how waves travel through the Earth. You have theories about mineral behavior. You have laboratory experiments on rocks at high pressure and temperature, using devices like multi-anvil presses and diamond anvil cells. You combine all of that and try to build a consistent story. But it's still a story built from indirect evidence. This is another reason deep focus earthquakes are unsettling. They remind us that much of Earth science is inference. We are studying a planet we live on, but we cannot access most of it. We live on the crust, a thin skin. Everything below is mostly out of reach. So deep focus earthquakes are one of the few direct signals from that hidden world. They are like knocks from the inside. Now, deep focus earthquakes also have some strange properties that differ from shallow earthquakes. For example, Deep focus earthquakes often have less aftershock activity compared to shallow earthquakes, although aftershocks do occur. The rupture process may be different. Deep earthquakes can also have higher stress drops, meaning the amount of stress released per unit area can be larger. This suggests the rupture may involve stronger material or different failure conditions. Deep earthquakes also occur in a narrower region, within the slab compared to shallow earthquakes, which can occur along broader fault zones. These differences hint that the mechanism is not exactly the same as shallow fault slip. So deep focus earthquakes are both familiar and unfamiliar. They look like earthquakes, but they behave slightly differently. Now, why does this matter beyond academic curiosity? Because deep focus earthquakes tell us about slab dynamics. The subducting slab is not just sinking, it is deforming, it is bending, it is stretching, it is undergoing mineral transformations, it is interacting with mantle flow. Deep earthquakes are one way the slab releases internal stress. This internal stress can come from several sources. The slab bends as it enters the trench. That bending creates stress. The slab experiences resistance as it sinks into the mantle. That creates stress. The slab may be pulled downward by its own weight, creating tension. The slab may be compressed in some regions and stretched in others. The slab may be interacting with the 660-kilometre boundary, which can act like a barrier or a transition zone. All of these factors create stress patterns. Deep earthquakes occur where stress is concentrated and where failure mechanisms can operate. So deep focus earthquakes are like stress markers in the slab. They show us where the slab is under strain. In Tonga, the pattern of deep earthquakes can reveal how the slab is behaving. Is it tearing? Is it folding? Is it deforming? Is it stagnating or penetrating deeper? These are the questions scientists ask. Now, there is another unsettling aspect of deep focus earthquakes. They can be very large, and because they occur deep, they can be felt over huge distances. A shallow earthquake might cause intense shaking locally, but its effects may be limited in distance. A deep earthquake, because it is deep, sends waves that spread widely. The shaking may be less intense in any one place, but it can be felt across a broad region. This can make deep earthquakes feel strange to people who experience them. They may feel a long rolling motion rather than sharp jolts. They may feel it far from the epicenter. It can be confusing. So deep earthquakes have a different character, and that character reflects their depth. Now, deep focus earthquakes also matter because they can influence the stress state of the subduction zone. A deep earthquake can alter stress in the slab and in the surrounding mantle. It can potentially affect shallower seismicity, although the connection is complex. It can also influence the slab's ability to transport water and material downward. If the slab fractures or deforms, it may create pathways for fluids. So deep earthquakes are part of the subduction system's evolution. Now, the Tonga region is a place where deep focus earthquakes occur frequently enough that scientists can build detailed catalogues. They can analyse patterns over time. They can look for clustering. They can study how deep earthquakes relate to slab geometry. They can compare Tonga to other subduction zones. This comparative approach is important because it helps identify what factors matter. Why do some subduction zones produce many deep earthquakes and others produce fewer? Is it slab age, convergence rate, slab temperature, water content, geometry? Tonga provides one end-member example, steep and fast, so it helps constrain models. Now, even with all this, the mystery remains. Deep focus earthquakes are still not fully explained, and that is what makes them so unsettling. They are reminders that the Earth's interior has behaviours we can observe but not fully understand. They are reminders that our planet is not a static rock. It is an active system with processes that operate far below our reach, and Tonga is one of the places where those processes announce themselves most clearly. Now, after deep focus earthquakes, the next thing to consider is how the subduction zone's geometry and speed can create additional stress and hazards. In particular, how one subduction zone can pull too hard how slab pull and trench rollback can reshape the region, and how that can contribute to both seismic and volcanic activity. Because Tonga is not just a place where the slab sinks, it is a place where the slab's motion is strong enough to affect everything around it, like a heavy object falling through a flexible surface and dragging the edges along with it. If you could watch the Earth from far enough away and fast enough, plate tectonics would look less like a slow crawl and more like a system under constant tension. Not the dramatic tension of a single earthquake or eruption, but the steady mechanical tension of a planet that never stops moving. And in that system, subduction zones are not passive boundaries, they are active engines. They do not simply sit there while plates slide around them. They pull, they drag, they bend rock, they reshape entire regions. Some subduction zones do this more aggressively than others. The Tonga subduction zone is one of them. This is one of the reasons the Tonga Trench still terrifies scientists. It is not just deep, it is not just active. It is part of a subduction system that seems to pull harder than you would expect, and when one subduction zone pulls too hard, the effects do not stay neatly confined to the trench itself. They spread. They show up in earthquakes, in volcanic activity, in the opening of back arc basins, in the way the seafloor is shaped, and in the way the entire region moves like a stressed piece of machinery. To understand what it means for a subduction zone to pull too hard, you have to start with one of the most important forces in plate tectonics: slab pull. Slab pull is exactly what it sounds like. A subducting slab of oceanic lithosphere sinks into the mantle because it is denser than the surrounding material. As it sinks, it exerts a pulling force on the rest of the plate still at the surface. It is like a heavy curtain being pulled down through a narrow opening. The part that has already gone through keeps falling, and it drags the rest behind it. This force is considered one of the main drivers of plate motion. There are other forces too, like ridge push, where plates slide away from elevated mid-ocean ridges, and mantle flow, which can assist or resist motion. But slab pull is often described as the strongest, and Tonga has a lot of slab pull. The Pacific plate in this region is old and cold. Old oceanic crust is denser because it has cooled and thickened over time. That density makes it sink more readily when it reaches a subduction zone. So when the Pacific plate reaches the Tonga Trench, it does not just bend and slide down slowly, it sinks, and the sinking is fast. This is one of the fastest converging subduction zones on Earth. The exact rates vary depending on how you measure and which segment you focus on, but the overall picture is that the Pacific plate is being consumed quickly here. That speed matters, because a fast-sinking slab does not just disappear into the mantle quietly. It creates stress, it creates deformation, it creates motion in the surrounding plates. It also creates a kind of mechanical imbalance. If one part of a plate boundary is pulling strongly downward, it can change the shape of the boundary. It can cause the trench to migrate. It can cause the overriding plate to stretch. This brings us to another key idea: trench rollback. Trench rollback is the process where a trench moves backward relative to the overriding plate. This happens when the subducting slab sinks steeply and pulls the trench toward the ocean side while the overriding plate remains relatively stable or moves differently. It is easier to picture with a simple mental image. Imagine pushing a stiff sheet of paper down into a thick liquid. As the paper sinks, the point where it bends downward can shift. The bend can migrate. In the Earth, the subducting slab is like that sheet, and the mantle is like the thick liquid. As the slab sinks, it can pull the hinge point backward, causing the trench to retreat. This trench retreat can have major consequences. When the trench retreats, the overriding plate can be stretched behind the volcanic arc. That stretching can lead to back arc spreading, where new oceanic crust forms. And this is exactly what we see behind Tonga. The Lau Basin, behind the Tonga volcanic arc, is a back arc basin where the crust is being pulled apart and new seafloor is forming. This is not a minor detail, it is a sign that the subduction zone's pull is strong enough to reshape the overriding plate. So the Tonga region is not just a place where crust is being destroyed, it is also a place where crust is being created nearby. because the system is being pulled apart. This is what happens when a subduction zone pulls too hard. It does not just consume, it reorganizes. Now, from a scientific perspective, this is fascinating. It is one of the clearest examples of how subduction dynamics can drive back arc spreading. But from a hazard perspective, it is unsettling. Because when a region is being pulled apart and compressed at the same time, it becomes a place of stress. Stress is not distributed evenly. It concentrates along faults. It builds in zones of weakness. It releases in earthquakes. It influences magma pathways. So the Tonga system becomes a region where multiple tectonic processes overlap. Subduction at the trench, volcanism in the arc, extension in the back arc basin, deep slab descent and deep earthquakes. This overlap is what makes the system feel like it is pulling too hard. It is doing too many things at once. Now let's talk about how this pull affects earthquakes. At the shallow level, the boundary between the subducting plate and the overriding plate can lock and release in large earthquakes. These are the classic subduction zone megathrust earthquakes that can generate tsunamis. At intermediate depths, the slab itself can produce earthquakes as it bends and deforms. At deep levels, the slab produces deep focus earthquakes as it undergoes transformations and internal failure. So the slab pull system is associated with seismicity at many depths, but the pull also affects the stress state of the overriding plate. When the overriding plate is stretched in a back arc region, it can develop normal faults. These faults can produce earthquakes, they can create rift zones, they can influence magma ascent. So the system is not just generating earthquakes at the trench, it is generating earthquakes throughout the region. This makes the hazard picture more complex. Now, the pull also affects volcanoes. Volcanic arcs form because the subducting slab releases fluids into the mantle above, triggering melting. The magma rises and forms volcanoes. But the exact behaviour of volcanism depends on slab geometry and a mantle flow. If the slab is steep and sinking quickly, it can influence how mantle material flows around it. It can influence where melting occurs. It can influence the chemistry of magma. In Tonga, the steep slab and the back arc spreading create a dynamic mantle environment. Mantle material can flow into the back arc region. Melting can occur in multiple zones. Magma can have different compositions depending on its source. So volcanism in Tonga is not a simple arc volcano story. It is a system influenced by both subduction and extension. This can contribute to unusual volcanic behaviour. It can also contribute to the formation of many submarine volcanoes in the back arc region, and submarine volcanoes are harder to monitor and harder to predict. So again, the pull creates complexity. Now the idea of pulling too hard also shows up in how the slab itself behaves. A slab sinking rapidly can experience strong tension. It can be stretched as it descends. It can bend sharply. It can interact with mantle boundaries. In some cases, slabs can tear. Slab tearing is exactly what it sounds like. The slab develops a break or a tear, often because different parts of the slab are moving differently or because the slab encounters resistance. A tear can change mantle flow patterns. It can create pathways for hot mantle material to rise. It can influence volcanism. It can also create unusual seismic patterns. In Tonga, scientists have investigated whether parts of the slab might be tearing or deforming in complex ways, because the system is so active and the slab geometry is so steep. Even if a slab does not fully tear, it can warp and fold. And warping and folding can influence where earthquakes occur. So the pull is not just a surface force, it is a deep force that shapes the slab itself. Now, there is another way the pull shows up, and it is subtle but important. It affects the motion of the plates around it. Tonga is not just interacting with the Pacific plate, it is part of a region where multiple plates and microplates interact. The plate boundaries in the Southwest Pacific are complex. There are arcs, basins, and small plate fragments. When the Tonga subduction zone pulls strongly, it can influence the motion of these smaller plates. It can contribute to the opening of basins. It can change the stress distribution in the region. So the Tonga system is not isolated. It is part of a network of plate interactions. This is why scientists sometimes describe the Southwest Pacific as one of the most complex tectonic regions on Earth. And complexity again means unpredictability. Now, the reason this matters for the Tonga Trench's reputation is that the trench is the surface expression of this pull. It is the visible edge of a slab that is sinking with force. When you look at the trench on a map, you're looking at the hinge point of a massive descending plate. The trench is not just deep, it is dynamic. It is not just a scar, it is a moving boundary, so the trench becomes a symbol of the system's power. Now, it's also worth thinking about what happens over long timescales. Over millions of years, slab pull can reorganize entire regions. It can cause arcs to migrate. It can open basins. It can create new plate boundaries. The Tonga arc has likely moved and evolved over time. The low basin has opened. The trench has shifted. The system has changed. So the region is not fixed. It is evolving. This is important because it means hazards and activity patterns can change too. A region that is quiet now may become more active later. A volcanic system may shift. A basin may open faster. A fault may become more stressed. The Earth does not promise stability. Now, in a practical sense, when scientists monitor a subduction zone like Tonga, they are trying to understand not just what is happening now, but how the system is likely to behave in the future. They want to know where stress is building. They want to know what kinds of earthquakes are possible. They want to know how volcanic activity might change. But because the system is complex, the answers are probabilistic rather than certain. Scientists can say, this region is capable of producing large earthquakes. They can say, this region is capable of generating tsunamis. They can say, this region has active volcanism. But they cannot say, this exact event will happen at this exact time. So the pull remains a source of uncertainty. Now, one of the most unsettling consequences of a strong subduction system is tsunami generation. Tsunamis are not guaranteed after every earthquake. Many earthquakes do not generate significant tsunamis, but subduction zones are the main source of the largest tsunamis because megathrust earthquakes can displace huge volumes of water. The Tonga region has tsunami risk, and it has produced tsunamis from both tectonic and volcanic sources. When a subduction zone pulls hard, it can produce large earthquakes. When it produces large earthquakes, it can generate tsunamis, so the pull connects directly to hazard. This leads us naturally to the next focus, the tsunami problem that no one can fully predict. Because even if you understand slab pull and trench rollback and back arc spreading, you still face the reality that tsunamis are shaped by many factors, and the Tonga region has multiple ways of generating them. So the next step is to look at why tsunami prediction remains difficult, why the Tonga system complicates it, and why the ocean can go from calm to dangerous in a way that feels almost unfair, especially in a region where the surface looks peaceful most of the time. A tsunami is one of the most unfair things the ocean can do, not because it is mysterious in the basic sense. Scientists understand what a tsunami is. They understand the physics of waves. They understand how earthquakes can move the seafloor and displace water. They can model wave propagation across ocean basins. They can build warning systems and evacuation plans. But even with all of that knowledge, tsunamis still have a way of arriving like a surprise. They still have a way of turning a calm coastline into a dangerous place within minutes. And in regions like Tonga, where the ocean can look peaceful while the earth underneath is constantly moving, the tsunami problem becomes especially difficult. Not impossible, but difficult in a way that makes scientists careful about what they promise, because the truth is simple and uncomfortable. No one can fully predict tsunamis. They can estimate risk, they can detect triggers, they can issue warnings, they can improve response times. But the exact behaviour of a tsunami, how big it will be, where it will hit hardest, and how it will interact with a specific coastline is still hard to know with certainty in the moment when it matters most. and the Tonga Trench system adds extra layers of complexity because it is not just one tsunami source. It is multiple sources stacked in the same neighbourhood. Earthquakes, underwater landslides, volcanic eruptions, collapse of volcanic structures. Each of these can move water in different ways. Each of these can produce waves with different timing, different directions, and different characteristics. So Tonga's tsunami problem is not a single problem. It is a collection of problems. Now, let's start with the most familiar tsunami source, subduction zone earthquakes. When most people think of tsunamis, they picture a huge earthquake offshore. The seafloor suddenly shifts, water is displaced, a wave travels outward. That picture is accurate, but it leaves out the details that make prediction hard. In a subduction zone, the boundary between the plates can lock. The subducting plate keeps moving, but the fault is stuck. Stress builds. The overriding plate is pulled down and compressed. When the fault finally slips in a megathrust earthquake, the overriding plate can spring upward, lifting the sea floor. That vertical movement is what creates a major tsunami. But not every subduction earthquake produces a tsunami, and not every tsunami-producing earthquake produces the same kind of tsunami. The key factors include how much slip occurred, how large the rupture area was, how shallow the rupture reached, how much vertical displacement happened, the direction the rupture propagated, the shape of the seafloor above the rupture. So even if you know the earthquake magnitude, you still may not know the tsunami size immediately. Magnitude is a measure of total energy release, but tsunami generation depends strongly on the geometry of seafloor displacement. A deep earthquake might have a large magnitude but produce little tsunami because it does not displace the seafloor effectively. A shallower earthquake with similar magnitude might produce a much larger tsunami. This is one of the first reasons prediction is difficult. Now, in Tonga, earthquakes happen frequently. Many are not tsunami generating, but the region is capable of producing large subduction earthquakes that can generate tsunamis, so the risk is real. But Tonga's tsunami problem is complicated by the trench's geometry and the region's seafloor shape. Trenches are not flat surfaces. The seafloor slopes steeply. There are ridges, seamounts, and irregular terrain. There are volcanic structures. There are basins. When a tsunami wave travels across the ocean, it interacts with this terrain. In deep water, a tsunami wave is not a tall-breaking wave. It is a long, low wave that can travel fast, hundreds of kilometers per hour. It can pass beneath ships without being noticed, but when it approaches shallow water, it slows down, and the wave height increases. The energy is compressed into a smaller water column. This is when it becomes dangerous. The way it grows depends on the shape of the seafloor and the coastline. A gently sloping coast might produce a different run-up pattern than a steep coast. A bay can funnel waves and amplify them. A reef can break waves and reduce energy in some cases, but it can also create complex currents. Islands can block waves, but they can also reflect and refract them, creating unexpected patterns. So even if you know a tsunami is coming, predicting exactly how it will behave at a specific island is difficult. And Tonga is a chain of islands, not a single coastline. This makes the problem more complex. A tsunami might hit one island hard and another less hard, depending on the direction of wave travel, the local bathymetry, and the shape of the coastline. Now, beyond earthquakes, Tonga also has volcanic tsunami sources. The eruption of Hunga Tonga Hunga Ha'apai showed the world that volcanic tsunamis can be different from tectonic tsunamis. Volcanic tsunamis can be generated by explosive eruptions that displace water, by collapse of volcanic structures, by pyroclastic flows entering the ocean, or by underwater landslides triggered by volcanic activity. These processes can generate waves quickly and locally, and local tsunamis are especially dangerous because they arrive fast. If a tsunami is generated far away, warning systems can detect it and send alerts before it arrives. People may have hours. If a tsunami is generated nearby, the warning time can be minutes. In some cases, the first warning is the shaking itself, or the sudden withdrawal of water. In volcanic tsunamis, there may not even be strong shaking because the trigger is not necessarily a major earthquake, so the warning cues can be less obvious. This is one reason scientists find volcanic tsunamis particularly difficult. They can be sudden, localized, and hard to detect with standard earthquake-based warning systems. Now, Tonga's region also has underwater landslide tsunami sources. Subduction zones produce steep slopes and unstable sediments. Earthquakes can trigger landslides. Volcanic activity can destabilize slopes. Sediment can accumulate and then fail. When a large mass of sediment slides down a slope, it displaces water and can generate a tsunami. These tsunamis can be very localized, but they can also be powerful. Landslide tsunamis are difficult because they are harder to detect. An earthquake is easy to detect globally. Seismic networks pick it up instantly. Magnitude and location can be estimated quickly. A landslide underwater may not produce a strong seismic signal, or it may produce a signal that is hard to interpret quickly. So landslide tsunamis can occur without a clear immediate trigger. This adds uncertainty. Now, even when warning systems work well, there is still the problem of the first wave not always being the largest. This is something that surprises people. A tsunami is not one wave. It is a series of waves. The first wave might be small, the second might be larger, the third might be larger still. The interval between waves can be minutes to tens of minutes. This makes response difficult because people might see a small wave and assume the danger is over. It isn't. In Tonga, where islands are close to the source, wave trains can arrive quickly and in complex patterns. Reflections off islands and seafloor features can create multiple arrivals, so the danger can last longer than people expect. Now, another factor that makes tsunamis hard to predict is the way they interact with tides. If a tsunami arrives at high tide, the water level is already elevated. The run-up can be worse. Flooding can extend farther inland. If it arrives at low tide, the visible effect might look different, but currents can still be dangerous, so timing matters. But in the moment of an event, predicting exact arrival time and tide interaction for each island is not always straightforward. Now, from a scientific standpoint, one of the main tools for tsunami warning is the combination of seismic data and sea level data. Seismic data tells you an earthquake happened. Sea level data from tide gauges and deep ocean pressure sensors tells you whether a tsunami wave is actually moving through the ocean. Systems like deep ocean tsunami detection buoys can measure pressure changes as a wave passes. These measurements can confirm a tsunami and help estimate its size, but coverage is not perfect everywhere. The Pacific has warning systems, but there are gaps. Remote regions can have fewer instruments, and the Tonga region's remoteness is part of the challenge. Maintaining sensors in the open ocean is difficult. They can fail, they can be damaged by storms, they can be expensive to replace, so sometimes the data is incomplete, and incomplete data means more uncertainty. Now, there is also a modelling problem. Tsunami models are powerful. They use bathymetry data, seafloor maps, and physics equations to simulate wave propagation. But models depend on input. If the input earthquake parameters are wrong, the model output will be wrong. If the bathymetry data is incomplete or low resolution, the model will miss important seafloor features that influence wave behaviour. In some regions, bathymetry is still not mapped in fine detail. Trenches are deep and difficult to map. Ships can map from above, but resolution decreases with depth. Submersibles can map locally, but coverage is limited, so even the seafloor map itself can be uncertain. This matters because small features can have big effects on wave focusing. A ridge can refract a wave, a seamount can scatter it, a channel can funnel it. So the tsunami problem is partly a mapping problem. Now, there is another subtle issue that makes Tonga's tsunami problem especially unsettling. The region has both tectonic and volcanic tsunami sources, and these sources can occur close together in time. For example, an earthquake might trigger a landslide, producing a tsunami. A volcanic eruption might be associated with seismic activity, producing both seismic signals and water displacement. so you can have multiple wave sources overlapping. This can create complex wave trains. It can also confuse interpretation. If you detect an earthquake and predict a tsunami, but then a landslide adds extra energy, the tsunami might be larger than expected. If you detect an eruption but the main tsunami source is a collapse event, the wave characteristics might differ from typical eruption-based models. So the system can surprise. Now, the Tonga eruption is a perfect example of this complexity. The eruption produced tsunamis, but it also produced atmospheric shock waves. Those shock waves affected sea level measurements in ways that were unusual. Some tide gauges recorded sudden changes associated with pressure waves. This was not the standard tsunami scenario. It showed that in rare cases, the atmosphere and ocean can interact in ways that complicate tsunami signals. So Tonga's tsunami problem includes not only seafloor displacement, but also atmospheric effects and extreme volcanic events. That is not something most people think about when they think about tsunamis, but it matters for prediction and interpretation. Now, all of this can sound discouraging, but it is important to emphasize something. Even if tsunamis cannot be fully predicted, warning systems still save lives. The goal is not perfect prediction. The goal is fast detection, clear communication, and effective response. In many cases, tsunami warnings provide enough time for evacuation. Education also matters. In tsunami-prone regions, people are taught to recognize natural warnings: strong shaking, sudden sea withdrawal, unusual roaring sounds. If you feel strong shaking near the coast, you do not wait for an official warning. You move to higher ground. That simple rule saves lives. In Tonga, as in other Pacific Island nations, tsunami awareness is part of living with the ocean. But the scientific challenge remains. Scientists want to reduce uncertainty. They want to improve models. They want to map the seafloor better. They want more sensors. They want better understanding of volcanic tsunami mechanisms. And Tonga is one of the places where these improvements matter most, because it is remote, active, and complex. Now, as we continue, it makes sense to look at the volcanic and tectonic landscape that sits behind the trench, because the tsunami problem is connected to the region's broader geological activity. The Tonga system is not just a trench and an arc. It includes back arc basins, underwater volcanoes, and seafloor spreading. These features shape the hazards and the science. So the next step is to explore the moving seafloor behind Tonga, the volcanoes and basins that form a constantly changing landscape, and why the region feels like it is never fully settled, even when the ocean above it looks calm. If you could peel back the ocean and look at the ground beneath Tonga, you would not see a stable foundation. You would see movement, not movement in the dramatic sense of waves and storms, but movement in the geological sense. The kind of motion that reshapes the seafloor over time, building new crust in one place while destroying it in another, cracking it open behind the volcanic arc, and feeding volcanoes that sometimes sit above the surface and sometimes stay hidden below it. This is one of the reasons the Tonga region feels so intense. The trench is the headline feature, the deep cut in the ocean floor that grabs attention. But the trench is only the front edge of a larger machine. Behind it, the system continues. Volcanoes rise along the arc. The back arc basin stretches and splits. The seafloor opens, creating new crust. Underwater mountains grow and collapse. Hydrothermal systems release mineral-rich fluids. Earthquakes mark the shifting stresses. So when scientists talk about Tonga, they are not just talking about one deep place. They are talking about a whole region where the seafloor is in motion. And motion means change. Change means uncertainty. That combination is why the area has such a strong hold on researchers. It is a place where the planet is actively building and breaking itself at the same time. Now, to make sense of this, it helps to start with a simple map in your head. At the front edge of the system you have the Tonga Trench. That is where the Pacific Plate bends downward and begins to sink beneath the plate system to the west. A little farther west of the trench, you have the Tonga Volcanic Arc, a chain of volcanoes and islands. Some of these volcanoes rise above the surface as islands, many are underwater, and behind the arc, farther west again, you have the low basin, the back arc basin. So the system is arranged in layers: trench, arc, back arc basin. Each layer is connected to the same tectonic engine, but each behaves differently. The trench is where the plate goes down. The arc is where magma rises. The back arc basin is where the crust stretches and splits. Now, if you've never heard of a back arc basin before, it can sound strange. We're used to thinking of plate boundaries as either convergent, where plates collide, or divergent, where plates pull apart. A back arc basin is a place where both are happening in the same general region. You have subduction at the trench, a convergent boundary, and you have spreading behind the arc, a divergent-like process. This seems contradictory at first, but it makes sense when you think about slab pull and trench rollback, which we talked about earlier. If the subducting slab sinks steeply and pulls strongly downward, it can cause the trench to retreat. As the trench retreats, the overriding plate can be stretched behind the volcanic arc. That stretching can thin the crust, create faults, and eventually open a spreading centre. That spreading centre creates new seafloor, so the back arc basin is a response to the subduction zone's motion. It is the system's way of adjusting, but adjustment does not mean stability. It means ongoing deformation. In the Lau Basin, spreading is active. The seafloor is being created in segments, not necessarily as a single clean ridge like the Mid-Atlantic Ridge, but as a complex system of spreading centres, rifts, and volcanic features. This creates a seafloor that is not smooth. It is broken and young. Young seafloor is different from old seafloor. Old oceanic crust has had time to cool, thicken, and accumulate sediments. It becomes smoother under layers of sediment. Young crust is still hot. It is thin. It is rough. It is actively cracking and forming. It often has volcanic features, ridges, and fissures. So behind Tonga, the seafloor is young and restless. This matters because it creates a region of underwater volcanism that is not limited to the main volcanic arc. In many subduction systems, volcanism is concentrated in the arc. But in back arc basins, volcanism can occur behind the arc as well, because spreading and thinning of the crust allows magma to rise. So the Tonga region is a place with multiple volcanic zones, the arc volcanoes fed by subduction fluids, the back arc volcanoes fed by decompression, melting and mantle flow. This creates variety in magma chemistry. Subduction zone magma tends to be influenced by water and sediments from the slab. It can be more viscous and more explosive. Back arc magma can be more similar to mid-ocean ridge basalt in some cases, but it can also be influenced by subduction fluids depending on how close it is to the arc. So the region becomes a mixing zone, and mixing zones can produce unexpected behaviour. Now, volcanoes themselves are not just mountains that erupt occasionally. They are plumbing systems. They have magma chambers, conduits, vents, and fractures. In underwater settings, those systems can be even more complex because water pressure affects eruption style. At shallow depths, underwater eruptions can be explosive because water interacts with magma and flashes into steam. At greater depths, pressure suppresses explosive degassing, and eruptions may be more effusive, producing lava flows. But even deep eruptions can be violent if gas content is high, or if the eruption interacts with water in certain ways. So underwater volcanism is not predictable in the same way as surface volcanism. This is one reason the Tonga region is difficult to monitor. Many of its volcanoes are underwater. They can erupt without anyone seeing them directly. The first signs might be seismic signals, changes in water chemistry or floating pumice. Sometimes a volcano can build an island and then erode away again. Sometimes it can collapse, producing landslides. Sometimes it can erupt explosively and generate tsunamis. So the volcanic side of the Tonga system is part of the hazard landscape. Now, the low basin also contains hydrothermal vents. Hydrothermal vents are one of the most fascinating features of the deep ocean. They are places where seawater circulates through hot rock, becomes heated, picks up minerals, and then emerges as mineral-rich fluid. When this hot fluid meets cold seawater, minerals precipitate, forming chimneys and deposits. These vents support ecosystems based on chemosynthesis. Microbes use chemical energy from the vent fluids to produce organic matter. Other organisms feed on these microbes. Hydrothermal vent ecosystems are some of the most unusual on Earth. They do not depend on sunlight, they depend on the Earth's internal heat. In the Lao Basin, hydrothermal systems are influenced by both spreading and subduction. This can create vents with unusual chemical compositions compared to mid-ocean ridge vents. This matters scientifically because it allows researchers to study how different tectonic settings influence vent chemistry and biology. So the Tonga region is not just a hazard zone, it is also a zone of discovery. But again, discovery comes with difficulty. Hydrothermal vents are hard to locate. They require specialized instruments. They are often found by detecting chemical plumes in the water, like elevated methane or hydrogen sulfide, or by detecting temperature anomalies. Once found, they can be studied with submersibles and remotely operated vehicles, but the region's remoteness makes such missions rare. Now, when you combine arc volcanism, back arc spreading, hydrothermal activity and deep subduction, you get a region where the seafloor is constantly being reshaped. This reshaping happens at different scales. At the largest scale, plates move and basins open over millions of years. At intermediate scales, earthquakes shift faults and cause landslides. At smaller scales, eruptions build new volcanic cones and lava flows. At the smaller scales, hydrothermal deposits accumulate and microbial mats grow. So the seafloor is a living landscape in a geological sense. This is why scientists describe it as being in motion. Now, there is another reason this matters for the Tonga Trench's reputation. When the seafloor is in motion, it can create hazards that are difficult to anticipate. For example, underwater volcanic eruptions can generate pumice rafts, huge floating fields of pumice that can drift across the ocean. These can affect shipping and marine ecosystems. Underwater landslides can generate tsunamis. Back arc spreading can create earthquakes in unexpected locations, not just at the trench. Hydrothermal activity can alter water chemistry and affect local ecosystems. So the region's activity is not confined to one boundary, it is distributed. Distributed activity is hard to monitor because you need instruments in more places, and in a remote region, that is challenging. Now, there is also a scientific reason why the seafloor in motion is unsettling. It complicates the story of how subduction zones work. We often teach subduction as a simple diagram. One plate goes down, volcanoes form above, earthquakes occur along the boundary. But Tonga shows that subduction zones can be coupled to extension behind the arc. They can create back arc basins. They can produce complex mantle flow patterns. So Tonga is a reminder that tectonic systems are three-dimensional and dynamic. They evolve over time. This matters for understanding other subduction zones, because it shows what is possible. It shows that subduction can lead to basin opening. It shows that slab pull can reshape plates. It shows that volcanism can be distributed. So Tonga is not just a local curiosity, it is a case study. Now, let's bring this back to a human sense of scale. When you stand on an island in Tonga, the ground feels solid. The ocean feels steady. The horizon looks calm. You do not feel the seafloor spreading behind you. You do not feel magma moving beneath the arc. You do not feel the slab sinking beneath the trench. But all of that is happening. That disconnect is part of what makes the region feel unsettling. The surface experience does not match the deep reality. It is like living above a factory that never shuts down, except the factory is the Earth itself, and the work it is doing is the reshaping of the crust. Now, scientists who study this region often have to think in multiple timescales at once. They think about the immediate timescale of earthquakes and eruptions. They think about the decade timescale of monitoring and hazard assessment. They think about the million-year timescale of basin opening and arc migration. and they think about the deep mantle timescale of slab descent and recycling. This multi-timescale thinking is part of what makes geology both fascinating and difficult, because it forces you to accept that the Earth is always changing, but usually too slowly for humans to notice. And then, sometimes it changes fast enough that you cannot ignore it. Now, the Tonga region has provided one of the clearest examples of that sudden change in recent years, with the eruption that shook the planet. So the next step is to focus on that event, not just as a news headline, but as a reminder of what this system is capable of. Because the eruption of Hunga Tonga Hunga Ha'apai was not just a volcanic explosion. It was a demonstration of how the Tonga system can connect the deep Earth to the atmosphere, the ocean, and the entire planet in one moment, and why scientists who study this region never fully relax, even when the ocean looks perfectly calm. There are moments when the Earth reminds everyone, not just scientists, that it is still an active planet. Most of the time, the planet's biggest processes happen quietly. Plates move a few centimetres a year, volcanoes build slowly, trenches deepen and fill with sediment over millions of years. The surface world carries on, and the deep world does its work out of sight. But every so often, something breaks through that quiet. Something large enough that you can't ignore it, even if you live on the other side of the planet. For Tonga, that moment came with the eruption of Hunga Tonga Hunga Ha'apai. It wasn't just an eruption that affected a local coastline. It wasn't just a plume of ash and steam. It wasn't just a loud explosion. It was a planetary event. The kind of event that made scientists sit up, not because they didn't know Tonga was active, but because the scale and the reach were so dramatic that it forced everyone to pay attention to the same patch of ocean at the same time. It shook the whole planet in more than one way. It shook the atmosphere. It shook the ocean. It shook the way people think about underwater volcanoes. And it reminded scientists that the Tonga region is not only deep and mysterious, it is capable of producing events that ripple outward far beyond its borders. Now, when most people imagine a volcanic eruption, they imagine a mountain on land, lava, ash, a crater glowing red, maybe a column of smoke rising into the sky. Hunga Tonga Hunga Ha'apai did not fit that picture neatly. This volcano was partly underwater and partly above water, sitting in the Tonga Volcanic Arc. It was not a towering mountain you could hike up and photograph from a safe distance. It was a volcanic system hidden under the sea, with only small islands showing above the surface. That matters because water changes everything. Water changes pressure. It changes how gases behave. It changes how magma fragments. It changes the violence of explosions. It changes how energy transfers into the surrounding environment. When magma meets water, you don't just get lava cooling quietly. You can get a violent interaction called a phreatomagmatic eruption. In simple terms, hot magma and cold seawater collide. The water flashes into steam. The rapid expansion creates explosions. The magma shatters into fine particles. Ash and steam are blasted upward. This can produce an eruption that is far more explosive than many purely lava-driven eruptions. And in Tonga, the eruption had the perfect conditions to become something extreme. It was a shallow submarine system with enough water to drive explosive steam generation, and enough magma and gas to keep feeding the event. When the main eruption happened, it produced a towering plume that reached high into the atmosphere. This wasn't a modest ash cloud. It was a massive vertical column that punched upward with incredible force. The eruption also produced a shockwave. People sometimes use that word casually, like it just means a loud bang. But in this case, it was literal. The eruption generated pressure waves that travelled through the atmosphere and were detected around the world. Instruments recorded it. People heard it in distant places. The sky itself carried the signal. That is not normal. It is not something most eruptions do. It is the kind of thing you associate with the largest explosive events, the kind that make global headlines. And this one happened in the middle of the ocean. Now, the shockwave was only one part of the story. The eruption also generated tsunamis. This is where the event becomes even more complicated because it was not a simple tsunami source. A classic tectonic tsunami is caused by seafloor displacement from an earthquake. The seafloor moves up or down, displacing water, sending waves outward. A volcanic tsunami can be caused by several mechanisms. An explosion can displace water directly. A collapse of part of the volcanic structure can displace water. A landslide can displace water. Pyroclastic flows can enter the ocean and push water outward. In the Tonga eruption, multiple mechanisms may have contributed. The eruption was powerful enough to disturb the ocean directly, and it may have involved collapse processes as well. The result was waves that reached nearby islands quickly, and waves that travelled far across the Pacific. So the event was not just an eruption, it was an ocean event. And it was not just an ocean event, it was an atmospheric event. It was one of those rare moments when the Earth's systems linked together in a way you could see and measure. Now, the eruption also had another effect that made it unusual. It injected material high into the atmosphere. Volcanic eruptions can influence climate when they inject sulfur dioxide into the stratosphere, forming sulfate aerosols that reflect sunlight and cool the planet. In Tonga's case, the eruption was notable for injecting a large amount of water vapour into the stratosphere. Water vapour is a greenhouse gas. It affects atmospheric chemistry and temperature. So scientists were interested not only in the ash and aerosols, but in the water vapour injection. This is not typical for most eruptions. Most eruptions inject ash and sulfur compounds, but this one, because it involved enormous amounts of seawater, had a different signature. So the eruption became a case study in how underwater or near-surface eruptions can affect the atmosphere differently than land eruptions. This matters because it expands the range of volcanic impact scientists have to consider. Now, if you were watching the eruption from a satellite, the images were stunning. A huge plume expanding outward like a flower. Concentric rings of pressure waves visible in cloud patterns. A column rising into the stratosphere. It looked almost unreal, but the reality on the ground, or rather on the islands, was harsh. Tonga experienced ashfall. Communications were disrupted. Infrastructure was damaged. The tsunami caused flooding. The shockwave was intense. For a small island nation, an event like this is not just interesting geology. It is disruption. It is danger. It is recovery. So the eruption also became a reminder of vulnerability. Remote does not mean safe. The fact that Tonga is far from major continents does not protect it from the hazards of its own geology. Now, from the scientific perspective, the eruption was both a tragedy and an opportunity to learn. Scientists do not celebrate disasters, but they do study them, because each major event provides data that cannot be obtained otherwise. In this case, the data came from many sources. Seismic sensors recorded the activity. Infrasound sensors recorded atmospheric pressure waves. Satellites recorded the plume and shock wave. Tide gauges recorded tsunami signals. Ocean sensors recorded pressure changes. Weather stations recorded atmospheric effects. So the eruption was observed in a multi-system way. This is one of the reasons it shook the whole planet. Not just physically, but in the sense that it created signals detectable everywhere. Now, why did this eruption happen in this region? Because Tonga sits above a subduction zone, and subduction zones feed volcanic arcs. The subducting slab releases water into the mantle melts, magma rises, volcanoes form, but the specific behaviour of any volcano depends on its magma supply, its plumbing system, and its interaction with water. Hunga Tonga Hunga Ha'apai had erupted before. It had shown signs of activity. It had built and destroyed land, so it was not a completely unknown volcano. But the scale of the 2022 eruption was beyond what many people expected. And this is another part of the fear scientists feel around the Tonga region. Even when you know a system is active, you don't always know what its upper limits are. Volcanoes can behave quietly for years and then erupt violently. Submarine volcanoes can hide much of their growth and instability underwater. a volcano can build a structure and then collapse it, so the system can surprise you. Now, the eruption also highlighted a problem in hazard monitoring. Monitoring underwater volcanoes is difficult. On land, volcanoes can be monitored with seismometers, GPS, gas sensors, and visual observation. Underwater, you cannot easily measure gas emissions. You cannot easily see deformation. You cannot easily observe changes in vents. You can place instruments on the seafloor, but that is expensive and difficult. So submarine volcano monitoring is less comprehensive. This means eruptions can occur with less warning. The Tonga eruption was a reminder of that. It showed that underwater volcanoes are not just minor features. They can produce major events. Now, there is also something psychologically unsettling about this eruption. It was an event that combined deep ocean invisibility with surface world impact. The volcano itself was mostly hidden. The processes leading up to the eruption were mostly hidden. And then the eruption was visible from space. It was like the ocean had been hiding something powerful and then suddenly revealed it. This fits the broader theme of the Tonga Trench and its region. Hidden forces beneath calm surfaces. Now, the eruption also connects back to the trench in another way. The subduction system creates the conditions for volcanism, but it also creates the stress environment. Earthquakes and volcanic activity can interact. A large earthquake can alter stress and influence magma movement. Magma movement can alter stress and influence earthquakes. The connections are complex and scientists study them carefully, but in an active region like Tonga, the possibility of interactions adds another layer of uncertainty. So when a major eruption happens, scientists don't just look at the volcano, they look at the region's seismic activity, they look at the subduction zone, they look at the back arc basin, they look at the whole system, because the system is connected. Now, after an event like this, one of the big questions is, what does it tell us about the region's future? Does it change the hazard landscape? Does it relieve pressure or increase it? Does it alter the volcanic system? Does it change the seafloor shape? Does it create new instability? Scientists can study the aftermath. They can map changes. They can measure new deposits. They can track ongoing seismicity. But they cannot say with certainty what will happen next. And that uncertainty is part of what makes the region feel terrifying. Not terrifying like a horror movie. Terrifying like a reminder that nature can do things that exceed our expectations. Now, the Tonga eruption also showed the limits of our exploration and monitoring technology. We can see the surface effects, we can record the signals. But the deep details, the exact sequence of events underwater, the precise mechanism of tsunami generation, the internal collapse processes, those are harder to reconstruct. So even after a global event, the deep ocean keeps some secrets. That is another reason scientists remain cautious. The trench and the Arc region do not give up information easily. Now, after seeing what Tonga's volcanic system can do, the next question becomes practical. How do we explore a place like this? How do we send machines into a trench environment? How do we map the seafloor? How do we measure chemistry and biology? How do we monitor hazards? Because the trench is not just deep and dark. It is remote, crushing, and connected to an active tectonic system. So the next step is to look at the engineering challenge, how we explore a place that tries to crush our machines, and why every mission into the deep feels like a careful negotiation between curiosity and caution. Exploring the deepest parts of the ocean is not like exploring anywhere else on Earth. When humans explore mountains, the challenge is thin air, cold temperatures, and weather. When humans explore deserts, the challenge is heat, dehydration, and distance. When humans explore space, the challenge is vacuum, radiation, and the complete absence of breathable air. But when humans explore trenches like the Tonga Trench, the challenge is something more blunt. The environment is trying to crush your machines, not in a dramatic, personal way, but in a mechanical way that feels almost indifferent. The pressure is always there. The cold is always there. The darkness is always there. And the distance is always there. meaning that even if something goes wrong, you cannot reach down and fix it quickly. So deep trench exploration becomes a test of engineering discipline as much as scientific curiosity. It's not enough to want answers. You need tools that can survive the environment long enough to bring those answers back. And in the Tonga Trench, that is never guaranteed. Now, the first thing to understand is that we don't explore trenches by sending humans down there regularly. Human-occupied deep submersibles exist, but they are rare and expensive to operate. They require extreme safety margins. They require specialized support ships. They require extensive planning. Most trench exploration is done with unmanned systems. That means remotely operated vehicles, autonomous vehicles, and deep-sea landers. Each approach has strengths and weaknesses, and the Tonga Trench's environment forces engineers to make hard choices. Because the deeper you go, the more difficult everything becomes. Let's start with the simplest kind of deep-sea exploration tool, the lander. A deep-sea lander is essentially a free-falling platform. It is lowered into the ocean, but not on a cable the whole way down. Instead, it is released from a ship and sinks under its own weight. A typical lander has ballast weights to make it sink. It has buoyant materials to ensure it can float back up when it's time. It has instruments attached, cameras, sensors, sometimes baited traps, sometimes sample collectors. The lander sinks for hours depending on depth. It reaches the bottom. It sits there, collecting data. Then, when it's time to return, it releases its ballast, usually using an acoustic signal from the surface. Once the weights drop, the lander becomes buoyant and rises back up. This sounds simple, and in concept, it is. But at trench depth, nothing stays simple. The first challenge is pressure. Every instrument on the lander has to survive thousands of meters of a descent. That means pressure housings for electronics. That means seals that won't fail. That means materials that won't crack. Any air-filled space is a problem. Even something as basic as a battery becomes complicated at depth. Batteries have to operate in cold temperatures. They have to be sealed. They have to be reliable. Cameras have to be housed behind pressure-resistant windows. Lights have to work efficiently. Sensors have to remain calibrated. And all of it has to survive not just pressure, but time under pressure. Because the pressure doesn't only test strength, it tests endurance. A housing might survive the descent but fail after hours on the bottom because of tiny leaks or slow deformation. So landers are designed with conservative safety margins. They are often overbuilt because failure is expensive. Now the second challenge is corrosion. Seawater is corrosive, especially over long durations. Salt water attacks metals. It creeps into tiny gaps. It can cause galvanic corrosion when different metals interact. So material selection matters. Titanium is commonly used because it resists corrosion and has high strength. Certain steels can be used with careful protection. Plastics and composites can be used in some parts. But even corrosion-resistant materials can be challenged by long deployments. So engineers design landers to be robust and to minimize vulnerable joints and connections. Now the third challenge is communication. As we mentioned earlier, radio communication does not work well underwater. GPS does not work underwater. So landers communicate with the surface using sound. Acoustic communication can send simple commands like release ballast or send status. But acoustic communication is not high bandwidth. You cannot stream video from the bottom of the trench to the ship above. The data is usually stored on board and retrieved when the lander returns. This means trench exploration often has a delayed payoff. You deploy the lander, you wait, you recover it, and only then do you see what it recorded. That waiting can be stressful, because you don't know what's happening down there. If the lander fails to release ballast, it might never come back. If a component fails, you might recover the lander but lose the data. So every deployment carries uncertainty. Now, landers are only one approach. If you want more active exploration, you need vehicles that can move. That brings us to remotely operated vehicles, ROVs. ROVs are tethered vehicles controlled from a surface ship. They have cameras, lights, manipulator arms and sensors. They can move around, collect samples and provide live video. ROVs are extremely useful for deep-sea exploration, but trench depths make tethered operation difficult. The deeper you go, the longer the tether must be. A tether that is 10 kilometers long is heavy. It creates drag, it can tangle, it can be affected by currents. Managing it requires powerful winches and careful ship handling. So trench-capable ROVs are rare. They exist, but they are not common, and operating them is complex and expensive. Now, another option is autonomous underwater vehicles, AUVs. AUVs are untethered. They are programmed to follow a mission plan. They can map the seafloor using sonar, collect water chemistry data, and sometimes take images. Because they are untethered, they avoid the tether problem. But autonomy introduces its own challenges. An AUV has to navigate without GPS. It has to avoid terrain. It has to manage battery life. It has to return to a recovery point. In the deep ocean, navigation often relies on inertial systems and acoustic positioning from the surface. The vehicle estimates its position based on motion sensors, but small errors accumulate over time, so long missions can lead to uncertainty in location. In a trench environment with steep slopes, this matters. A navigation error could mean crashing into a wall or descending into a dangerous zone, so trench AUV missions require careful planning and conservative navigation strategies. Now, beyond landers, ROVs and AUVs, there are also human-occupied vehicles and specialised deep submersibles. The idea of sending a human into the trench is both inspiring and unsettling. On one hand, humans can observe directly. They can make decisions in real time. They can respond to unexpected discoveries. On the other hand, human safety requires extreme reliability. The pressure hull must be flawless. Every system must have redundancy. Emergency systems must exist. Rescue options are limited, so human trench dives are rare. Historically, a small number of manned dives have reached extreme depths. These dives are milestones in exploration history, but they are not routine science missions. Most trench science is done by machines. Now, one of the most important engineering concepts in trench exploration is pressure housing design. As we mentioned earlier, spheres are favoured because they distribute stress evenly. A spherical hull can resist pressure better than a cylindrical one of the same thickness. This is why many deep submersibles have spherical crew compartments or instrument housings. But a sphere is hard to build. It requires precision machining. It requires strong materials. It requires careful welding or forging. Even a tiny flaw can be catastrophic at depth. So quality control is critical. Engineers use non-destructive testing methods like ultrasound and radiography to inspect hulls. They test components in pressure chambers. They simulate conditions as much as possible. But even with testing, the real ocean is different. Pressure chambers can replicate pressure, but they may not replicate all conditions. They may not replicate long-duration exposure, vibration, or unexpected impacts. So real deployments are always a test. Now, another crucial technology is buoyancy. In shallow water, buoyancy can be achieved with air-filled floats. In the trench, air-filled floats collapse, so trench vehicles use syntactic foam. Syntactic foam is a composite material filled with tiny hollow spheres, usually glass or ceramic, embedded in resin. These spheres can withstand high pressure, allowing the foam to remain buoyant at depth. This material is one of the key enablers of deep exploration. Without it, vehicles would struggle to control buoyancy. But syntactic foam is expensive and heavy, and it must be carefully designed for the target depth. If the foam is not rated for the depth, it can crush, losing buoyancy and causing the vehicle to sink. So engineers have to match foam properties to mission requirements. Now, another challenge is power. Batteries have improved over the years, but deep-sea missions still face energy limits. Lights consume power. Thrusters consume power. Sensors consume power. Computers consume power. So mission duration is limited by battery capacity. Some landers can stay down for long periods because they use low-power sensors and minimal lighting. Active vehicles have shorter endurance because movement and imaging require more energy. So engineers balance mission goals against power constraints. Now, beyond these technical challenges, there is a practical challenge: recovery. The ocean is big. A lander or vehicle returning to the surface might drift with currents. It might surface far from the ship. It might surface at night. It might surface in rough seas. So recovery requires tracking. Landers often have radio beacons, GPS receivers that work once they surface, flashing lights, and sometimes acoustic pingers to help locate them. But recovery can still be difficult, and if a vehicle is lost, it is often lost permanently. This is why trench exploration feels like gambling, even when everything is planned carefully. You can do everything right and still lose the machine. Now, the Tonga Trench adds extra challenges because it is remote. Remote means fewer nearby ports. It means longer travel times. It means limited rescue options. It means higher costs. It also means fewer opportunities. A trench expedition is not something you can do casually. It requires a research vessel, crew, equipment, funding, and time. So the Tonga Trench has been explored less than it deserves, not because it is uninteresting, but because it is hard to reach and hard to work in. Now, another aspect of trench exploration is mapping. Before you send a vehicle down, you want to know what the seafloor looks like. Ships use multi-beam sonar to map the seafloor. This produces bathymetric maps, but at great depth, resolution decreases, the sonar beams spread, the details become less sharp, so trench maps can be less detailed than shallow maps. AUVs can improve this by mapping closer to the seafloor, producing higher resolution data. But AUV mapping covers smaller areas, so mapping is a trade-off between coverage and detail. In Tonga, where the terrain can be steep and complex, detailed mapping matters. It helps avoid hazards. It helps identify interesting features. It helps plan sampling sites. So mapping is often the first step in exploration. Now, sampling is the next challenge. Collecting sediment cores at trench depth requires corers that can penetrate deep mud and retrieve intact layers. These layers can tell scientists about past events, organic matter accumulation, and chemical conditions. Collecting biological samples requires traps or suction samplers. Collecting rock samples is difficult because the trench bottom is often sediment covered, but volcanic and tectonic features can provide exposed rock. Sampling water chemistry requires bottles that can close at depth and remain sealed. Each sample type requires specialized equipment, and each piece of equipment has to survive pressure. Now, even after you collect samples, you face another problem. Bringing them back changes them. Pressure-sensitive organisms may not survive ascent. Chemical conditions can change as pressure decreases. Gases can come out of solution. So scientists have to process samples quickly and carefully. In some cases, specialized pressure-retaining samplers are used to keep organisms and fluids at high pressure during recovery. These are complex and rare, but they can preserve deep conditions. This is another example of how the trench forces engineering innovation. Now there is also a human element to trench exploration that doesn't show up in the technology. Patience. Trench missions take time. Descent can take hours. Bottom time may be limited. Ascent takes hours. Recovery takes time. Processing takes time. So a trench expedition involves long periods of waiting and careful monitoring. It is not a fast-paced adventure. It is slow, methodical work, and in that slowness, uncertainty builds. Is the lander still functioning? Will it release ballast? Will it return? Did the camera record anything? Did the sensors work? So trench exploration is emotionally demanding. Scientists are trained to handle uncertainty, but it still matters, because each mission represents months or years of preparation. Now, despite all these challenges, exploration continues, because the trench holds answers. It holds information about deep earth processes. It holds ecosystems that test the limits of biology. It holds sediments that record past earthquakes and eruptions. It holds clues about how the planet cycles material. So scientists keep going back. They build better vehicles, they improve sensors, they develop new mapping techniques, they share data, they collaborate internationally, and slowly the unknown becomes less unknown. But it never becomes fully known, because the trench is too big, too deep, and too difficult to explore completely. Now, after understanding how we explore a place that tries to crush our machines, the next question becomes even bigger. Why do we bother? Why does the Tonga Trench matter beyond Earth science? Why does it matter beyond hazard monitoring? The answer is that the trench might teach us something about other worlds. Because when you look at the Hadal zone, you're looking at an environment that resembles conditions that might exist elsewhere in the solar system. Dark oceans under ice, high pressure, cold temperatures, chemical energy instead of sunlight. So the next step is to look at what Tonga might teach us about other worlds, and why the deepest places on Earth are often the closest thing we have to an alien ocean. When scientists talk about other worlds, it's easy to imagine they're talking about places that are completely separate from us. Mars, with its dust storms and dry valleys. Venus, with its crushing atmosphere and toxic clouds. Europa and Enceladus, with their hidden oceans under ice. Titan, with its methane lakes and thick orange haze. These places feel distant, both physically and emotionally. Their names on a screen, images from spacecraft, diagrams in textbooks. But the deeper you look into Earth's most extreme environments, the more you realise something strange. We already live on a planet that contains alien worlds inside it. The Hadal zone, including the Tonga Trench, is one of the closest things we have to an environment that feels truly off limits. It's dark, it's cold, it's under pressure that would destroy most equipment, it's far from sunlight, it's isolated, and yet it is active. Not just geologically, but biologically. Life exists there, chemistry works there, energy flows there. And that combination is exactly why the Tonga Trench matters for understanding other worlds. Because when scientists look at places like Europa or Enceladus, they're not just asking, is there water? They're asking, is there energy? Is there chemistry? Is there stability? Is there a way for life to exist? Earth's deep trenches don't give us direct answers about alien oceans, but they give us something almost as valuable. They give us a test environment, a place where we can study how life behaves without sunlight, how chemistry supports ecosystems, how geology shapes an ocean floor, and how technology can operate in extreme conditions. So Tonga becomes a kind of training ground for planetary science, not because it's similar in every detail, but because it forces us to confront the same core problems. How do you explore an ocean you can't easily reach? How do you search for life where you can't see? How do you measure chemistry in a place that tries to destroy your instruments? How do you interpret indirect signals? These are the same questions you face on other worlds. Now let's start with the most obvious connection. Hidden oceans. Some of the most exciting targets in the search for life in the solar system are icy moons. Europa, one of Jupiter's moons, is believed to have a global ocean beneath an ice shell. Enceladus, one of Saturn's moons, has plumes of water vapour and ice particles erupting from cracks near its south pole, suggesting an ocean beneath. There are other candidates too, like Ganymede and Callisto, and possibly even Titan in a different form. The reason these worlds are exciting is simple. Where there is liquid water, there is potential for life. But liquid water alone is not enough. Life needs energy. On Earth, most life ultimately depends on sunlight, either directly through photosynthesis or indirectly through food chains. In the Hadal zone, sunlight does not reach, yet life exists. So the Hadal zone is proof that sunlight is not the only energy source that can support ecosystems. In the deep ocean, chemical energy can support life. Hydrothermal vents provide chemical gradients that microbes can use. Organic matter sinking from the surface provides food for scavengers and decomposers. In some environments, methane seeps provide energy. So the Tonga region, with its subduction-driven volcanism and back arc spreading, is a place where chemical energy sources exist. Hydrothermal systems in the Lau Basin, for example, show how tectonic activity can create chemical environments that support life without sunlight. This is important for icy moons, because if an ocean exists beneath ice, sunlight won't reach it. Any life there would likely depend on chemical energy, possibly from hydrothermal activity on the seafloor, so Tonga helps us study how such ecosystems might work, not in a direct copy, but in a conceptual way. Now, another connection is pressure. The Hadal zone is under immense pressure. In trenches like Tonga, pressure is high enough to challenge both biology and technology. On icy moons, pressure at the bottom of a deep ocean could also be enormous, depending on ocean depth and gravity. So studying how organisms and materials behave under pressure on Earth can inform what might be possible elsewhere. For example, deep-sea organisms have adaptations to pressure. Their proteins function under pressure, their membranes remain stable. Their enzymes work in cold, high-pressure conditions. These adaptations show that life can evolve to function in environments that would destroy surface organisms. So the existence of Hadal life expands our understanding of the range of possible life conditions. It tells us that high pressure does not automatically mean sterile. Now, another connection is temperature. Trench water is cold, it is near freezing, yet life exists. On icy moons, ocean temperatures are expected to be cold, though hydrothermal vents could create warmer localized zones. So Tonga and other Hadal environments show how life can function in cold conditions and how ecosystems can exist with low energy input. This matters because energy availability is one of the main constraints for life in deep, dark oceans. If energy input is low, life might exist, but at low density. It might be sparse, it might be slow, it might be hard to detect. This is a key point for astrobiology. Life might not be dramatic, it might not be obvious, it might not form large organisms, it might be microbial and subtle. So studying sparse deep-sea ecosystems helps scientists develop realistic expectations. Now, the Tonga Trench also teaches us about isolation and connectivity. At first glance, a trench seems isolated. It is deep and remote. It is far from surface conditions, but it is not truly isolated. Organic matter sinks from the surface. Water masses circulate, sediments slide down. Earthquakes disturb the environment. Chemical inputs arrive from geological processes. So the trench is connected to the rest of the ocean system, but in limited and delayed ways. This is important for thinking about alien oceans. If Europa has an ocean, how connected is it to the surface? Are there cracks in the ice that allow exchange? Are there plumes that carry material upward? Are there processes that bring oxidants from the surface ice down into the ocean? Scientists think this matters because life needs chemical gradients. If the surface produces oxidants through radiation chemistry, and those oxidants can be transported into the ocean, that could provide energy for life. So the question of connectivity between layers is crucial. Earth's trenches are not the same as Europa's ice shell, but they help scientists think about how isolated environments can still receive inputs that support life. Now, there is another lesson Tonga offers. Geology creates habitability. On Earth, geology is not just background scenery, it actively shapes where life can exist. Subduction recycles material. It creates volcanoes. It creates hydrothermal systems. It moves nutrients. It drives chemical cycles. In the Tonga region, the subduction zone drives volcanism and hydrothermal activity. It shapes the seafloor. It creates chemical environments. This shows how an active interior can support life by providing energy and nutrients. In planetary science, this leads to a key question. Does an ocean world have an active seafloor? If Europa's seafloor is geologically active, it could support hydrothermal vents. If it is inactive and cold, energy sources might be limited. So Tonga's lesson is that habitability is not just about having water. It's about having an active system that creates chemical opportunities. Now, there is also a lesson about exploration itself. Exploring the Tonga Trench is difficult. It requires specialised vehicles, pressure-resistant housings, acoustic communication, careful navigation, and expensive missions. Exploring Europa's ocean would be far harder. You would need a spacecraft to travel there. You would need to land on ice. You would need to drill through kilometers of ice. You would need to deploy a submersible into an ocean you cannot see, and you would need to do it all with limited power and limited communication, millions of kilometers from Earth. So Tonga is not just a scientific analogue, it is a technological analogue. It helps engineers test ideas for exploring extreme oceans, for example, autonomous systems. In the trench, communication is limited. Vehicles must operate with autonomy. They must handle uncertainty. On Europa, autonomy would be essential. Communication delays would prevent real-time control. So trench exploration pushes autonomy development, which supports future planetary missions. Another example is pressure-resistant instrumentation. Trench missions require sensors that can function under high pressure. Planetary ocean missions would require the same. Another example is sampling and contamination control. When exploring Earth's deep ocean, scientists try to avoid contaminating samples and environments. On another world, contamination control would be even more critical, because you would not want to introduce Earth microbes into an alien ocean. So trench exploration forces scientists to think carefully about clean sampling. Now, Tonga also teaches a lesson about interpretation. When you explore a trench, you don't get a complete picture. You get limited samples, you get partial maps, you get snapshots of biology and chemistry. You have to infer the bigger story from incomplete data. That is exactly how planetary science works. You rarely get perfect data, you get fragments. So the trench teaches humility. It teaches that even on Earth, with ships and sensors and decades of research, the deep ocean remains partly unknown. So on another world, uncertainty will be even greater. This doesn't mean exploration is hopeless. It means expectations must be realistic. Now, there is another connection that is easy to miss. The Tonga Trench is a place where the Earth recycles material deep into the mantle. Sediments, water and crust are carried down. This recycling influences the planet's long-term chemistry. On other worlds, recycling processes could influence ocean chemistry too. For example, if a moon has an ocean and an active rocky interior, water-rock interactions could produce hydrogen, methane, and other compounds. These compounds could support microbial life. So understanding how Earth's subduction and deep cycling work helps scientists think about how other worlds might cycle chemicals. Now, it's also worth mentioning that Tonga's region shows how extreme events can reveal hidden systems. The eruption that shook the planet revealed how powerful an underwater volcano can be. It created global signals. It forced scientists to study the region in detail. On other worlds, we may also rely on rare events. Plumes on Enceladus, for example, provide a way to sample the ocean without drilling through ice. You can fly through the plume and analyse the particles, so in planetary exploration sometimes the world itself provides a sampling mechanism. Tonga's eruption was not helpful in that sense, but it was a reminder that hidden systems can produce visible signals. This is important because it suggests that we might detect life or chemistry indirectly, through plumes, surface changes, or atmospheric signatures. Now, after all of this, you might wonder, if Tonga can teach us so much, why does it still terrify scientists? Because it is not just an analogue for other worlds. It is a reminder of how hard it is to understand our own world. The trench is deep, it is active, it is remote, it is dangerous for equipment. It is connected to hazards like earthquakes, tsunamis and eruptions. So Tonga is both a research target and a hazard zone. It is a place where the planet shows its power. And when you study that power, you learn more about the Earth, but you also learn how much remains uncertain. Now, as we move toward the end of this journey, there is one final thought that keeps coming back. The Tonga Trench will still be there when we look away. It will keep sinking plates, it will keep producing earthquakes, it will keep feeding volcanoes, it will keep hosting life in the dark, and that permanence is both comforting and unsettling. Comforting because it means the Earth is stable enough to have long-term systems. Unsettling because it means the Earth does not need us to understand it in order to keep doing what it does. So the next step is to bring everything together, not with a dramatic conclusion, but with a quiet reminder of what the trench represents and why scientists keep returning to it even when it refuses to give up its secrets easily. The strange thing about the deepest places on Earth is that they don't feel urgent until they suddenly are. Most of the time, the Tonga Trench is not in the news. It isn't trending. It isn't part of everyday conversation. It doesn't show up in your routine unless you're the kind of person who reads about oceanography for fun, or you work in geology, or you happen to live in the Pacific and you've learned, from experience, that the ocean can change its mood quickly. For everyone else, the trench is just a name on a map, if it's anything at all, a line in the ocean, a feature in a documentary, a place so far away that it might as well be imaginary. And yet, the Tonga Trench is real. It is there right now. It is deeper than most of the ocean. It is part of one of the most active subduction systems on Earth. It is linked to earthquakes that happen in places that shouldn't break, and to volcanoes that can disturb the atmosphere, and to tsunamis that do not wait for permission before they arrive. That's the uncomfortable truth. The trench will still be there when we look away. It doesn't pause because we stop paying attention. It doesn't calm down because the surface seems quiet. It doesn't become less powerful because we feel small compared to it. It just keeps going. And that is the part that scientists don't always say out loud, but they always understand in the background. The planet does not need our awareness to keep functioning. Now, it's easy to hear that and feel a kind of fear, or maybe a kind of resignation. Like, what's the point of studying something you can't control? What's the point of mapping a place that keeps changing? What's the point of trying to predict hazards that can never be fully predicted? But that isn't how most scientists think about it. For many of them, the trench's persistence is exactly why it matters. Because the trench is not just a threat, it is a system. It is a part of the Earth's recycling process. It is a place where the surface world is pulled down into the deep. It is a place where old crust is destroyed and returned to the mantle. It is a place where water locked in minerals is carried down and released again. It is a place where chemical cycles are driven by geology. It is a place where energy moves from the interior of the planet into the ocean, shaping both the seafloor and the life that lives there. So when scientists study Tonga, they are not just studying danger, they are studying how the Earth works, and there is a difference. Danger is an event, a system is something that continues. Now, the Tonga Trench system is one of those rare places where you can see through data and maps and seismic signals how many parts of the Earth connect to each other. You have the surface ocean, calm or stormy depending on the day. You have the deep ocean, cold and dark, carrying water masses and nutrients slowly around the planet. You have the seafloor, shaped by tectonics, cut by trenches, lifted into arcs, split into basins. You have the subducting slab, sinking into the mantle, releasing fluids, changing minerals, producing deep earthquakes. You have the volcanic arc, building islands and destroying them again. You have the back arc basin stretching open behind the arc, creating new crust. And you have life somehow living through all of it, from microbes in sediment to scavengers in the Hadal darkness. So the trench becomes a kind of meeting point. Not a meeting point you can visit easily, but a meeting point in the sense that it links processes that happen on very different scales. That's why it's so valuable. Now, if you think back to everything we've covered, you can start to see why scientists describe the Tonga region with a mix of excitement and caution. The depth itself is intimidating, because it represents the limits of exploration. The pressure is intimidating because it represents the limits of engineering. The darkness is intimidating because it represents the limits of direct observation. But the real intimidation comes from what the trench reveals about the Earth. It reveals that the planet is still active at every level, not just at the surface, where storms and waves are visible, but in the deep, where plates sink and break and transform, where rock behaves in ways we still don't fully understand, and where the boundaries of normal geology get pushed. Deep focus earthquakes are the perfect example. They happen at depths where rock should deform quietly, but it doesn't. It fails suddenly. It releases energy. It sends seismic waves through the planet. So the trench system reminds us that the Earth can still surprise us, even in areas where we think we understand the physics. Now, the tsunami problem is another reminder. Tsunamis are not mysterious in a basic sense, but they are difficult in practice. They depend on the details of seafloor motion, landslides, volcanic collapses, wave focusing, and coastline shape. Tonga's region has multiple tsunami sources, which makes it more complicated than a simple earthquake equals tsunami story. So the trench system reminds us that hazards are not always cleanly categorized. Nature does not separate events into neat boxes, it combines them. Now, the volcanic side of the story is perhaps the most emotionally obvious example of Tonga's power. The eruption that shook the planet was a moment when the deep world made itself impossible to ignore. It showed that an underwater volcano can influence the atmosphere and the ocean at the same time. It showed that a remote place can create global signals. It showed that our monitoring systems, while impressive, still have blind spots. So even in the age of satellites and global sensors, the Earth can still produce surprises. Now, there is another part of this story that is quieter but just as important: the life in the trench. When people think of terrifying places, they often imagine empty places. But the Hadal zone is not empty. It is inhabited. It is not crowded like a coral reef, but it is not barren either. Life exists in the sediments. Life swims in the water column. Scavengers find food. Microbes break down organic matter. Chemistry supports slow ecosystems. So the trench system reminds us that life is adaptable. It can persist in darkness, cold, and pressure. That has implications for Earth, because it expands our understanding of where life can exist, and it has implications for other worlds, because it makes the idea of life in hidden oceans feel less like fantasy, and more like a scientific possibility. Now, there is something else that scientists learn when they study places like Tonga. They learn patience, because the trench does not give answers quickly. A single expedition can take years of planning. A single dive can take hours of descent and ascent. A single sample can represent a tiny fraction of the trench environment, so progress is slow, and that slowness can be frustrating. But it also forces a certain mindset. Instead of expecting complete understanding, scientists learn to build understanding in layers. A better map here, a better seismic model there, a new species discovered in one trench, a new chemical measurement that changes an assumption, a new instrument that survives longer than the last one. Over time, the picture becomes clearer, not complete, but clearer, and that is enough to keep going. Now, if you step back, you can see the trench as something more than a place. You can see it as a reminder that the Earth is still shaping itself, a reminder that the ocean is not just a surface but a depth, a reminder that what looks calm can be under tension, a reminder that we live on a planet with powerful systems operating beyond our senses. And when you remember that, it changes how you see the world, not in a dramatic way, but in a quiet way. It makes you look at the ocean differently. It makes you realize that beneath the surface, there are landscapes we haven't seen, forces we can measure but not touch, and processes that will continue whether we watch them or not. Now, the phrase, "the trench will still be there when we look away," can sound like a warning, and it is, in a sense, because it means the hazards do not disappear when we ignore them. It means earthquakes will still happen. It means volcanoes will still erupt. It means tsunamis will still be possible. So awareness and preparedness matter, but it is also a kind of comfort. Because it means the Earth is stable enough to have long-term systems. It means the planet is not random chaos. It has patterns. It has cycles. It has processes that repeat and evolve, and the trench is part of that structure. Now, even if you never visit Tonga, even if you never see the trench, even if you never look at a bathymetric map again, it is still part of your planet. it is still part of the system that recycles crust. It is still part of the system that shapes the Pacific. It is still part of the ocean that influences climate and chemistry, so it is connected to you, even if you don't feel it, and that connection is one of the reasons scientists keep studying it. Not because they expect to tame it, but because understanding it helps us understand the Earth as a whole. Now, if you're listening to this while lying in bed, or while driving, or while doing something quiet, it might feel strange to think about something as intense as the Tonga Trench. It might feel like a distant story, but there's something calming about distant stories too, because they remind you that the world is bigger than your day, that there are processes happening far away, deep under the ocean, that will continue whether your inbox is full or empty, whether your plans work out or don't. The trench doesn't care about your schedule. It doesn't care about the time. It doesn't care about the noise of the surface world. It just exists, and it does what it does. And in a strange way, that can make your own worries feel smaller. Not unimportant, but less overwhelming. Because the planet has been doing this for a long time. And it will keep doing it. Now, if there's one thing to carry with you from this whole journey, it's not a single fact or a single number. It's the sense that the deepest places on Earth are not dead zones. They're active, connected, and full of unanswered questions. The Tonga Trench is terrifying because it is deep and powerful, but it is also fascinating because it is one of the clearest windows we have into the hidden workings of the planet. And even when we look away, even when we stop thinking about it, even when the ocean looks calm, the trench remains, quietly pulling the surface down into the deep, quietly feeding volcanoes, quietly shaping the seafloor, quietly hosting life in the dark, and waiting, in the way the Earth always waits, for the next moment when it will remind us that it is still here, still moving, and still full of places we haven't truly understood yet.